Hello there, and a most warm welcome to Physics with William, a quiet sanctuary where we gently take the largest, most profound questions in the universe, lower the lights just a little, and examine them together without the slightest hint of rushing. Tonight, we are going to ask a deceptively simple question, one that sounds almost elementary at first, but becomes infinitely stranger and more mesmerizing the longer you sit quietly with it. How much unimaginable force would it truly take to break the very fabric of spacetime? That is quite a dramatic, perhaps even startling question for such a peaceful, quiet evening. It sounds almost as though spacetime might be a delicate sheet of stained glass waiting for the heavy strike of some colossal cosmic hammer, or perhaps an ancient, creaking wooden floorboard that could finally give way if a sufficiently heavy, dying star stepped too heavily upon it. Yet physics, as is so often the case, is not quite that straightforward or easily pictured. Space-time is not a physical material in any ordinary, tangible sense. You cannot hold a small, shimmering piece of it in your hand, fold it neatly away into a forgotten drawer, or accidentally scrape and damage it while clumsily moving heavy furniture. Still, this vast universe contains celestial objects and violent events so unimaginably extreme that the fundamental structure of space and time itself can be bent, stretched, squeezed, and forcefully pushed into mysterious conditions where even our very best, most sophisticated theories stop giving clear, reliable answers. Before we venture any farther into this cosmic journey, take a gentle moment to notice exactly where you are listening from tonight. Perhaps you are nestled in a cozy bedroom with the heavy curtains drawn against the night, resting on a soft sofa with a single warm lamp still glowing. Or perhaps you find yourself somewhere much less restful, such as a rigid airport chair designed by someone who clearly harbored a deep dislike for the delicate curves of the human spine. What distant part of this vast world are you in right now? And what quiet hour of the night is it there? While you comfortably settle in, consider something else for a moment. Have you ever felt the surface beneath you flex ever so slightly under weight? Think of a soft mattress gently sinking when you first lie down, an old wooden footbridge shifting subtly under your quiet footsteps, or a well-worn sofa cushion giving up all of its resistance after years of loyal, comforting service. Those are merely ordinary, everyday materials responding naturally to physical pressure. The profound question before us tonight is whether reality itself, the very stage of our existence, can do something remarkably similar, and what chaotic wonders might happen if that cosmic pressure becomes far too great to bear. If you find these slow, meditative journeys through science relaxing, deeply interesting, or simply useful for giving your wandering thoughts somewhere peaceful and calm to go, you can leave a kind like and subscribe to our quiet channel. It genuinely helps more kindred listeners find this small, comforting corner of physics, especially those weary souls who enjoy learning about the mysteries of black holes at an hour when most sensible people are fast asleep. For now, there is absolutely nothing you need to remember, calculate, or actively solve. Just let yourself float and follow these grand ideas at a perfectly easy, unhurried pace. The evocative phrase "break spacetime" creates an immediate, striking picture in our minds, but it can also be somewhat misleading. In our daily lives, breaking usually means that something once beautifully connected becomes permanently separated. A taut rope suddenly snaps, a brittle glass window cracks, or a dry biscuit breaks cleanly in half, often when you are trying to dip it into a hot cup of tea with far more confidence than that fragile biscuit ever deserved. In each of these everyday cases, the object is made of smaller, microscopic pieces held tightly together by invisible forces. Apply enough external stress, and those delicate bonds inevitably fail. Spacetime, however, does not appear to be built in quite that same mechanical way, at least not at the microscopic scales we can ever hope to observe directly. It is, instead, the very fundamental framework in which physical positions, vast distances, quiet durations, and all motion have any meaning at all. Asking what could possibly break it is a little like asking what could tear the abstract idea of distance itself, or put a physical crack right through the steady, unstoppable passage of a single second. Yet, physicists themselves do occasionally use language that comes remarkably close to this. They speak softly about mysterious singularities, where our best-known equations break down and produce mathematical quantities that become infinitely unbounded. They closely study silent horizons that divide different regions of the universe in ways no ordinary physical wall could ever hope to manage. They eagerly investigate incredibly violent collisions that send ripples of gravitational disturbances traveling across billions of light-years. They even consider whether spacetime might possess a minute, fundamental, smallest possible structure, and whether that delicate structure could somehow become utterly unstable under extreme, chaotic conditions. None of this, of course, means that the universe is about to suddenly split wide open right beside your warm bed. Rather, it simply means that the word break carries several fascinating, possible meanings, and each one gently leads us toward a different, breathtaking edge of modern physics. One such meaning would be to stretch and bend spacetime so incredibly strongly that every possible path nearby is inexorably dragged inward. This is precisely what transpires around the dark majesty of a black hole. A black hole is not merely a physical hole punched through some passive background sheet. Instead, it is an extraordinary region where concentrated matter or immense energy has reshaped the surrounding geometry so severely that, beyond a certain invisible boundary, even the fleetest light can no longer escape to the outside universe. That mysterious, ultimate boundary is called the event horizon. Yet, nothing necessarily snaps or tears at that threshold. A solitary traveler falling through a very large event horizon might not notice any sudden surface or hostile barrier at the exact moment of crossing. The real, profound trouble lies much deeper within, where our mathematical theory points toward an infinitely dense singularity and abruptly stops describing physical events in a normal, complete way. Another meaning of a break would be to produce a delicate tear or a hidden tunnel connecting far-flung places that are normally separated by vast, unyielding distances. Science fiction often vividly presents this as a dramatic rip in the cosmic fabric of space. Physics itself possesses beautiful mathematical ideas that closely resemble these tunnels, including wormholes, but we must remember that a mere mathematical possibility is not at all the same as a stable, tangible object that can be easily built, safely visited, or casually used for a weekend trip. A wormhole would not necessarily represent broken spacetime. It could instead be a wonderfully unusual arrangement of spacetime, rather like a scenic road that takes a clever shortcut through a mountain, instead of damaging the tranquil countryside. The immense difficulty is that keeping such a fantastic shortcut open may require exotic forms of matter or negative energy that we do not yet know how to gather in any useful amounts, assuming that nature permits them to exist in the necessary form at all. A third meaning is far more serious. Spacetime might be considered truly broken when the very laws we use to describe it can no longer predict what happens next. Modern physics depends absolutely on being able to connect earlier conditions with later, inevitable outcomes. The mathematical prediction does not need to be effortless, and it does not always need to be perfectly certain, but the theory must at least tell us what specific kinds of outcomes are fundamentally allowed. If a troubled region appears where our equations completely lose that predictive ability, then something deeply fundamental has gone wrong. Perhaps spacetime itself has reached a genuine, ultimate limit. Perhaps our beloved theory is simply incomplete. Or perhaps the profound question has been framed in the wrong way. That subtle distinction will matter immensely throughout our long journey. When a hand-drawn map ends at the very edge of the known, familiar territory, it does not mean the actual land ends there. It may only mean that no brave cartographer has drawn the next section yet. General relativity, our leading and most elegant theory of gravity, has been remarkably, triumphantly successful. It beautifully explains the majestic motion of planets, the subtle bending of starlight, the slow behavior of clocks in intense gravitational fields, and the ripples of gravitational waves produced when massive cosmic objects violently accelerate. It has triumphantly passed many extraordinarily difficult tests. Even so, its own rigorous mathematics inevitably leads to certain places where the theory appears to fail. Those mysterious places are not definitive proof that spacetime literally breaks. They are merely clear signs that our current map may be missing a much deeper, more fundamental description. To understand why force is not quite the right word to use here, imagine gently pressing your hand into a soft, yielding cushion. The harder you push, the deeper the surface bends. It feels entirely natural to think of gravity in this same intuitive way. place more heavy mass in one region, and spacetime bends more dramatically. This familiar comparison is useful, but it has its clear limits. The cushion bends into the physical space around it. Spacetime, however, does not need some larger, empty room outside the universe in order to curve. Its intricate curvature is measured through internal relationships within spacetime itself. Clocks run at slightly different rates. Paths that would otherwise remain perfectly parallel can gradually move together. Light itself follows cosmic routes that appear bent. The underlying geometry changes, and objects naturally respond to that changed geometry. Force in our everyday tactile life is something that actively pushes or pulls. Gravity in the realm of general relativity is described quite differently. A freely falling object is not being aggressively dragged by some invisible, ghostly rope. It is simply following the straightest, most natural path available through curved spacetime. That path may look curved when we describe it through the rigid lens of ordinary coordinates, but from the object's own intimate, local point of view, it is simply gliding along its most natural path. This subtle truth means our central question requires a gentle adjustment. Instead of merely asking how much raw force would shatter the delicate fabric of spacetime, we ought to ask how much concentrated energy, mass, pressure, or sheer density would be required to strain its geometry to the absolute limit. Here, concentration becomes the truly crucial element. A vast, majestic amount of mass spread widely over a colossal region of space may produce only a soft, barely perceptible curvature. Yet, that very same mass, when compressed tightly into an unimaginably smaller region, can generate a gravitational distortion far more intense and dramatic. Our own Earth curves spacetime gently around us, yet its embrace is not nearly strong enough to hold back the fleeting beams of light. Eventually, the falling object simply fades away, dissolving slowly into the silent dark. Yet, from the intimate perspective of the falling traveler itself, the experience is profoundly different. It steadily reaches and crosses the threshold after only a finite, brief passage of its own personal time. Indeed, if the black hole is sufficiently immense, this historic crossing may not involve any sudden, violent physical sensation at all. There is no physical wall to strike, and no glowing line painted across the velvet dark of space. The intrepid traveler might only notice the distant, outside universe becoming increasingly warped and distorted, while the horizon itself passes by without any localized event to mark its crossing. These two vastly different descriptions are not competing, contradictory stories. Rather, they are the natural result of different, equally valid ways of measuring the flow of time and assigning coordinates within a deeply curved spacetime. And so, the distant observer continues to wait, endlessly receiving older, fainter, and increasingly delayed signals from a journey that, to them, never truly ends. Meanwhile, the falling traveler continues along their solitary path, drifting smoothly through the threshold of the horizon. The mighty sun bends spacetime far more powerfully, yet sunlight still escapes its warm grasp and streams outward into the cosmos without difficulty. This is precisely why these abyssal entities are so notoriously difficult to describe using the limits of our ordinary, everyday language. We naturally expect an event either to happen or not to happen at a single, universally shared moment. Yet, Einstein's relativity does not grant us a single universal clock that everyone can agree upon. Instead, each individual observer measures the passage of time along their own unique path, and the profound curving of spacetime dynamically alters how those disparate measurements compare with one another. Furthermore, the very existence of the horizon depends on what will unfold in the absolute future. To decide whether a specific event has occurred inside the black hole, physicists must ask whether any light originating from that event can ever escape to reach the safety of the distant universe. If the answer is a silent, definitive no, then the event is deemed to lie inside. This means that this invisible boundary is defined using the entire, overarching structure of spacetime, rather than merely the localized, fleeting conditions at a single instant. Such a definition sounds incredibly inconvenient, and indeed it is. Nature did not design these cosmic giants for the sake of easy bookkeeping, but compress enough mass within a sufficiently small and critical boundary, and a mysterious event horizon will inevitably form. In practical, real-world calculations, physicists often rely on related, alternative boundaries that are far easier to identify during a chaotic collapse or a violent merger. These pragmatic boundaries meticulously track the specific regions where outward-moving light is no longer expanding outward as normally expected. By doing so, they gracefully help researchers simulate dynamically changing black holes without the impossible requirement of knowing the complete future in advance. For a quiet, settled black hole, the event horizon gradually assumes a much simpler, more elegant form. Its physical size depends almost entirely on the mass and the spin of the black hole itself. Naturally, a more massive black hole possesses a correspondingly larger horizon. A rotating black hole, however, does something even more marvelous. It actively drags the surrounding fabric of spacetime along with it, adding a mesmerizing layer of complexity to the local geometry. This gravitational pulling is known as frame dragging. Any spinning mass produces it to some degree, including our own Earth, though the terrestrial effect is so extremely small as to be nearly imperceptible. Yet, near a rapidly spinning black hole, this dragging of frames becomes so violently powerful that no physical object can possibly remain stationary relative to the distant universe. It is not merely the sheer quantity of material that matters in this cosmic dance, but rather how tightly and densely that material is packed together. Spacetime itself is caught in the current, swept bodily around the black hole. Just outside the absolute horizon of such a spinning black hole lies a turbulent region known as the ergosphere. A traveler or object caught in this domain can still manage to escape, but they must actively run with this cosmic rotation to some degree. In principle, vast amounts of energy can actually be extracted from the black hole's immense spin by sending matter along carefully calculated, precise trajectories. Natural astrophysical processes involving intense magnetic fields and the swirling, hot plasma surrounding the abyss may also drain this rotational energy, helping to power truly colossal cosmic jets. These magnificent jets can extend incredibly far, stretching way beyond the borders of the very galaxy that houses the black hole. Importantly, these are not streams of material somehow escaping from inside the event horizon itself. Nothing ordinary, after all, can ever escape from that dark interior. Instead, these spectacular jets form entirely outside, where tangled magnetic fields, superheated plasma, and rapid rotation interact dynamically with the immense reservoir of energy available just around the black hole. A feeding, active black hole can therefore paradoxically become one of the most brilliant, luminous objects in the entire cosmos, even while the central engine itself remains completely and utterly dark. This is the profound reason why a dark, silent black hole can arise from the ashes of a collapsing star. Swirling gas spirals relentlessly inward through an accretion disk. Intense friction, chaotic turbulence, and magnetic forces heat this matter to unbelievably extreme temperatures. Long before crossing the final horizon, the glowing gas releases torrents of energetic radiation. The closer it draws to the abyss, the more gravity's immense pull converts raw orbital energy into brilliant heat and light. This conversion process is remarkably, astonishingly efficient. Indeed, matter falling toward a black hole can release a far larger fraction of its resting mass energy than the matter undergoing thermonuclear fusion deep inside the core of a star. The black hole itself does not burn this infalling material in any chemical or nuclear sense. Rather, this staggering energy is born purely from the frantic motion and extreme heating of matter as it rubs against itself within the highly curved spacetime outside. Conversely, a dormant black hole that is not actively feeding can be exceedingly difficult to detect in the dark void. Yet, clever astronomers can still find these silent giants by watching a visible companion star as it performs a ghostly orbit around an unseen, massive companion. A massive, luminous star spends the grand majority of its active life delicately balancing two opposing, titanic forces. They may also observe the light from a distant, background star being briefly and beautifully magnified as the black hole's gravity warps space while passing directly in front of it. Or, they might detect the faint ripples of gravitational waves singing through the cosmos when it finally merges with another compact stellar remnant. While the horizon forever hides the secrets of the interior, the external universe still carries vital, readable clues about the black hole's mass and rotation, and, if it happens to possess an electrical charge, that can also influence the intricate tapestry of its surrounding geometry. Yet, real astronomical black holes are widely expected to become almost completely neutral, as opposite charges in the chaotic surrounding matter are rapidly attracted and collected into their dark embrace. This elegant simplicity is sometimes famously described by physicists who say that black holes have very little hair. This playful phrase simply means that almost all the complex, messy details of the original material that once collapsed to form the black hole are forever hidden, completely invisible across its settled exterior. Thus, a black hole birthed from a gently collapsing cloud of gas, and one forged through the violent, cosmic merger of smaller black holes can eventually appear entirely identical, provided their final mass, spin rotation, and charge are exactly the same. Its own gravity pulls relentlessly inward, while the fierce, radiant pressure produced by central heat and intense nuclear processes pushes boldly outward. This uniformity immediately creates a profound and deeply unsettling puzzle. In our ordinary understanding of the physical world, fundamental processes must preserve information in some subtle form. If a highly detailed, complex object falls past the event horizon into a black hole, and the silent exterior remembers only a few sparse, general properties, what truly happens to all that lost, intricate information? The question becomes significantly sharper, almost agonizingly so, when the precise rules of quantum physics are introduced into the equation. Quantum theory strictly forbids information from simply dissolving into nothingness. Though a physical system can admittedly become incredibly complicated, deeply mixed, and practically impossible to ever reconstruct in reality, the underlying quantum evolution is always expected to preserve the precise memory of its earlier state. Black holes, however, appear to defiantly challenge this fundamental expectation. These cosmic abyssals can easily absorb vast amounts of matter carrying rich, detailed quantum information. Yet, according to subtle quantum effects, they must also slowly, almost imperceptibly, emit thermal radiation and consequently lose their mass over time. If a black hole eventually evaporates away entirely into the void, and this outgoing radiation contains absolutely no trace or record of what originally fell inside, then that fundamental information seems to have been permanently destroyed. When the aging star finally runs out of the nuclear fuel that supports its burning core, this beautiful balance can suddenly and catastrophically fail. This profound mystery is known as the famous black hole information problem. This is not merely some dry, academic disagreement about where a scientist might have misplaced a notebook. Rather, it exposes a deep, dramatic conflict at the very heart of physics, a clash between Einstein's general relativity, the microscopic laws of quantum mechanics, and the mysterious behavior of cosmic horizons. The quiet whisper of radiation involved is known as Hawking radiation. Near the threshold of a horizon, quantum fields never truly become completely inactive or silent. The black hole can slowly emit a faint, ghostly thermal glow, causing it to gradually lose its energy and shrink over unimaginably long periods of time. For the immense black holes formed from collapsing stars, this delicate radiation is far too weak and faint to be detected by our current primitive instruments. Currently, the surrounding universe is much warmer than these cold black holes. Such massive objects still absorb far more ambient energy from the cosmic microwave background than they ever lose. Only after the universe grows exceedingly older, darker, and colder will the slow process of evaporation finally begin to dominate for these isolated stellar black holes. A smaller black hole, conversely, would be significantly hotter, evaporating at a much faster rate. Its brilliant outer layers may explode violently away into the void, while the heavy central region collapses rapidly in upon itself. As it steadily loses mass, its temperature would rise higher and higher, rapidly accelerating the rate of its energy loss. The dramatic final stage of this process remains deeply uncertain, because the evaporating black hole would eventually shrink to a scale so unimaginably small that the unknown laws of quantum gravity must finally come into play. The simplest, most straightforward calculation of Hawking radiation suggests it is entirely thermal. This means that the outgoing particles only reveal the black hole's surface temperature, offering no clue about the detailed state of the diverse matter that once fell inside. If this evaporation concludes with absolutely nothing remaining, the original information appears lost forever. To resolve this crisis, several intriguing answers have been proposed by physicists. Information might gradually whisper its way out through incredibly subtle, highly correlated patterns embedded within the outgoing radiation. Alternatively, it might remain safely stored in a tiny, stable final remnant, or perhaps pass entirely into another newborn region of spacetime. Some suggest the basic evaporation calculation simply requires profound corrections from a future theory of quantum gravity, while others believe our standard, ordinary assumptions about the sharp division between the inside and outside of the event horizon are fundamentally incomplete. In certain extreme cases, no physical pressure known to science can halt this inexorable collapse. Today, many physicists strongly expect that this precious information is indeed preserved, though the exact elusive mechanism remains a major, captivating subject of modern research. Revolutionary ideas involving the mysteries of quantum entanglement, holographic descriptions, and the deep, hidden relationship between geometry and information have completely transformed how we approach this ancient problem. The elegant holographic principle suggests that the complex physics taking place within a certain region of space may be fully and beautifully described by the information encoded on its boundary. This does not mean the physical universe is merely a visual projection in the everyday sense of a hologram. Rather, it profoundly implies that a complex theory of gravity operating inside a given volume may be mathematically equivalent to another, simpler theory completely devoid of gravity, existing quietly on a lower dimensional boundary. Enigmatic black holes played a crucial role in inspiring this profound concept, primarily because their entropy, which carefully measures the vast number of possible hidden microscopic states, depends uniquely on the outer surface area of the event horizon rather than the physical volume contained deep within. This counterintuitive result is deeply surprising. For ordinary, familiar physical systems, one would naturally expect the overall storage capacity to scale proportionally with volume. As matter is squeezed to unimaginable extremes, the surrounding curvature grows ever steeper, and a black hole is born. Yet, black holes point directly toward a far deeper, more mysterious connection weaving together surface area, information, and the very fabric of spacetime. This elegant connection has led visionary researchers to suspect that the familiar tapestry of spacetime itself may actually emerge, like a phantom, from underlying quantum information. In certain delicate theoretical models, the intricate patterns of entanglement weaving through quantum systems help construct the basic geometric relationships that we perceive as physical distance and spatial connectivity. Alter the subtle entanglement, and the entire geometry shifts accordingly. If this sweeping, grand idea is indeed correct, the mysterious interior of a black hole may not exist as an independent realm to be described separately from its outer horizon. Rather, the information encoded on the boundary and the complex geometry within may simply be two complementary descriptions of the exact same underlying physical reality. Admittedly, this does not yet paint a complete or flawless picture of a real, turbulent black hole born from the collapse of a dying star. The most clearly understood examples typically involve highly idealized toy universes, possessing vastly different large-scale properties from our own sprawling cosmos. Still, they offer tantalizing and powerful evidence that gravity, cosmic geometry, and quantum information are intimately and inextricably linked. The daunting information paradox becomes especially difficult and poignant when we contemplate what a daring, free-falling observer actually experiences. But does this truly count as spacetime breaking? The elegant equations of general relativity softly suggest that crossing a vast, large horizon should feel locally quiet and entirely uneventful. Yet, stubborn quantum arguments regarding the escape of trapped information seem to demand that something violent must happen near that very horizon, fundamentally altering the physical state of the infalling matter. One striking proposal suggested that a fiercely energetic barrier, aptly named a firewall, might materialize directly at or near the horizon, instantly destroying any object that dares to cross. While this would desperately preserve certain core principles of quantum theory, it directly violates the cherished expectation from relativity that the horizon of a massive black hole remains locally smooth and unblemished. This radical proposal ignited an intense, passionate debate because it forced physicists to choose painfully among fundamental principles that had all seemed remarkably reliable. Perhaps the horizon is indeed smooth and welcoming. Perhaps information somehow escapes its clutches. Or perhaps quantum entanglement behaves in ways far stranger than we have ever dared to expect. To hold on to every comforting assumption simultaneously appeared painfully difficult, and today, there is still no universally accepted, final resolution. Yet, that very uncertainty remains incredibly useful for our exploration, precisely because it identifies a clear, defining edge. Not in the vast, ordinary region lying safely outside the event horizon, where the geometry remains beautifully smooth and understandable. Black holes do not merely warp space to generate immensely strong gravity. They boldly drag our finest, most cherished theories into direct, irreconcilable conflict over what spacetime, information, and the act of observation truly mean. And at the very center, there lies an even more glaring, unavoidable problem. Classical general relativity unflinchingly predicts a singularity. For a simple, non-rotating black hole, this singularity is commonly pictured as an infinitely dense, dimensionless point. For an idealized, rotating black hole, the elegant mathematics yields a bizarre ring-shaped structure, opening up far more complex and puzzling internal regions. In reality, actual black holes are formed through violent stellar collapse and continuously interact with their dynamic surroundings, meaning that even small external disturbances might render this pristine, idealized picture unstable. The exact physical geometry hidden inside a realistic spinning black hole is almost certainly far more convoluted and chaotic than the clean, elegant textbook solutions would ever suggest. Yet, what remains stubbornly difficult to avoid within classical relativity is the stark, haunting conclusion that gravitational collapse inevitably leads to incomplete cosmic paths. A brave observer can reach an absolute physical limit after a finite amount of personal, elapsed time with no ordinary, continuous future provided for them by the theory. There, we can easily calculate planetary orbits, predict with precision how passing light bends, and model how gas and matter heat to a glow as they fall inward. This is a far more precise and careful way to describe a singularity, rather than simply stating that physical density becomes mathematically infinite. Thus, the singularity is not treated as an ordinary, physical location resting quietly inside spacetime. Instead, it is far better understood as a sheer, absolute boundary where our physical descriptions utterly cease. To ask what happens after reaching this final precipice may be like asking what lies north of the North Pole, though admittedly even this poetic comparison remains imperfect. The very question may assume a continuation, that the underlying geometry simply does not provide. If a future theory of quantum gravity eventually replaces this unfathomable singularity, then the fabric of spacetime may well continue onward in an entirely new, unimagined form. The innermost central region might harbor an incredibly highly compressed quantum state. It might undergo a dramatic, fundamental transition, or perhaps it might connect seamlessly to another distant region. Ultimately, it might completely avoid the classical end without resembling any familiar place we have ever known. Even the mysterious boundary of the event horizon itself reveals itself as a regular, mathematically sound feature when described with sufficient care. One intriguing family of ideas treats the very fabric of spacetime as being built from tiny, discrete elements. In that fascinating case, there may exist a fundamental, smaller scale beyond which further compression simply has no ordinary physical meaning. The gravitational collapse could eventually reach a novel state where the inherent quantum properties of geometry actively resist the formation of the classical singularity. Another profound approach elegantly treats these basic ingredients as extended, vibrating objects rather than infinitesimally small points. Their natural behavior may gently smooth out the extreme interactions that would otherwise inevitably become mathematically unbounded. Within such theories, black holes can possess rich microscopic descriptions, intricately involving vast numbers of microquantum states. Some revolutionary proposals replace the traditional, empty interior with a highly complex structure that extends nearly all the way to the outer horizon. Instead of a vast empty space surrounding a dark central singularity, the black hole could instead be a deeply compact quantum object, whose myriad possible internal arrangements beautifully account for its massive thermodynamic entropy. Other thoughtful models choose to preserve a recognizable interior for a long, quiet time, but they drastically alter the dramatic final stage. There may occur a sudden, powerful bounce into a newly expanding region, though whether that newborn region remains dynamically connected to our own parent universe remains deeply uncertain. The true, likely breakdown of our understanding occurs only at the very center, or at least at that singular point which classical general relativity identifies as the heart of the darkness. Alternatively, there may be a slow transition into something closely resembling a white hole, occurring after an unimaginably long delay. A white hole is defined as the time-reversed mathematical partner of its dark counterpart. Matter and radiant light can freely leave its bounds, but absolutely nothing can ever enter it from the outside world. Yet, no confirmed white holes have ever been observed in our skies. Their inherent stability and complex formation present serious theoretical problems, so they remain highly speculative entities. Mysterious wormholes also frequently appear in modern discussions of black hole interiors. Certain highly idealized mathematical solutions can connect incredibly distant regions of spacetime through a hypothetical bridge. However, the fragile bridge in the simplest black hole solution collapses far too quickly to allow any real travel. It is by no means a practical tunnel and simply cannot be crossed from one distant exterior region to another. Rotating black hole solutions contain far more complicated, enticing routes on paper, but these turbulent internal regions may be fundamentally unstable. Stray radiation and tiny external disturbances can grow quite dramatically near the inner horizons, likely disrupting and changing the entire geometry long before any brave traveler can enjoy the advertised shortcut. There, both density and curvature are driven so far beyond the ordinary limits that the theory can no longer provide a physical or coherent answer. This is a recurring, humbling lesson in theoretical physics. A solution can be beautifully and mathematically allowed under perfect, sterile conditions, while becoming utterly impossible once the slightest realistic disturbance is included. A perfectly balanced pencil can stand effortlessly on its sharp point within the clean lines of an equation. The true difficulty begins when the physical universe remembers that tiny, chaotic vibrations exist. The profound edges of black holes therefore present themselves in several distinct forms. The silent event horizon remains an absolute edge of cosmic communication. The dreaded singularity stands as the definitive edge of our classical spacetime description. The persistent black hole information problem marks a turbulent edge between general relativity and quantum theory. And the mysterious final stage of Hawking evaporation represents the very edge of our current physical prediction. Yet, none of these fascinating boundaries proves that spacetime can be violently torn open by a sufficiently large force. Instead, they gently show us that extreme gravitational curvature exposes the deeply hidden assumptions buried within our current theories. In this context, the simple word beyond is incredibly useful. Smooth, continuous geometry may not always remain fundamental. Local information may be intrinsically related to distant holographic boundaries. Perhaps space and time themselves emerge from deeper quantum relationships that do not resemble either familiar concept. Tremendous black hole mergers now give us a precious way to study some of these grand ideas from safely outside the event horizon. When two massive black holes orbit one another in a cosmic dance, the complex geometry around them changes continuously and dynamically. They continuously emit powerful gravitational waves, gradually losing their orbital energy. Consequently, the orbit shrinks, the orbital speed increases, and the ripples in spacetime grow ever stronger. During the final, cataclysmic merger, the two horizons violently distort and combine. The final result is a single, newly born black hole that initially possesses a highly uneven, asymmetric shape. It acts as a humbling reminder, preventing us from pretending we know more than we truly do. Gradually settles itself by radiating away its excess energy through gravitational waves in a hauntingly beautiful pattern known as the ring down. The precise, fading frequencies and the rapid decay of that cosmic signal intimately reveal both the total mass and the swift rotation of the newly formed, final black hole. This monumental event stands as one of the most unimaginably violent and cataclysmic processes in the entire universe. Within a fleeting, brief interval, an amount of mass equivalent to several suns can be converted entirely into raw ripples of gravitational wave energy. Yet, despite this titanic release of power, the result is surprisingly not a shattered or torn fabric of spacetime. The local geometry of the cosmos gracefully absorbs the violent disturbance, fluidly reorganizes its structure, and peacefully settles back into a stable, quiet black hole. Sophisticated computer simulations are absolutely required to follow this intricate process, because the underlying gravitational fields are highly dynamic and profoundly curved. The complex and nonlinear equations of general relativity must be solved numerically with immense computational power. Indeed, decades of intense, painstaking work were needed before stable merger simulations finally became possible. These brilliant simulations successfully predicted the exact signals that our sensitive detectors on Earth would later observe. When a trusted theory suddenly produces an infinite result, nature is not necessarily announcing that an actual physical infinity exists. The remarkable agreement between theoretical predictions and actual physical measurements triumphantly showed that general relativity continues to function perfectly under conditions far more extreme and chaotic than any found within our calm, familiar solar system. Yet, that spectacular success makes the theory's remaining, stubborn failures even more deeply interesting. The classical theory can beautifully describe two immense horizons colliding and seamlessly joining. It can precisely describe the ripples of gravitational waves leaving the system. It can even describe the final black hole ringing down into silence. But it still inevitably predicts hidden, problematic singularities at its center and completely fails to explain the ultimate, complete quantum fate of trapped information. A cosmic merger also clearly demonstrates that event horizons are not rigid, fixed shells. They can grow, distort, and smoothly combine. The total area of the horizon always increases during this classical process. Sometimes, the mathematical theory is gently whispering to us that it has been stretched far past the specific conditions where its predictions can be trusted. This intriguing behavior closely resembles the inevitable increase of entropy in thermodynamics, which historically helped lead physicists to the radical idea that black holes themselves possess a physical temperature and immeasurable entropy. This profound comparison became far more than just a loose analogy once the existence of Hawking radiation was theoretically discovered. In truth, black holes obey physical laws that are intimately related to the fundamental laws of thermodynamics. Their silent horizons possess a definite temperature. Their outer area is deeply connected with entropy. They actively exchange energy with their cold surroundings. This realization means a black hole is not merely a massive gravitational object. It is also, fundamentally, a thermodynamic and quantum mechanical system. Consequently, any complete, satisfying description of these monsters must seamlessly combine all three of these vast areas of physics. Yet, that grand unification is exactly what our current theories struggle so desperately to provide. While general relativity beautifully describes the large-scale geometry of spacetime, quantum field theory governs the delicate behavior of particles and fields near the horizon. Just as an ancient navigation chart might mark a perilous, unexplored coast with vague, monstrous shapes simply because the survey was incomplete, we must not assume the ocean itself becomes mathematically infinite at that point. And thermodynamics describes the collective statistical behavior of the entire system. A complete theory of quantum gravity must eventually explain why these disparate descriptions fit together so harmoniously, and reveal what fundamental microscopic structures produce them. The evocative phrase edge of breaking is therefore highly appropriate, provided we are careful about exactly what is breaking. The physical horizon itself does not appear to break or tear. The surrounding spacetime outside remains remarkably smooth and continuous, and the majestic mergers proceed exactly as predicted. Instead, the severe strain falls squarely upon our mathematical theories when they are asked to describe the mysterious center, the preservation of information, and the incomprehensibly small scales of existence. Perhaps physical spacetime continues smoothly all the way inward, only to undergo a subtle quantum correction near the very center. Perhaps the entire interior of the black hole is holographically encoded upon the boundary of the horizon itself. Perhaps the familiar interior is merely an approximate, emergent description that manifests only for certain fortunate observers. Or perhaps space and time themselves entirely stop being meaningful concepts long before the classical singularity is ever reached. Rather, it simply means that more precise measurements and a more complete map are desperately needed. Each of these fascinating possibilities radically changes the answer to our original, profound question. If spacetime is indeed a fundamental and continuous fabric, breaking it might require creating a true, physical boundary or a raw singularity. If it is discrete, then extreme, concentrated energy may violently disrupt its smallest, indivisible units. And if it is merely emergent, it may simply dissolve away when the underlying quantum relationships begin to change and unravel. Black holes miraculously bring all of these diverse options incredibly close together. They are tangible, observable cosmic objects with measurable masses, spins, glowing accretion disks, powerful relativistic jets, and detectable gravitational waves. They are also supreme laboratories of the cosmos, containing inaccessible, cloaked regions where our most cherished theories completely lose agreement and break down. Ultimately, the next illuminating clue does not come from staring only into the silent darkness. Instead, it comes from the profound disturbances that black holes whisper and send cascading outward into the cosmic void. These celestial ripples, known as gravitational waves, allow the universe to faithfully report how the very fabric of spacetime behaves during violent collisions, catastrophic collapses, and furiously rapid motions. Yet, at the dark center of a black hole, such better measurements are exceedingly difficult to arrange. They elegantly reveal precisely how much immense distortion the cosmic geometry can endure without failing entirely, and how the echoes of such primal cosmic violence can travel across unimaginably vast distances before producing a minute tremor, one far smaller than a single atomic nucleus, inside a sensitive detector here on Earth. That incredibly tiny, almost imperceptible movement serves as the vital key to one of the most direct and profound ways we can study the nature of spacetime under such extreme, unforgiving conditions. Gravitational waves do not paint spacetime for us as a brightly visible surface, nor do they graciously allow us to watch the dark heart of a black hole from the safety of its interior. What they truly provide is an exquisite record of how the geometric fabric responds when massive celestial objects move violently through space. A majestic pair of black holes can collide far beyond the limited reach of any optical telescope, and the resulting titanic disturbance can travel tirelessly across the silent universe until it finally reaches Earth, subtly altering the distance between two hanging mirrors by an almost impossibly, miraculously small amount. The ancient, faraway event that produced this faint signal may have originally involved massive bodies far greater than our own sun, hurtling wildly at a significant fraction of the ultimate speed of light. Yet, the physical effect measured on Earth can be far smaller than the mere width of a single proton. This astonishing contrast is precisely one of the reasons why gravitational wave astronomy is so profoundly remarkable. Any precious information born deep inside the event horizon cannot travel outward in the usual, familiar way. The distant cosmic source can be counted among the most violently powerful events in all of existence, while the arriving signal is so exquisitely weak that a passing truck on a nearby road, a gentle gust of wind, or even a solitary person walking through the wrong part of a laboratory building can create a much larger, disruptive disturbance. To deeply understand where these elusive waves truly come from, let us begin with the elegant simplicity of a basic orbit. Our Earth moves in a steady path around the Sun, and the Sun, in its turn, moves ever so slightly in gravitational response to the Earth. Both of these celestial objects travel continuously through the continuum of spacetime, and their mutual motion gently alters the gravitational field immediately surrounding them. In absolute physical principle, this dancing system produces gravitational waves. However, the resulting effect is far too incredibly weak to matter for the stability of the orbit over ordinary human timescales, and far too vanishingly small for our current, delicate detectors to measure directly. This profound weakness stems partly from the fundamental fact that gravity itself is exceptionally weak when compared directly with the other primal interactions of nature, and partly from the graceful, whispering smoothness of their orbital motion. Earth and the Sun are undeniably massive by our humble human standards, but they are simply not compact enough, close enough, or moving fast enough to generate a strong, detectable signal. Replace them, however, with two dense neutron stars or two ravenous black holes, and the cosmic situation changes dramatically. No intrepid probe can descend into that abyss, gather its readings, and beam a cheerful, triumphant report back to the eager scientists in the laboratory. These extreme, compact objects can contain an absolutely enormous amount of mass packed within incredibly small, compressed regions of space. They can orbit frantically close together without ever touching in the ordinary physical sense. As they slowly lose their orbital energy through the emission of gravitational waves, they inevitably spiral inward and accelerate to terrifying speeds. The warping of the local geometry becomes increasingly rapid, and the outgoing waves become significantly stronger and more pronounced. Yet, these waves do not arise from a mass simply existing in silent stasis. A perfectly still, solitary object creates a static gravitational field around itself, but it does not send out a continuous, traveling gravitational wave. Even a steady, unyielding motion along a perfectly straight line is not enough to stir the deep waters of spacetime. The vital, indispensable requirement is a dynamically changing motion arranged in an uneven, asymmetrical way. A perfectly spherical star that rhythmically expands and contracts equally in every direction would not produce this same kind of outgoing, propagating gravitational wave. Its immediate gravitational influence certainly changes, but the flawless symmetry of the motion completely prevents the required disturbance pattern from escaping into the void as radiation. Instead, we must rely upon elegant theory, subtle indirect evidence, and strict consistency with everything we can still observe in the luminous world outside. Something dynamic must step in to create an essential imbalance. Two heavy objects orbiting closely around one another do this entirely naturally. A violently lopsided stellar explosion can also easily accomplish this. A rapidly spinning neutron star possessing even a tiny, imperfect deformation on its crust can do it as well. Ultimately, a rapidly changing, dynamic distribution of mass creates the shifting pattern that travels outward across the cosmos. As it propagates, the wave gently stretches the fabric of spacetime in one direction while simultaneously squeezing it in another. A brief moment later, these rhythmic effects gracefully reverse. Imagine, if you will, a perfect circle of freely floating dust particles suspended in the silence of deep space. As a gravitational wave gently passes through them, the pristine circle becomes slightly stretched into an elongated oval. Then it returns smoothly toward a circle and stretches in the. This inevitable limitation leaves ample room for several fascinating possibilities. Other direction. These free-floating particles are not being physically pushed through some static, ordinary background in the everyday sense. Instead, the measured separations between them are constantly changing because the underlying geometry of spacetime itself is shifting. This is precisely why the familiar word ripple is highly useful, yet ultimately incomplete. A gentle ripple on a quiet water surface changes only the physical height of the water itself. In profound contrast, a passing gravitational wave fundamentally alters the very relationships of distance and time. It does not require any material medium to travel. It glides effortlessly through the absolute emptiness of space because it is, in its purest essence, a direct disturbance of spacetime itself. These invisible waves travel through the cosmos at the ultimate speed of light. This breathtaking speed was predicted by the elegant equations of general relativity and was later brilliantly confirmed through direct observations. A deeper, more fundamental theory might eventually replace the troublesome singularity with an extremely dense but entirely finite physical state. When two incredibly dense neutron stars merged in a violent cosmic embrace, vigilant astronomers on Earth successfully detected both the faint gravitational waves and the brilliant flash of light emitted from the singular event. The dual signals reached our distant planet after traveling for an immense, almost unimaginable span of time, with their nearly simultaneous arrival beautifully demonstrating that the two distinct forms of radiation moved at essentially the same speed, within incredibly strict, narrow limits. That historic observation did far more than merely confirm a basic theoretical prediction. It decisively ruled out many alternative, competing theories of gravity that allowed gravitational disturbances to travel through the cosmos at a noticeably different, mismatched rate. From that one distant, cataclysmic collision, researchers harvested a wealth of profound information about the mysterious nature of gravity, the dense interior of neutron stars, the cosmic origin of heavy elements, and the accelerating expansion of our universe. Long before direct detection became technically possible, the most compelling evidence for the existence of gravitational waves came from a dancing pair of neutron stars. One of these dense partners was a pulsar, rapidly spinning and sending out highly regular radio pulses like a precise, eternal cosmic beacon. Patiently, astronomers tracked their orbital dance over the years and found that the two stars were gradually, inevitably drawing closer together. The smooth fabric of spacetime itself might reveal a granular, pixelated texture when viewed at unimaginably microscopic scales. The precise amount of orbital energy being lost over time matched almost perfectly with the exact amount that general relativity predicted should be silently carried away by outgoing gravitational waves. The elusive waves themselves were not yet detected directly at Earth, but their unmistakable effect on the stellar orbit was beautifully clear. It was remarkably similar to noticing that a battery is slowly losing its vital charge and correctly identifying the distant device that is consuming that energy, even though you cannot yet see the invisible electric current flowing directly. To achieve direct detection, scientists required a radically different, far more sensitive approach. The primary instruments designed for this monumental task utilized long, pristine vacuum arms arranged precisely at right angles to one another. A brilliant laser beam is carefully split and sent traveling along both of these perpendicular arms. Highly polished mirrors at the far ends reflect the pure light back, and the returning beams are then intricately compared. Under ordinary, undisturbed conditions, the optical paths are so perfectly balanced that the recombined light produces a completely stable, unchanging pattern. Yet, when a passing gravitational wave washes through, one arm becomes slightly longer while the other arm becomes slightly shorter. This subtle difference in length momentarily changes the delicate way the light waves combine, creating a highly precise, measurable signal for scientists to record. At that level, our most familiar, intuitive concepts of precise location and quiet duration might entirely cease to apply. Saying that a massive arm becomes longer can be somewhat confusing, because the mirrors are not simply being dragged apart through a rigid, unyielding space. Rather, the very geometry of the space between them is changing. The light itself, traveling along the length of the arm, also experiences and adapts to that changing geometry. The entire detector is meticulously designed so that this combined, subtle effect leaves a distinct pattern that watchful researchers can clearly measure. And yet, this physical change is extraordinarily, almost unimaginably small. The vacuum arms themselves are several kilometers long, but the actual shift in length can be far smaller than the tiny width of an atomic nucleus. Successfully detecting such a minuscule whisper requires the heavy mirrors to be completely isolated from the constant rumble of ground vibrations, subtle temperature changes, faint sounds, electrical noise, and countless other terrestrial disturbances. To achieve this, the mirrors are suspended from complex, multi-stage systems of delicate pendulums. The laser must remain incredibly stable. Or perhaps, the mysterious interior contains rich, exotic structures that are simply not captured by our current, limited conceptual vocabulary at all. The massive tubes carrying the light are kept under an extreme, ultra-high vacuum so that even a stray air molecule cannot interfere with the light's journey. Even with these precautions, the detector continuously records a chaotic mixture of useful cosmic data and unwanted local noise. A single instrument operating alone would struggle mightily to prove that a brief, fleeting signal actually came from the depths of space. A local, earthly disturbance could easily imitate some small part of the expected pattern. This is why several independent detectors are strategically operated in different, distant locations around the globe. A true gravitational wave, sweeping across the planet, reaches them at slightly different times, leaving a matching, related signal shape in each device. Carefully comparing these precise arrival times also helps astronomers estimate, with remarkable accuracy, the cosmic direction of the mysterious source. The very first direct, historic detection of these waves came from the violent merger of two colossal black holes. The recorded signal lasted only a fraction of a second within the detector's most exquisitely sensitive range, yet it contained an undeniably clear and beautiful progression. Interestingly, there exists another fascinating route toward extreme spacetime that does not begin with the lonely death of a single collapsing star. The frequency rose steadily as the two black holes spiraled ever closer in their cosmic dance, and the signal grew noticeably stronger. Then, in a final grand collision, the objects merged, leaving behind only the slowly fading vibration of the newly formed black hole settling into its quiet existence. This rising pattern is often poetically called a chirp, because when converted into audible sound, it closely resembles a short, sharp increase in pitch. Of course, the actual gravitational wave is not a sound. The vastness of space is far too empty for any ordinary sound wave to travel across the silent gulfs between galaxies. Instead, researchers thoughtfully turn the data into audio because these frequencies happen to fall within the delicate range of human hearing, and because our ears are remarkably adept at noticing subtle patterns. This brief signal carried a wealth of information, enough to estimate the immense masses of the original black holes, the final mass of the newly merged black hole, its rapid rotation, and the unimaginable distance to the event itself. It also revealed that a significant portion of the system's mass had been violently converted into pure gravitational wave energy. For one fleeting moment, the power carried by these ripples was greater than the combined light output of all the shining stars in the observable universe. Such an extraordinary statement makes it sound as though the wave should have arrived with enough destructive force to knock planets easily out of their orbits. Two majestic black holes can orbit one another in a silent, cosmic waltz, slowly losing their orbital energy through the rippling of gravitational waves, and eventually merge into one. Yet it did not. The energy spread outward in all directions, dispersing across an ever-growing region of space. By the time it finally reached Earth, the effect was incredibly weak. Energy can be utterly enormous at its source and yet completely negligible at a distant location. Just as a bright lamp is easy to see nearby but becomes difficult to notice from many kilometers away, a gravitational wave spreads through three-dimensional space, naturally weakening with distance as it covers a larger and larger area. These first detections also revealed something entirely unexpected about black holes. Before the dawn of gravitational wave astronomy, stellar black holes were often detected only by watching them interact with their nearby companion stars. Those indirect observations suggested a certain modest range of masses. However, the first merging black holes discovered were far heavier than many astronomers had ever expected. This proved that the universe could indeed produce pairs of heavy black holes and bring them close enough to merge. During their final, breathless moments, the local geometry of spacetime changes with violent rapidity. Researchers were then forced to consider how such mysterious systems formed. They may begin their lives as pairs of massive stars that evolve together, or they may form separately in dense, crowded star clusters and later become partners through chance gravitational encounters. Different detected systems may well come from these different routes. Each observed merger adds a new piece of information about the greater population. The masses, spins, distances, and orientations of these celestial bodies help researchers test and refine their models of stellar evolution. Thus, the signal is not only a test of the nature of spacetime, it is also a profound record of how stars once lived and died. Neutron-star mergers produce an even richer and more colorful collection of signals, because neutron stars contain physical matter and can emit bright light. When two such stars approach each other, they create gravitational waves in much the same broad way as black holes do. Yet during their final moments, the stars can distort and deform under each other's intense gravity. Their complex internal structure directly affects how easily they deform. As the black holes combine, the surrounding spacetime rings profoundly like a heavily struck bell, sending ripples of gravitational waves traveling outward into the cosmic dark at the absolute speed of light. A more compact neutron star responds quite differently from one with a slightly larger radius, and those subtle differences leave delicate, distinct marks in the gravitational wave signal. By studying these tiny variations, physicists can learn about matter at extreme densities far beyond those of ordinary atomic nuclei. The violent collision can produce a temporary, highly massive neutron star, or cause it to collapse quickly into a black hole, throwing hot, neutron-rich material far out into space. Nuclear reactions occurring within that rapidly expanding debris create heavy elements, including some of the precious gold and platinum found on Earth and across the universe. The glowing light from this heated material can be observed across several different wavelengths of the electromagnetic spectrum. As telescopes carefully follow the changing brightness and shifting colors, gravitational waves simultaneously reveal the silent, powerful motion of the compact objects both before and during the collision. This harmonious combination of observation is called multi-messenger astronomy. Through this harmonious approach, different signals gracefully describe different aspects of the very same celestial event. While brilliant light vividly reveals the scorching matter and intense nuclear processes, elusive gravitational waves trace the ever-changing motion and fundamental geometry of spacetime. In certain violent explosions, ghostly neutrinos may offer yet another unique perspective. This cataclysmic event is violent enough to release an absolutely colossal amount of energy in a fleetingly short fraction of time, yet spacetime does not shatter like brittle glass. Utilizing these diverse messengers together produces a far more complete and breathtaking account than any single signal could ever hope to provide alone. Should a spectacular supernova occur within our own home galaxy, it too could generate subtle gravitational waves, provided the stellar collapse is sufficiently uneven. Such a pristine signal would intimately reveal the violent motions churning deep inside the dying star, reaching our detectors from mysterious core regions forever hidden from ordinary light. Ghostly neutrinos would also escape almost instantly from the collapsing core, whereas visible light might only arrive much later, after the powerful shock wave finally breaches the stellar surface. Such a rare, monumental event would allow patient astronomers to meticulously compare the mechanics of stellar collapse through several complementary channels. The profound difficulty, however, is that supernovae occurring close enough for detailed gravitational wave detection are searchingly rare. Consequently, modern astronomy sometimes demands that sophisticated instruments remain tirelessly prepared for a singular cosmic event that might not even occur during the entire working lifetime of the dedicated scientists who built them. Conversely, rapidly rotating neutron stars may create much longer-lasting, enduring signals. If such a dense star possesses even a microscopic mountain, or any other infinitesimally slight departure from perfect symmetry, its frantic rotation can produce continuous, whispering gravitational waves. This celestial mountain need not resemble any rugged peak on Earth. Indeed, a deformation far smaller than the mere thickness of a sheet of paper could matter immensely because the dead star is so unimaginably dense and rotates so incredibly quickly. Instead, it fluidly carries the immense disturbance away into the distance. Successfully detecting such a faint signal requires patiently combining massive amounts of data over exceptionally long periods. Though the signal may remain desperately weak, it is remarkably regular. To isolate it, dedicated researchers must meticulously account for subtle changes in the star's own rotation, the continuous orbital movement of Earth, and the shifting orientation of our terrestrial detectors. Beyond these individual sources, there may also exist a vast cosmic background woven from countless unresolved gravitational wave sources. Instead of identifying each unique contributor, sensitive detectors would measure a soft, general hum echoing through the cosmos. Some of this ambient background is believed to originate from ancient pairs of supermassive black holes slowly and majestically orbiting one another in incredibly distant galaxies. These gentle waves possess far lower frequencies than the rapid chirps detected by our ground-based instruments. Accurately measuring them requires an entirely different, highly imaginative method. To do this, astronomers cleverly use highly stable pulsars spread across the galaxy, treating them as a vast natural network of cosmic clocks. As a passing gravitational wave gently warps space, it slightly alters the arrival times of their precise radio pulses. That remarkable resilience alone tells us something deeply important about the universe. By watching many of these celestial beacons for years, researchers can seek out a subtle, shared pattern hidden within the timing deviations. Compelling evidence for such a cosmic background has already begun to emerge, strongly suggesting that countless supermassive black hole pairs are actively contributing to a low-frequency gravitational murmur echoing softly across the entire universe. Looking ahead, ambitious future space-based detectors will target the intermediate frequencies existing between the ranges studied by ground-based instruments and pulsar timing arrays. Instead of relying on mirrors suspended within steel tubes on Earth, fleet spacecraft will exchange precise laser signals across millions of kilometers of empty space. By operating in the quiet void, a space-based detector will completely avoid the disruptive seismic vibrations of Earth and will utilize vastly longer arms. Consequently, it should easily detect epic mergers involving massive black holes, dense compact stars slowly spiraling into much larger black holes, and many tight binary stars orbiting within our own galaxy. A relatively small, compact object orbiting a supermassive black hole can beautifully trace the local geometry with breathtaking precision. Each orbital loop intimately samples the warped curvature of spacetime. The resulting gravitational waves thus contain a rich, incredibly detailed record of the black hole's complex spacetime environment. Spacetime is not fragile in any ordinary, brittle sense of the word. Should the measured signal differ even slightly from the elegant predictions of Einstein's general relativity, it could suddenly reveal entirely new physics. Yet, so far, our observations have remained wonderfully consistent with relativity. The cosmic waves travel at precisely the expected speed of light, and their intricate shapes match computational simulations with remarkable fidelity. Furthermore, the final ring-down signals perfectly agree with black holes possessing the exact physical properties predicted by the theory. Despite these triumphs, relentless scientists continue searching for the slightest, most subtle disagreements. They carefully analyze whether different segments of a signal consistently yield the same final mass and spin. They tirelessly look for unexpected, additional wave patterns hidden in the noise. Lastly, they rigorously test whether the signal loses strength or mysteriously shifts its frequency in an unusual manner during its long journey across the vast cosmos. Even the most minuscule, almost imperceptible deviation could hold profound significance. It might whisper of an undiscovered, additional field, point toward a subtly altered theory of gravity, unveil an unexpected property of black holes, or simply expose a critical flaw in the very assumptions we use to painstakingly model the source. Indeed, it can effortlessly withstand cataclysmic events that make even the grandest of human explosions appear entirely insignificant. Far more often, however, such an apparent deviation ultimately reveals itself to be nothing more than mundane background noise, incomplete mathematical modeling, or a transient instrumental artifact. The history of physics is beautifully rich with thrilling, exotic possibilities that, upon closer inspection, disappointingly turn out to be nothing more than an errant cable behaving badly. Yet, these celestial gravitational waves also offer us a remarkably direct answer to a crucial part of our central, enduring question. We find that the delicate fabric of spacetime can be profoundly disturbed by unimaginably cataclysmic events without ever truly tearing apart. Giant black holes can violently merge, dense neutron stars can catastrophically collide, and massive stellar cores can suddenly collapse inward. Through it all, the underlying geometry of the cosmos carries this intense disturbance away, safely dispersed in a highly controlled, elegant form. The passing wave may dynamically stretch and squeeze physical distances, yet it never leaves a jagged, permanent rupture in its wake. Once the ripples subside, physical objects return almost exactly to their previous arrangements, although certain powerful waves can induce a subtle, enduring alteration known to physicists as gravitational memory. This exquisite effect gently shifts the relative positions or residual motions of objects, leaving a quiet imprint long after the wave itself has vanished into the void. This lingering memory does not imply that spacetime has been physically damaged. Rather, it signifies that the cosmic event has inscribed a permanent, elegant geometric record upon the universe. This cosmic fabric can be gently curved by the silent mass of stars, violently shaken by cosmic collisions, and gradually stretched by the eternal expansion of the universe itself. Thus, the universe does not always return perfectly to its precise initial configuration after enduring such a powerful burst of cosmic radiation. This ghostly effect is predicted to be exceedingly small and incredibly difficult for us to detect with our current technology. Perhaps highly advanced future instruments will finally possess the sensitivity to measure it. Achieving this would offer yet another crucial, rigorous test of how gravity behaves during these extraordinarily energetic, violent events. Could a passing gravitational wave ever be powerful enough to physically destroy an object? Unquestionably, very close to a violent cosmic source, the rapidly shifting tidal forces could become intensely severe, where a monstrously powerful wave would violently stretch and compress physical matter. Ultimately, the object would fracture and break because its intrinsic, binding forces could simply no longer maintain its original structure. Yet, even in this chaos, spacetime itself would still be behaving perfectly according to the laws of general relativity. The wave would never represent a physical crack in existence, but rather an extreme, yet entirely permitted, shift in cosmic curvature. Could two colliding gravitational waves somehow interact and dynamically construct a new black hole? Faint gravitational waves traverse unimaginably vast distances, slowly weakening along their journey, until sensitive detectors on Earth can subtly record the minuscule, fleeting changes they produce in their wake. In fundamental principle, all energy gravitates, most certainly including the vast energy carried by traveling gravitational waves. If an immense amount of this energy were concentrated within a sufficiently microscopic region, it could indeed contribute directly to the formation of an event horizon. Deliberately engineering such an extreme condition remains, of course, far beyond the reach of any realistic, foreseeable human technology. The profound, essential point here is that gravity can actively act upon gravity itself. Because gravitational waves carry real energy, that moving energy directly influences the structure of spacetime. The underlying mathematical theory is beautifully nonlinear, meaning that these waves do not always passively glide through one another as if they were completely independent entities. Under ordinary, currently detectable conditions, these subtle interactions remain extremely, almost imperceptibly weak. Yet, under truly extreme cosmic conditions, they can matter immensely. This intricate, nonlinear behavior is precisely why simulating black hole mergers demands the raw power of our most sophisticated supercomputers. The surrounding geometry dynamically dictates the frantic motion of the black holes, while their violent motion, in turn, continuously alters that very geometry. Our physical reality seems wonderfully capable of transmitting a truly remarkable amount of disturbance without ever developing a frayed, loose edge or dropping fragmented pieces behind some cosmic sofa. This constantly changing geometry carries precious energy away into the cosmos, relentlessly altering the orbital dance once again. Every singular part of this cosmic process intimately responds to all the others in a grand, interconnected feedback loop. During those breathless final moments, spacetime is no longer a calm, static stage across which celestial objects merely drift. Instead, the stage and the actors fuse into one dynamic, rapidly evolving system where event horizons violently bend, coalesce, and gradually settle. Tremendous waves cascade outward, leaving the turbulent region behind. The resulting final geometry contains tangibly less mass than the original combined total, simply because so much raw energy has escaped into the void. Remarkably, even this incredibly violent, chaotic process remains beautifully predictable. Einstein's theory does not result in a random cosmic tear, nor does it spawn a chaotic region where physical distances lose all coherent meaning outside of the event horizons. The delicate signal observed from our distant vantage point follows a highly structured, remarkably harmonious pattern. This serves as profound, compelling evidence that the fabric of spacetime can elegantly tolerate the most severe motion and extreme curvature. And yet, even for this resilient fabric, there may exist ultimate limits. Yet, there remains a fundamental limit to what these gravitational wave observations can ultimately tell us. They primarily reveal only the exterior, outward dynamics of these cosmic titans. The waves produced during a cataclysmic merger emanate from the rapidly shifting geometry surrounding the event horizons, meaning they do not carry direct, unshielded reports from the mysterious singularities hidden deep within. The final, resonant ring-down tests the outer structure of the resulting black hole. If the celestial object indeed possesses a defining event horizon and an outer environment that perfectly matches the predictions of general relativity, the resulting signal behaves in a highly specific, predictable way. Conversely, a different class of exotic, highly compact object, One with a physical surface resting just outside where the horizon would normally form, might produce faint, additional signals or ghostly echoes. Diligent researchers have actively searched for these elusive echoes. Yet, no conclusive evidence has ever shown that ordinary black holes possess such reflective, solid surfaces outside their expected, mathematical horizons. As our observational data continues to grow steadily richer, future, highly sensitive detectors will make even more precise tests possible. At sufficiently microscopic scales and unimaginably high energies, the grand architecture of general relativity must somehow find a way to meet the elusive realm of quantum physics. Indeed, this profound lack of any visible failure in relativity is itself immensely informative. Nature, in all its violent grandeur, can easily orchestrate cosmic collisions involving incredibly compact masses, near-luminal speeds, and breathtakingly rapid changes in curvature, all while elegantly preserving the smooth, continuous description of exterior spacetime. Whatever fundamental truth eventually breaks our cherished theories must lie at far more extreme scales, or perhaps in mysterious regions forever hidden from our direct observation. Gravitational waves bring us tantalizingly close to that ultimate boundary without ever fully crossing it. They beautifully confirm that dynamic spacetime is indeed real, can gracefully carry immense energy, can dynamically react to motion. It can melodiously ring like a giant bell after a cataclysmic collision. It can faithfully preserve a detailed, pristine record of dramatic events that transpired billions of years ago. While general relativity beautifully treats spacetime as a continuously smooth and elegant geometry, quantum physics instead describes nature through the chaotic language of fields, shifting probabilities, and discrete, sudden interactions. These cosmic ripples also elegantly demonstrate why the very phrase, the force needed to break spacetime, may be seeking the wrong physical measurement. Even the most violent, strongest detected events do not rupture this cosmic fabric. Instead, they merely generate larger, deeper curvatures and produce stronger, more resonant waves. The mathematical framework continues to hold, responding resiliently as we search for a possible threshold where smooth geometry truly stops functioning. Simply increasing the raw violence of an ordinary cosmic event may not be enough to tear this fabric. The truly important transition may instead occur only when physical distances become so unimaginably small, and energy becomes so intensely concentrated, that subtle quantum effects can no longer be ignored. At that microscopic scale, the fundamental question is no longer how violently spacetime can be shaken. Rather, it becomes a deeper mystery. Whether spacetime still exists at all as a smooth, continuous canvas that can shake in the first place. This realization gently takes us away from grand waves crossing vast galaxies, drawing us toward the smallest conceivable length and the shortest imaginable duration that current physics can meaningfully discuss, a realm where our familiar, continuous geometry may begin to lose its cohesive, unbroken form. Each of these masterfully crafted theories works exceptionally well within the comforting borders of its own distinct domain. That ultimate, smallest scale is formally known as the Planck scale, and it marks the precise point where our traditional descriptions of space, time, matter, and gravity can no longer be trusted to operate separately. It is not a tangible physical border floating visibly somewhere in the deep universe. There is no warning sign erected beside a black hole declaring that ordinary physics ends at this point. Rather, the Planck scale represents an extreme regime of vanishingly small distances, incredibly brief durations, and intensely concentrated energies where quantum mechanics and gravity are expected to become equally, inextricably important. In ordinary, everyday situations, physicists can easily and conveniently choose which of these two great theories matters most. Albert Einstein's general relativity beautifully describes the majestic dance of planets, stars, black holes, and the grand, large-scale structure of the cosmos. Meanwhile, quantum physics exquisitely describes the silent domain of atoms, subatomic particles, light, and the subtle interactions taking place at infinitesimally small scales. Each theory has been tested with breathtaking, extraordinary precision under the specific conditions where it is normally applied. The conceptual trouble begins only when a physical situation becomes both extremely small and simultaneously, strongly affected by the pull of gravity. A tiny particle isolated in a laboratory strictly requires the rules of quantum physics, but its gravitational influence is usually far too weak to ever matter. The true intellectual crisis appears when both perspectives are desperately needed at once, such as near the infinitely dense classical center of a black hole, or during the blindingly hot, earliest known stages of our infant universe. Conversely, a massive planet absolutely requires the language of gravity, but its large-scale orbital motion does not require a detailed quantum mechanical description. Yet, near the classical, infinite center of a black hole, both theories are desperately needed at the very same time. The exact same profound limitation is true when we attempt to describe the chaotic, early stages of our universe. General relativity elegantly treats spacetime as a perfectly smooth, continuous geometry. Any given location can always be divided into smaller locations, and those smaller regions can endlessly be divided again. Within this classical theory, there is no required, fundamental smallest piece of space. Curvature can vary smoothly and continuously from one point to the next. Yet, quantum physics paints a radically different kind of picture. It does not always assign physical objects one exact, localized position or one single, definite state before a measurement is actually made. In this strange, microscopic realm, physical quantities constantly fluctuate in a restless, chaotic dance. Modern physicists naturally expect a unified theory of quantum gravity to eventually provide a much more complete, satisfying account, but as of yet, there remains no single, experimentally confirmed theory to definitively settle the matter. Particles, once envisioned as solid points, can behave like undulating waves. Empty space itself is never truly, completely empty. Even in the deepest void, quantum fields remain subtly active and vibrant, whispering with energy even when no ordinary particles are present. If the very fabric of spacetime must obey these elusive quantum rules, then its fundamental geometry may also tremble and fluctuate. Distances, once thought immutable, may no longer remain perfectly defined. Precious time intervals may dissolve into uncertainty. Under these extreme conditions, the minute difference between one possible shape of spacetime and another may become utterly impossible to ignore. At the large, comforting scales of our daily lives, these ghostly fluctuations remain extremely, almost imperceptibly small. A quiet room does not visibly warp or change its shape simply because its underlying geometry is exploring several quantum possibilities at once. A steady clock ticking on the wall does not lose track of the orderly flow of events. For now, several theoretical approaches offer wildly different, competing pictures of this hidden reality. Instead, their vast collective effect gently settles into the smooth, predictable spacetime so beautifully described by Einstein's relativity. Yet, at the unfathomably tiny Planck scale, these chaotic fluctuations may become just as important as the very geometry being measured. Any attempt to define a precise, localized distance could disturb the delicate region so violently that our original, familiar concept of distance simply stops working altogether. The serene, smooth background so confidently assumed by ordinary physics may no longer exist in this turbulent, microscopic realm. The mysterious Planck length is far, far smaller than the compact nucleus of an atom. Indeed, it is smaller than the minuscule distances explored by our most powerful, towering particle accelerators by a truly enormous margin. Even a tiny proton is an impossibly vast, sprawling cosmos compared with it. If a single proton were somehow expanded until it was comparable in size to the entire observable universe, the Planck length, by contrast, would still correspond to something astonishingly small by our everyday human standards. While this sweeping comparison is not mathematically exact, it serves to give us a profound sense of the unfathomable gap between these worlds. The elusive Planck scale is not merely a little beyond the reach of our current microscopes. Some enticingly suggest that spacetime itself is woven from incredibly tiny, fundamental units or intricate networks. It is separated from our present-day experiments by an almost unimaginable, breathtaking range. Correspondingly, the Planck time is the fleeting duration that a beam of light would require to cross this tiny Planck length. It represents an extremely, unbelievably short interval of time. Our most precise atomic clocks do not come close to resolving its fleeting passage. Even the fastest, most violent physical processes known to science take vastly longer to unfold. These microscopic scales are not arbitrarily chosen simply because they form attractive, neat round numbers. Rather, they naturally arise when several fundamental features of modern physics are elegantly combined. Gravity, chaotic quantum behavior, and the absolute speed at which information travels all merge to become essential parts of the very same estimate. The striking result indicates the precise boundary where no single existing theory can be safely ignored. Suppose we try to examine a smaller and still smaller region of space. Others describe deeper, fundamental objects whose complex behaviors collectively give rise to the very dimensions of space and time we experience every day. To resolve such exquisite, fine detail, we inevitably need radiation or probe particles with much shorter wavelengths. Shorter wavelengths, however, demand significantly greater energy. This elegant principle works remarkably well through ordinary microscopy and high-energy particle physics, where steadily increasing the energy allows us to probe ever smaller, hidden structures. Eventually, however, concentrating such a colossal amount of energy into an incredibly small region creates a formidable new problem. Energy inevitably contributes to gravity. If we pack too much energy into too little space, the heavily warped region may collapse to form a miniature black hole. The very attempt to closely inspect the smallest imaginable distance could end up hiding that distance forever behind an impenetrable event horizon. Instead of revealing finer, deeper detail, the ambitious experiment would merely create a dense object that completely prevents any information from escaping. Nature may therefore impose a fundamental limit upon us, not because our scientific instruments are poorly designed, but because the act of measurement itself profoundly changes the local geometry of space. This fascinating barrier is sometimes presented as compelling evidence that there must exist a smallest, fundamental, meaningful length in the cosmos. There are also elegant proposals in which spacetime is not fundamental at all, but rather emerges beautifully from deeper, hidden relationships, much like the warmth of temperature emerges from the frantic. That conclusion is highly plausible, yet it is not yet proven in a single, universally accepted way. Different theoretical approaches to quantum gravity describe this ultimate limit in wonderfully different ways. The profound, main lesson is that ordinary measurement cannot be separated from the relentless pull of gravity at sufficiently high energy scales. A microscope, after all, works by actively interacting with the tiny object being studied. At normal, macroscopic scales, this inevitable disturbance can be carefully controlled. But at the extreme Planck scale, the intense energy needed for the interaction may alter the surrounding spacetime so severely that the original target is no longer even available to be seen. This is one major reason why simply building a more powerful particle accelerator is not a straightforward, easy path to reaching the mysterious Planck scale. Current accelerators already require enormous, sprawling machines to reach the highest controlled particle energies. Reaching the Planck range directly would require an advanced technology far beyond anything currently available to humanity. Collective motion of countless tiny particles. Even if such immense energy could somehow be produced, concentrating and controlling it would raise exceptionally severe gravitational problems. The accelerator might become far less of a helpful microscope and more of an extraordinarily expensive attempt to create a tiny, microscopic black hole in a laboratory. Some intriguing theories involving additional hidden dimensions suggest that gravity could become remarkably strong at lower energies than the usual Planck estimate. These ideas naturally led to intense speculation that tiny, microscopic black holes might be produced during high-energy particle collisions. Yet, rigorous experiments have not found any evidence for such exotic objects, and the simplest versions of those proposals face very strict limits. If microscopic black holes could somehow form, they would be expected to evaporate almost instantaneously through subtle quantum effects, rather than grow uncontrollably by consuming the planet. After all, powerful cosmic rays have struck the Earth and other astronomical bodies at extremely high energies for billions of years without causing any such disasters. Nature has already performed countless high-energy collision experiments across the cosmos without ever asking for a safety meeting. Directly reaching the elusive Planck scale may be unrealistic, but indirect evidence could still beautifully reveal the correct theory. Physics often studies completely inaccessible conditions by carefully observing their distant consequences. If spacetime is indeed an emergent phenomenon, then breaking it might closely resemble disrupting the underlying system so utterly and completely that our large-scale, familiar descriptions simply no longer apply. No human enters the blazing core of a star, yet its outward light and subtle vibrations gracefully reveal what happens deep inside. No physical detector crosses a black hole's silent horizon and returns, yet the frantic motion and radiation just outside provide profound information about the object itself. In a similar way, quantum gravity may leave delicate, small traces in the early universe, the mysterious behavior of black holes, the ripples of gravitational waves, subtle particle interactions, or the grand, large-scale structure of the cosmos. The great challenge is separating those faint traces from ordinary, mundane effects and from the many dizzying theoretical possibilities. One elegant approach to quantum gravity is string theory. In its basic, beautiful picture, the fundamental objects of nature are not dimensionless points. Instead, they are conceived as small, extended structures that can vibrate in different ways. These different vibration patterns appear to us as different fundamental particles. This physical extension can gently soften some of the harsh mathematical problems that appear when particles interact at a single, exact point. Gravity arises naturally and beautifully within the theory because one of the possible vibrations behaves precisely like the graviton, the quantum carrier expected for gravity. A majestic wave can break violently upon a sandy shore even though the water itself does not break. String theory also requires additional spatial dimensions in its most familiar, elegant forms. These dimensions would be hidden or tightly compact at scales far too small to observe directly. The theory has developed over decades into a large, sophisticated framework connecting gravity, particle physics, black holes, and quantum information. It has produced important mathematical results and deeply useful insights into the mysterious nature of black hole entropy. It has also shown remarkable examples where a gravitational theory in one region of space is completely equivalent to a quantum theory without gravity on its boundary. What it has not yet produced is a unique, confirmed description of our own universe. There are still many possible ways the additional dimensions could be intricately arranged, leading to an immense landscape of possible low-energy worlds. Finding clear, undeniable experimental evidence remains incredibly difficult. Another profoundly different approach is loop quantum gravity. It begins by applying quantum principles directly to the very fabric of geometry. A dense traffic jam can dissolve into nothingness even though the solid road beneath it remains unchanged. In this startling picture, areas and volumes do not vary smoothly but instead come in discrete, indivisible units. Spacetime at the smallest scale is not a continuous fabric, but is built from a vibrant network of quantum relationships. This network is not sitting inside an already existing passive space. Rather, its dynamic connections help define and create space itself. A large, smooth geometry only emerges when many of these tiny quantum elements are considered together. This is deeply similar to how a smooth, continuous surface can emerge from a huge, invisible collection of atoms. A table feels completely continuous to a resting hand even though its matter is made from much smaller, separate parts. In just this way, spacetime might appear continuous. Thought, thinking process. A frozen solid can melt, dramatically altering its large-scale behavior while its basic, underlying particles continue to exist undisturbed. 1. Analyze the request. Role, great writer, dive in how, eloquent, poetic, yet precise. Task, rewrite and gently interpret/expand by 10 to 20%, adding adjectives and adverbs for smoother flow. Style, soulful, evocative, deeply expressive, Trian Cam. Language, English. Strict rules. 1. Length must be slightly longer than the original. Expansion 10 to 20%. 2. In a very similar way, what we call spacetime might entirely cease to behave smoothly without the broader reality itself fading into absolute nothingness. Preserve 100% of the plot, characters, terminology, tone, and flow. No changes to the underlying scientific concepts/analogies, just elevating the prose. 3. Continuity. Seamlessly connect from the BICAN on TRC. Previous context ended with spacetime might appear continuous, and leave the end open-ended exactly where the original text ends, which is imagine quantum fluctuations in 4. No introductory/explanatory text. No markdown. Only raw text. 2. Analyze the previous context. Ends with spacetime might appear continuous. This is precisely one major reason why the deceptively simple phrase how much force always requires incredibly careful, delicate handling. So the rewrite of the source text must begin seamlessly to follow that phrase. Actually, the source text starts with, because its fundamental units are far below any scale we can normally detect. So, putting them together, spacetime might appear continuous previous because its fundamental units are far. Source. I need to rewrite the source text starting exactly with because its fundamental units, or integrating it smoothly. 3. Analyze the original source text to rewrite va expand. Original. Because its fundamental units are far below any scale we can normally detect. Loop-based models can replace some. There may not exist a single mathematical value, a single absolute cosmic limit, or one final catastrophic push that causes the fabric of spacetime to fail universally. Classical singularities with quantum transitions. In certain descriptions of the early universe, the Big Bang singularity becomes a bounce from an earlier, contracting state. In models of black holes, the central collapse may also be halted or redirected by quantum geometry. These results depend on assumptions and, instead, different kinds of extreme physical conditions may produce entirely different, localized kinds of structural breakdown. Simplified settings. They do not yet provide a complete, confirmed account of realistic stars collapsing into black holes. Still, they demonstrate how a discrete spacetime might avoid the infinities of classical relativity. Other approaches treat spacetime as emerging from more basic quantum information. A highly concentrated mass may quietly create an inescapable horizon. Distance may reflect how strongly different parts of a quantum system are connected. Nearby regions would share more direct relationships while distant regions would be less closely linked. Entanglement becomes especially important in these ideas. Two quantum systems can share a state in a way that cannot be described as two. A rapid, violent acceleration may generate immensely powerful gravitational waves. Independent objects carrying separate information. Measurements show correlations that remain even when the systems are far apart. Some theoretical work suggests that the pattern of entanglement helps construct a smooth geometry, reduce or remove particular connections, and the corresponding spacetime may. An enormous amount of energy packed tightly into an infinitesimally tiny region may inevitably require the intervention of quantum gravity. Separate or change shape. This offers a new way to think about breaking spacetime. A tear might not require ripping a material surface. Could mean disrupting the quantum connections that allow two regions to behave as parts of one continuous geometry. In certain simplified models, reducing certain theoretical arrangements might also alter the very causal structure of the cosmos, fundamentally changing which events can influence which others. Entanglement between two sets of quantum degrees of freedom causes the geometric connection between them to narrow. Remove enough of it and the spacetime description divides into separate regions. That does not mean a person could cut spacetime using a machine that switches off entanglement. The examples are theoretical and often the ultimate result depends not only on how much energy is present, but crucially on exactly where it is located, how dynamically it moves, how it is distributed, and what geometric shape already surrounds it. Involve highly controlled mathematical systems. They show that geometry may be related to information more deeply than everyday experience suggests. Another possibility is that spacetime resembles a material with different phases. Water can be solid, liquid, or gas, without changing the basic type of. The sheer scale of these extreme conditions is immensely difficult for us to picture, primarily because our entire human experience takes place within a remarkably gentle, quiet gravitational environment. Molecule. A fundamental quantum system might produce smooth spacetime in one phase, and something with no ordinary geometry in another. Under moderate conditions, the spacetime phase would support familiar distances, directions, and causal order. Under extreme energy or temperature, it might enter a different state where even the comforting gravity that safely holds you to the Earth is astonishingly weak when compared with the ferocious gravitational fields near neutron stars and bottomless black holes. Those ideas no longer apply. The earliest universe may have passed through such a transition. Asking what happened before ordinary spacetime emerged could be difficult, because the word before assumes that time already existed. This does not automatically make the question meaningless. A deeper theory might contain an. We notice this gravity constantly in our daily lives because it acts relentlessly over incredibly long distances, and because our entire massive planet participates in pulling us down. Ordering concept that later becomes time. It may describe relationships between states without using the same clock-based structure we experience. The situation is similar to asking for the temperature of one isolated molecule. Temperature is useful for a large collection of particles, but it does not. Yet, you can effortlessly lift a small, simple object from the floor using nothing but the electromagnetic forces residing in your muscles, easily overcoming the cumulative gravitational pull of the entire Earth on that single object. Apply to a single molecule in the same way. If time is emergent, demanding an ordinary time coordinate at the deepest level may be asking for a large-scale property where it does not belong. The Planck scale is often described using the phrase quantum foam. The image suggests that spacetime at tiny scales may fluctuate violently with. Gravity is wonderfully persistent, but at our ordinary, familiar scales, it remains surprisingly beautifully weak. Geometry changing from moment to moment. Small tunnels or disconnected structures might appear and disappear. This picture came from attempts to imagine quantum fluctuations in. For drafting the rewrite, applying elegant, poetic literary prose, 10-20% expansion, keeping exact flow. Segment 1. Because its fundamental units are far below any scale we can normally detect. Rewrite, solely because its most fundamental microscopic units reside far below any physical scale we can ever hope to detect with our current, rudimentary instruments. Segment 2. Loop-based models can replace some classical singularities with quantum transitions. Near incredibly compact cosmic objects. However, this peaceful situation changes dramatically. Rewrite. Within the elegant framework of loop-based models, those once fearsome classical singularities are beautifully replaced by smooth, continuous quantum transitions. Segment 3. In certain descriptions of the early universe, the Big Bang singularity becomes a bounce from an earlier contracting state. Rewrite. In certain profound descriptions of the early primordial universe, the terrifying singularity of the Big Bang is reimagined as a majestic bounce arising from an earlier, quietly contracting cosmic state. Segment 4. In models of black holes, the central collapse may also be halted or redirected by quantum geometry. Rewrite. Similarly, in sophisticated models of black holes, the catastrophic central collapse may be gently halted or creatively redirected by the subtle, protective hand of quantum geometry. Segment 5. These results depend on assumptions and simplified settings. Rewrite. To be sure, these promising results still depend heavily on specific, idealized assumptions and highly simplified mathematical settings. Segment 6. They do not yet provide a complete confirmed account of realistic stars collapsing into black holes. Rewrite. They do not yet offer us a complete empirically confirmed account of how actual massive stars collapse into the dark abyss of real black holes. Segment 7. Still, they demonstrate how a discrete spacetime might avoid the infinities of classical relativity. A dense neutron star can contain far more mass than our entire sun, packed tightly into a tiny sphere roughly the size of a single human city. Rewrite. Nevertheless, they brilliantly demonstrate how a discrete, granular spacetime might gracefully avoid the catastrophic infinities that plague classical general relativity. Segment 8. Other approaches treat spacetime as emerging from more basic quantum information. Rewrite. Other innovative approaches choose to treat the fabric of spacetime as something deeply emergent, arising gracefully from far more basic, underlying quantum information. Segment 9. Distance may reflect how strongly different parts of a quantum system are connected. Rewrite. In this view, physical distance itself may merely reflect how strongly and intimately the different parts of a vast quantum system are connected to one another. Segment 10. Nearby regions would share more direct relationships, while distant regions would be less closely linked. Rewrite. Regions that appear nearby would share rich, direct relationships, whereas seemingly distant regions would simply be far less closely and vibrantly linked. Segment 11. Entanglement becomes especially important in these ideas. Rewrite. Within these radical ideas, the mysterious phenomenon of quantum entanglement becomes especially, singularly important. Segment 12. Two quantum systems can share a state in a way that cannot be described as two independent objects carrying separate information. The surface gravity is absolutely immense. Rewrite. Two separate quantum systems can share a single, unified state in a breathtaking way that cannot possibly be described as two independent, lonely objects carrying separate, isolated pieces of information. Segment 13. Measurements show correlations that remain even when the systems are far apart. Rewrite. Our precise measurements reveal haunting correlations that endure flawlessly, even when the physical systems are separated by vast, unimaginable distances. Segment 14. Some theoretical work suggests that the pattern of entanglement helps construct a smooth geometry. Rewrite. Fascinating theoretical work now suggests that this intricate, invisible pattern of entanglement is precisely what helps construct our illusion of a smooth, unbroken geometry. Segment 15. Reduce or remove particular connections, and the corresponding spacetime may separate or change shape. Rewrite. Reduce or sever these delicate, invisible connections, and the corresponding spacetime fabric may quietly separate or alter its very shape. Segment 16. This offers a new way to think about breaking spacetime. Rewrite. This profound insight offers us an entirely new, evocative way to think about the literal breaking of spacetime. Segment 17. A tear might not require ripping a material surface. Matter residing there is violently forced into extreme, exotic states that are utterly impossible to reproduce in bulk on Earth. Rewrite. A tear in the cosmos might not require the violent, physical ripping of a tangible material surface. Segment 18. It could mean disrupting the quantum connections that allow two regions to behave as parts of one continuous geometry. Rewrite. Instead, it could simply mean quietly disrupting those fragile quantum connections that allow two distinct regions to behave as harmonious parts of one continuous, unbroken geometry. Segment 19. In certain simplified models, reducing entanglement between two sets of quantum degrees of freedom causes the geometric connection between them to narrow. Rewrite. Indeed, in certain simplified mathematical models, carefully reducing the entanglement between two separate sets of quantum degrees of freedom causes the geometric bridge between them to slowly narrow and wither. Segment 20. Remove enough of it and the spacetime description divides into separate regions. Rewrite. If you remove enough of this unifying entanglement, the once unified spacetime description inevitably divides into completely separate, isolated regions. Segment 21. That does not mean a person could cut spacetime using a machine that switches off entanglement. Rewrite. Of course, that does not mean a human being could ever hope to cut spacetime using some futuristic machine designed to switch off entanglement at will. Segment 22. The examples are theoretical and often involve highly controlled mathematical systems. Move even closer to the edge of a black hole, and the subtle differences in gravity from one point to another can suddenly become incredibly severe. Rewrite. These elegant examples remain purely theoretical, almost always involving highly controlled, abstract mathematical systems. Segment 23. They show that geometry may be related to information more deeply than everyday experience suggests. Rewrite. Yet, they undeniably show that physical geometry may be woven into the fabric of information far more deeply than our limited, everyday experience could ever suggest. Segment 24. Another possibility is that spacetime resembles a material with different phases. Rewrite. Another captivating possibility is that spacetime itself closely resembles a material substance capable of existing in different, distinct phases. Segment 25. Water can be solid, liquid, or gas without changing the basic type of molecule. Rewrite. Just as ordinary water can exist as solid ice, flowing liquid, or invisible gas without ever changing its basic, underlying molecular identity. Segment 26. A fundamental quantum system might produce smooth spacetime in one phase and something with no ordinary geometry in another. Rewrite. A fundamental quantum system might similarly produce a smooth, familiar spacetime in one phase and transition into something utterly devoid of ordinary geometry in another. Segment 27. Under moderate conditions, the spacetime phase would support familiar distances, directions, and causal order. These harsh differences are known to science as tidal effects. Rewrite. Under moderate, gentle conditions, this hospitable spacetime phase would comfortably support our familiar concepts of distances, clear directions, and a reliable causal order. Segment 28. Under extreme energy or temperature, it might enter a different state where those ideas no longer apply. Rewrite. However, under extreme, violent energies or unfathomable temperatures, it might enter a wild, chaotic state where those familiar concepts simply no longer apply. Segment 29. The earliest universe may have passed through such a transition. Rewrite. The earliest infant universe may well have passed through just such a dramatic, fundamental phase transition. Segment 30. Asking what happened before ordinary spacetime emerged could be difficult because the word before assumes that time already existed. Rewrite. Asking what happened before ordinary, structured spacetime emerged can be exceedingly difficult, primarily because the very word before already assumes that a river of time was already flowing. Segment 31. This does not automatically make the question meaningless. Rewrite. Yet, this conceptual hurdle does not automatically render the profound question entirely meaningless. Segment 32. A deeper theory might contain an ordering concept that later becomes time. They can relentlessly stretch an object in one. It may describe relationships between states without using the same clock-based structure we experience. Rewrite. A deeper, more fundamental theory might contain a subtle ordering concept that only later ripens into what we perceive as time. It may describe the intricate, timeless relationships between states without ever relying on the rigid, clock-based structure we experience in our daily lives. Segment 33. The situation is similar to asking for the temperature of one isolated molecule. Rewrite. The perplexing situation is remarkably similar to asking for the precise temperature of a single, isolated molecule. Segment 34. Temperature is useful for a large collection of particles, but it does not apply to a single molecule in the same way. Rewrite. Temperature is an incredibly useful measure for a vast, bustling collection of particles, but the concept simply does not apply to a lone, solitary molecule in that same familiar way. Segment 35. If time is emergent, demanding an ordinary time coordinate at the deepest level may be asking for a large-scale property where it does not belong. Rewrite. If time is truly emergent, demanding an ordinary, neat time coordinate at the deepest, most fundamental level of reality may be mistakenly asking for a macroscopic, large-scale property where it simply does not belong. Segment 36. The Planck scale is often described using the phrase quantum foam. Direction while violently squeezing it in another. Rewrite. The mysterious, ultramicroscopic Planck scale is often vividly described by physicists using the evocative phrase quantum foam. Segment 37. The image suggests that spacetime at tiny scales may fluctuate violently with geometry changing from moment to moment. Rewrite. This vivid image suggests that spacetime at these unimaginably tiny scales may fluctuate violently, with its geometry shifting restlessly from one fleeting moment to the next. Segment 38. Small tunnels or disconnected structures might appear and disappear. Rewrite. Within this roiling sea, minuscule wormholes, tiny tunnels, or completely disconnected topological structures might constantly appear and vanish like phantoms. Segment 39. This picture came from attempts to imagine quantum fluctuations in. Rewrite. This dramatic picture originally arose from early, daring attempts to imagine the chaotic quantum fluctuations in. Note: must end exactly with imagine quantum fluctuations in or something equivalent but slightly expanded yet keeping the exact unfinished state at the end. The original ends with imagine quantum fluctuations in attempts to imagine quantum fluctuations in. Let's write the ending as, this mesmerizing picture arose from early, daring attempts to imagine quantum fluctuations in to keep the exact sentence unfinished at in. For a relatively small, compact black hole, these relentless tidal forces near the event horizon would prove tragically fatal long before any intrepid traveler could ever find a single moment to admire the terrifyingly beautiful view. 5. Reviewing constraints. 1. Slightly longer than the original, 10 to 20% expansion. Yes, the flow is beautifully expanded, using rich vocabulary and smooth transitions. 2. Preserve 100% of the plot, characters, terminology, tone, and flow. Yes, all concepts, loop-based models, Big Bang bounce, black holes, entanglement, phase transitions, temperature of a single molecule, quantum foam, are strictly preserved. 3. Seamless continuity. It starts with because, continuing from spacetime might appear continuous, and ends mid-sentence at imagine quantum fluctuations in matching the original. 4. No intro, no outro, no markdown, raw text only. Yes, absolutely clean text. Conversely, around a truly supermassive black hole, the formidable horizon might be crossed in relative peace, where the local tidal forces are whisper-soft and much milder. 6. Final polish of the text, ensuring beautiful, poetic flow. Solely because its most fundamental microscopic units reside far below any physical scale we can ever hope to detect with our current, rudimentary instruments. Within the elegant framework of loop-based models, those once fearsome classical singularities are beautifully replaced by smooth, continuous quantum transitions. In certain profound descriptions of the early primordial universe, the terrifying singularity of the Big Bang is reimagined as a majestic bounce arising from an earlier, quietly contracting cosmic state. Similarly, in sophisticated models of black holes, the catastrophic central collapse may be gently halted or creatively redirected by the subtle, protective hand of quantum geometry. To be sure, these promising results still depend heavily on specific, idealized assumptions and highly simplified mathematical settings. They do not yet offer us a complete, empirically confirmed account of how actual massive stars collapse into the dark abyss of real black holes. Nevertheless, they brilliantly demonstrate how a discrete, granular spacetime might gracefully avoid the catastrophic infinities that plague classical general relativity. Other innovative approaches choose to treat the fabric of spacetime as something deeply emergent, arising gracefully from far more basic, underlying quantum information. Yet, even here, the inevitable journey deeper inward would still reach a dark and catastrophic end. In this view, physical distance itself may merely reflect how strongly and intimately the different parts of a vast quantum system are connected to one another. Regions that appear nearby would share rich, direct relationships, whereas seemingly distant regions would simply be far less closely and vibrantly linked. Within these radical ideas, the mysterious phenomenon of quantum entanglement becomes especially, singularly important. Two separate quantum systems can share a single, unified state in a breathtaking way that cannot possibly be described as two independent, lonely objects carrying separate, isolated pieces of information. Our precise measurements reveal haunting correlations that endure flawlessly, even when the physical systems are separated by vast, unimaginable distances. Fascinating theoretical work now suggests that this intricate, invisible pattern of entanglement is precisely what helps construct our illusion of a smooth, unbroken geometry. Reduce or sever these delicate, invisible connections, and the corresponding spacetime fabric may quietly separate or alter its very shape. This profound insight offers us an entirely new, evocative way to think about the literal breaking of spacetime. A tear in the cosmos might not require the violent, physical ripping of a tangible material surface. Instead, it could simply mean quietly disrupting those fragile quantum connections that allow two distinct regions to behave as harmonious parts of one continuous, unbroken geometry. These tidal forces offer us another, more nuanced meaning of what it truly means to break. Indeed, in certain simplified mathematical models, carefully reducing the entanglement between two separate sets of quantum degrees of freedom causes the geometric bridge between them to slowly narrow and wither. If you remove enough of this unifying entanglement, the once unified spacetime description inevitably divides into completely separate, isolated regions. Of course, that does not mean a human being could ever hope to cut spacetime using some futuristic machine designed to switch off entanglement at will. These elegant examples remain purely theoretical, almost always involving highly controlled, abstract mathematical systems. Yet, they undeniably show that physical geometry may be woven into the fabric of information far more deeply than our limited, everyday experience could ever suggest. Another captivating possibility is that spacetime itself closely resembles a material substance capable of existing in different, distinct phases. Just as ordinary water can exist as solid ice, flowing liquid or invisible gas without ever changing its basic, underlying molecular identity, a fundamental quantum system might similarly produce a smooth, familiar spacetime in one phase, and transition into something utterly devoid of ordinary geometry in another. Under moderate, gentle conditions, this hospitable spacetime phase would comfortably support our familiar concepts of distances, clear directions, and a reliable causal order. However, under extreme, violent energies or unfathomable temperatures, it might enter a wild, chaotic state where those familiar concepts simply no longer apply. The fabric of spacetime itself may remain perfectly, mathematically smooth even as the physical objects dwelling within it are violently pulled apart. The earliest infant universe may well have passed through just such a dramatic, fundamental phase transition. Asking what happened before ordinary, structured spacetime emerged can be exceedingly difficult, primarily because the very word before already assumes that a river of time was already flowing. Yet, this conceptual hurdle does not automatically render the profound question entirely meaningless. A deeper, more fundamental theory might contain a subtle ordering concept that only later ripens into what we perceive as time. It may describe the intricate, timeless relationships between states without ever relying on the rigid, clock-based structure we experience in our daily lives. The perplexing situation is remarkably similar to asking for the precise temperature of a single, isolated molecule. Temperature is an incredibly useful measure for a vast, bustling collection of particles, but the concept simply does not apply to a lone, solitary molecule in that same familiar way. If time is truly emergent, demanding an ordinary, neat time coordinate at the deepest, most fundamental level of reality may be mistakenly asking for a macroscopic, large-scale property where it simply does not belong. The mysterious, ultramicroscopic Planck scale is often vividly described by physicists using the evocative phrase quantum foam. This vivid image suggests that spacetime at these unimaginably tiny scales may fluctuate violently, with its geometry shifting restlessly from one fleeting moment to the next. A majestic planet, a glowing star, or an unfortunate, fragile spacecraft can be utterly disrupted simply because their neighboring parts are forced onto increasingly divergent and hostile paths. Within this roiling sea, minuscule wormholes, tiny tunnels, or completely disconnected topological structures might constantly appear and vanish like phantoms. This mesmerizing picture originally arose from early, daring attempts to imagine quantum fluctuations in 7. Final sanity checks. Words end with "imagine quantum fluctuations in exact match." Previous context ended with "spacetime might appear continuous exact continuation with solely because it's works perfectly." Tone. Very elegant, poetic, beautifully written, grand writer persona. No markdown, raw text only. No intro or outro. Solely because its most fundamental microscopic units reside far below any physical scale we can ever hope to detect with our current, rudimentary instruments. It is the physical object that breaks, not the silent, underlying canvas of spacetime. Within the elegant framework of loop-based models, those once fearsome classical singularities are beautifully replaced by smooth, continuous quantum transitions. In certain profound descriptions of the early primordial universe, the terrifying singularity of the Big Bang is reimagined as a majestic bounce arising from an earlier, quietly contracting cosmic state. Similarly, in sophisticated models of black holes, the catastrophic central collapse may be gently halted or creatively redirected by the subtle, protective hand of quantum geometry. To be sure, these promising results still depend heavily on specific, idealized assumptions and highly simplified mathematical settings. They do not yet offer us a complete, empirically confirmed account of how actual massive stars collapse into the dark abyss of real black holes. Nevertheless, they brilliantly demonstrate how a discrete, granular spacetime might gracefully avoid the catastrophic infinities that plague classical general relativity. Other innovative approaches choose to treat the fabric of spacetime as something deeply emergent, arising gracefully from far more basic, underlying quantum information. In this view, physical distance itself may merely reflect how strongly and intimately the different parts of a vast quantum system are connected to one another. Regions that appear nearby would share rich, direct relationships, whereas seemingly distant regions would simply be far less closely and vibrantly linked. Within these radical ideas, the mysterious phenomenon of quantum entanglement becomes especially, singularly important. This is a subtle, crucial distinction easily lost in the dramatic descriptions of cosmic destruction. Two separate quantum systems can share a single, unified state in a breathtaking way that cannot possibly be described as two independent, lonely objects carrying separate, isolated pieces of information. Our precise measurements reveal haunting correlations that endure flawlessly, even when the physical systems are separated by vast, unimaginable distances. Fascinating theoretical work now suggests that this intricate, invisible pattern of entanglement is precisely what helps construct our illusion of a smooth, unbroken geometry. Reduce or sever these delicate, invisible connections, and the corresponding spacetime fabric may quietly separate or alter its very shape. This profound insight offers us an entirely new, evocative way to think about the literal breaking of spacetime. A tear in the cosmos might not require the violent, physical ripping of a tangible material surface. Instead, it could simply mean quietly disrupting those fragile quantum connections that allow two distinct regions to behave as harmonious parts of one continuous, unbroken geometry. Indeed, in certain simplified mathematical models, carefully reducing the entanglement between two separate sets of quantum degrees of freedom causes the geometric bridge between them to slowly narrow and wither. If you remove enough of this unifying entanglement, the once unified spacetime description inevitably divides into completely separate, isolated regions. Of course, that does not mean a human being could ever hope to cut spacetime using some futuristic machine designed to switch off entanglement at will. When we say that gravity tears an object apart, it does not mean that gravity has torn the deeper, underlying geometry of the universe. These elegant examples remain purely theoretical, almost always involving highly controlled, abstract mathematical systems. Yet, they undeniably show that physical geometry may be woven into the fabric of information far more deeply than our limited, everyday experience could ever suggest. Another captivating possibility is that spacetime itself closely resembles a material substance capable of existing in different, distinct phases. Just as ordinary water can exist as solid ice, flowing liquid or invisible gas without ever changing its basic, underlying molecular identity, a fundamental quantum system might similarly produce a smooth, familiar spacetime in one phase, and transition into something utterly devoid of ordinary geometry in another. Under moderate, gentle conditions, this hospitable spacetime phase would comfortably support our familiar concepts of distances, clear directions, and a reliable causal order. However, under extreme, violent energies or unfathomable temperatures, it might enter a wild, chaotic state where those familiar concepts simply no longer apply. The earliest infant universe may well have passed through just such a dramatic, fundamental phase transition. Asking what happened before ordinary, structured spacetime emerged can be exceedingly difficult, primarily because the very word before already assumes that a river of time was already flowing. Yet, this conceptual hurdle does not automatically render the profound question entirely meaningless. The vast universe also offers grand examples of expansion rather than catastrophic collapse. A deeper, more fundamental theory might contain a subtle ordering concept that only later ripens into what we perceive as time. It may describe the intricate, timeless relationships between states without ever relying on the rigid, clock-based structure we experience in our daily lives. The perplexing situation is remarkably similar to asking for the precise temperature of a single, isolated molecule. Temperature is an incredibly useful measure for a vast, bustling collection of particles, but the concept simply does not apply to a lone, solitary molecule in that same familiar way. If time is truly emergent, demanding an ordinary, neat time coordinate at the deepest, most fundamental level of reality may be mistakenly asking for a macroscopic, large-scale property where it simply does not belong. The mysterious, ultramicroscopic Planck scale is often vividly described by physicists using the evocative phrase quantum foam. This vivid image suggests that spacetime at these unimaginably tiny scales may fluctuate violently, with its geometry shifting restlessly from one fleeting moment to the next. Within this roiling sea, minuscule wormholes, tiny tunnels, or completely disconnected topological structures might constantly appear and vanish like phantoms. This mesmerizing picture originally arose from early, daring attempts to imagine quantum fluctuations in geometry. On truly immense cosmic scales, the vast distances between unbound galaxies gradually increase as space itself quietly and endlessly expands. Yet, this vivid illustration should by no means be mistaken for a confirmed microscopic photograph of the subatomic realm. We do not possess any concrete proof that spacetime literally resembles a restless foam, nor does any empirical evidence point to tiny, whispering bubbles floating silently beneath the calm surface of our ordinary reality. The profound value of this metaphor lies simply in the realization that our familiar, smooth geometry may become fundamentally unreliable at these unimaginable scales. If indeed every conceivable shape contributes dynamically to the overarching quantum state, then spacetime itself may lack any single, definite structure until it is gently coaxed into focus at a much larger scale. Such deep-seated uncertainty could inevitably disrupt the very chronological order of events. At our comforting, ordinary scales of existence, one clear event can directly cause another, provided a physical signal has sufficient time to travel gracefully between them. Here, the majestic causal structure of the universe remains solid and clear enough to strictly prevent any bizarre effects from arriving before their rightful causes. Yet, down at the elusive Planck scale, the violently fluctuating geometry could render these neat, sequential relationships far less definite. The fundamental idea of one distinct event occurring strictly before another might dissolve, becoming merely an approximate truth. Consequently, any complete and harmonious theory would still be heavily tasked with explaining exactly why ordinary cause and effect manage to emerge so reliably and beautifully at larger, macroscopic scales. In the dawn of the early universe, this expansion may have surged through a brief, breathtaking period of extraordinary acceleration. In response, certain intriguing theoretical proposals seek to preserve a fundamental, unbreakable causal order at the very bottom of things. Causal set theory, for example, elegantly treats the fabric of spacetime as a vast, web-like collection of discrete, fundamental events, all intricately connected by relations that dictate precisely which events are permitted to influence others. The seamless, smooth dimensions we observe in our daily lives would eventually emerge from a staggeringly large set of these basic, primordial connections. Within such an elegant model, the sheer number of these fundamental events corresponds roughly to the overall spacetime volume itself. Thus, geometry itself becomes purely statistical in nature, much like how macroscopic pressure emerges naturally from the chaotic, collective collisions of countless tiny particles in a container of gas. Conversely, other creative approaches seek to build the grand tapestry of spacetime from simple, discrete geometric building blocks. These fundamental pieces are combined in countless possible configurations, allowing a smooth, macroscopically stable universe to emerge organically from their collective, harmonious behavior. The ultimate goal remains to successfully recover Einstein's general relativity without ever assuming a smooth, continuous spacetime fabric right from the beginning. Each of these competing approaches makes a distinctly different philosophical choice about what should be considered truly fundamental. String theory, for instance, boldly places extended, vibrating quantum objects at the very heart of reality. Some highly speculative models even contemplate far-off futures where this expansion becomes so relentlessly intense that majestic galaxies, solar systems, peaceful planets, and eventually the smallest atomic structures are inexorably pulled apart. Loop-based theories, on the other hand, make quantum geometry itself the central pillar of existence. Meanwhile, causal sets choose to begin simply with primordial events and their absolute causal ordering. Still other elegant, information-based approaches focus their lens on the fundamental quantum relationships that bind reality together. Beyond these, various alternative models employ complex fields, mathematical matrices, intricate networks, or even more unfamiliar exotic structures. This dazzling abundance of ideas mirrors both the profound importance and the immense, daunting difficulty of this cosmic puzzle. As of yet, empirical experiments have not been able to gently force physicists toward a single, definitive final theory. Many of these brilliant proposals can successfully match known physics at currently accessible energy scales, a vital achievement, yet one that remains tantalizingly insufficient. A truly successful theory of quantum gravity must faithfully reproduce all the rigorously tested predictions of general relativity in regions where cosmic curvature is moderate and distances are comfortably large. Simultaneously, it must harmonize perfectly with quantum physics in realms where the pull of gravity is remarkably weak. It must naturally explain the mysterious nature of black hole entropy, successfully avoid or elegantly interpret cosmic singularities, and vividly describe the turbulent early universe without relying on arbitrary, undefined conditions. This hauntingly poetic idea is often called the Big Rip. Most importantly, it should ideally make clear, distinct predictions that can eventually be tested in our laboratories. For any theory that explains everything only at unreachable, extreme energies risks becoming tragically indistinguishable from its many imaginative competitors. For this reason, dedicated researchers tirelessly search for ways to achieve physical amplification. They hope that a microscopic quantum gravity effect might accumulate over vast, cosmic distances, or perhaps manifest clearly within a highly sensitive, modern experimental system. For instance, ancient light traveling across the cosmos from a distant stellar explosion could potentially reveal whether the texture of spacetime causes photons of different energies to travel at slightly different, discernible speeds. Thus far, precise observations have placed remarkably strict, narrow limits on many such proposed effects. High-energy photons journeying from incredibly distant cosmic sources arrive here with no noticeable, Planck-scale delay of the exact type predicted by certain theoretical models. Of course, this does not completely rule out the existence of quantum gravity. Rather, it effectively rules out or severely constrains the specific, dramatic ways in which such an effect might manifest. Similarly, the delicate polarization of ancient, primordial light can also serve to test whether spacetime possesses subtle directional or energy-dependent properties. Once again, actual observations continuously demonstrate that ordinary, classical relativity works with breathtaking accuracy. It depends entirely on the elusive nature of dark energy, which remains deeply shrouded in scientific uncertainty. Any underlying microscopic granularity must therefore preserve this seamless, smooth behavior with truly remarkable, exquisite accuracy at all larger scales. Meanwhile, the whisper of gravitational waves rushing through the cosmos offers yet another thrilling possibility for discovery. If the very fabric of spacetime possesses a delicate microscopic structure, traveling waves might subtly disperse, gradually lose their energy, or slowly develop intricate additional patterns as they journey across the vast cosmos. Our current observations reveal no convincing departure from the elegant framework of general relativity, yet future, more sensitive detectors will examine far longer signals and significantly broader frequency ranges. Ultimately, the primordial early universe may provide us with the strongest and most magnificent natural experiment of all. During its first fleeting moments, the cosmic energy densities were immeasurably greater than anything that humans could ever hope to create in a laboratory. Subtle quantum fluctuations were rapidly stretched to immense astronomical scales by the sudden cosmic expansion, and they may well have left delicate, lasting patterns imprinted in the distribution of matter and ancient cosmic radiation. Precise measurements of those ancient patterns already strongly support the beautiful idea that these tiny, primordial fluctuations became the very seeds from which great galaxies grew. Even more detailed observations may eventually reveal whether gravity itself experienced its own quantum fluctuations and how those fluctuations dynamically behaved in the infancy of time. A highly specific pattern imprinted in the ancient cosmic microwave background radiation could provide the first definitive evidence of elusive primordial gravitational waves. Yet, even in that extreme scenario, asserting that spacetime breaks would merely be a convenient and simplified shorthand. Successfully detecting it would offer invaluable information about the unimaginably high-energy conditions that governed the earliest moments of the universe. Yet, this noble search remains exceedingly difficult, because interstellar dust within our own galaxy and various other cosmic effects can easily mimic key parts of this subtle signal. Meanwhile, black holes remain another major and profoundly mysterious testing ground for these fundamental ideas. Their thermodynamic temperature and hidden entropy beautifully connect the seemingly disparate realms of quantum theory, gravity, and thermodynamics. Any proposed theory of quantum gravity must thoroughly explain why the area of the event horizon behaves so precisely like a direct measure of hidden microscopic information. Some mathematical approaches seek to count the vast number of possible quantum states that correspond directly to a black hole possessing a specific set of visible, macroscopic properties. In certain special, highly symmetric cases, this complex quantum calculation matches the black hole entropy predicted so elegantly through classical gravity. This is profoundly important because it strongly suggests that black holes are not merely featureless, empty objects at their deepest, most fundamental level. Instead, they possess countless microscopic arrangements, even though a distant outside observer can only detect their macroscopic mass, spin rotation, and electric charge. Those rich microscopic states may ultimately explain how delicate physical information is preserved as the black hole slowly undergoes quantum evaporation. The cosmic geometry would simply evolve in a way that dissolves all bound structures, while the deeper, more profound meaning of that final state would depend on a more complete and correct physical theory. The outgoing Hawking radiation could contain extremely subtle, hidden correlations that only reveal themselves when the entire quantum process is fully and comprehensively considered. If that view is correct, the perfectly smooth horizon and interior geometry described by general relativity may only be convenient, approximate features of a deeper reality. They function beautifully for immense black holes and ordinary, macroscopic observers, but the complete, underlying quantum state contains far more rich information than the classical geometry ever reveals. The elusive Planck scale would then represent the precise level where this hidden description becomes absolutely unavoidable. It is the boundary where spacetime itself stops being a sufficient starting point for our theories and instead becomes a phenomenon that must be deeply and fundamentally explained. This shifts and transforms our original inquiry once again. To ask how much physical force would be required to tear or break spacetime is to assume that spacetime is a tangible, foundational substance already present in the background. Yet, at the extreme limits of the Planck scale, physical force itself may no longer be the most basic or meaningful concept. After all, the very concept of force inherently requires distinct objects, definite positions, continuous changes in motion, and the passage of time. If those familiar concepts only emerge from a much deeper layer of physics, then our questions must be translated into the true native language of that underlying, fundamental theory. There exist even more exotic, wondrous possibilities within the realms of theoretical physics. We might instead ask how much colossal energy must be concentrated within a tiny region before our smooth, classical geometry completely fails. We might ask what extreme conditions destroy the very connections that produce the perception of distance. Or we might ask whether a region of the universe can undergo a profound phase transition into an exotic state entirely devoid of ordinary space and time. Currently, none of these fascinating questions has a single confirmed numerical answer. While there is indeed a natural energy scale associated with quantum gravity, Reaching it does not guarantee some simple, dramatic event where the fabric of spacetime suddenly cracks. The actual outcome could depend delicately on the precise distribution of energy, the underlying quantum state, the surrounding geometric landscape, and the specific theory that ultimately proves to be correct. A single, isolated particle carrying enormous energy does not necessarily create the same physical situation as that very same amount of energy tightly compressed and trapped within a tiny, localized region. Two energetic particles passing swiftly through one another differ fundamentally from a stable, dense concentration of energy. A black hole, for instance, spreads its mass behind a protective event horizon, whose physical size depends crucially on that mass. Hypothetical cosmic strings, if they truly exist, could create highly unusual, shimmering distortions in the cosmic fabric. In the grand cosmic theater, the delicate arrangement of this matter remains just as crucial as it always was for the life and death of stars. Mere total energy alone can never be enough to dictate the outcome. Indeed, density, motion, exquisite symmetry, pressure, and the intricate quantum state all contribute their own silent voices to the final equation. There may also exist a fundamental, sovereign limit on precisely how much information can be compressed within a local region of space before it inevitably collapses into the dark embrace of a black hole. This profound connection between the area of the horizon and its internal entropy strongly suggests that nature restricts information storage far more severely, and indeed more beautifully, than our ordinary, volume-based intuition would ever imply. Should too much raw energy or dense information be tightly packed into a single, confined region, the underlying fabric of space may respond defensively by cloaking itself within a newly formed horizon. The resulting black hole then quietly hides this attempted physical overloading behind an impenetrable, silent boundary. This intriguing behavior has led many contemplative physicists to view these black holes as nature's own way of strictly enforcing an absolute limit on what can be resolved or stored locally within our universe. From that poetic perspective, spacetime actively protects itself from our direct, intrusive probing. Push too aggressively at an infinitesimally small distance, and the very experiment itself yields a shielding horizon. The secretly hidden region may well contain the long-sought truths of quantum gravity, but the curious observer remains forever locked outside, left to ponder with only indirect, tantalizing evidence. High-energy collisions far beyond the reach of our current machines might someday probe the smallest, most fundamental scales of reality. Yet, this does not mean that the mysterious Planck scale is forever rendered inaccessible to human inquiry. The universe has already effortlessly created the necessary extreme conditions. They may lie waiting inside the hearts of active black holes, and they certainly must have existed during the violent earliest epochs of the cosmic dawn. The daunting problem we face is finding those faint, resilient signals that somehow survive this journey and finally reach our patient instruments. A truly correct, unified theory might predict subtle, undeniable features of black hole mergers, gradual Hawking evaporation, early cosmic structures, or peculiar particle behaviors that no competing framework could ever hope to reproduce. Just one reliable, undeniable discrepancy could provide the crucial, illuminating opening that physicists so desperately need. For now, however, the elusive Planck scale remains a stark warning label attached to our grandest calculations. Below this incredibly minuscule threshold, the very concept of a smooth, continuous spacetime may cease to carry any physical meaning at all. Near this perilous boundary, the wild infinities that plague classical relativity simply cannot be accepted without some form of deep, stabilizing quantum correction. Concepts that once seemed fundamental may dissolve into mere rough approximations. Furthermore, certain elegant solutions of relativity even allow for closed paths through time, though whether nature actually permits the required conditions is an entirely different, unresolved question. Space itself could be discrete, woven from individual threads. Time could be merely emergent, a collective illusion. Geometry could beautifully arise from quantum entanglement. Devastating singularities could be transformed into smooth transitions, and the mysterious interiors of black holes could be encoded in information stored in some wholly unexpected, holographic way. Each of these revolutionary options would replace our simple, violent image of a torn cosmic sheet with something far more intricate and wondrously complicated. The evocative word fray is therefore infinitely more suitable to describe this phenomenon than the abrupt word break. Our cherished theories begin to fray precisely because their underlying assumptions are violently pulled in completely different directions. General relativity assumes a continuous, smoothly curved geometry, while quantum physics demands chaotic fluctuations and fundamental uncertainty. Applying both simultaneously without a deeper, more harmonizing framework produces only irreconcilable contradictions or mathematically uncontrolled infinities. Yet, the physical universe itself does not necessarily fray along with our mathematical struggles. The common thread throughout these mysteries is that the mathematical equations allow us to explore realms far beyond our ordinary human experience. Nature continues doing whatever it elegantly does, undisturbed. It is merely our human description that loses its sharp clarity. That profound distinction has appeared before us several times throughout scientific history. A catastrophic singularity might represent a genuine physical failure of spacetime itself, or it might simply be a failure of general relativity to explain the extreme. A dark horizon might hide a true physical endpoint, or it might merely conceal a rich quantum state that remains beautifully finite. For now, the absolute absence of a complete, unified theory prevents us from deciding which path is true. The ultimate, final answer must therefore carefully separate what is directly measured from what is merely theoretically inferred. We know with certainty that spacetime gracefully bends. We know that physical clocks slow down in response to gravity. We know that whispering gravitational waves carry real, measurable energy. Yet they do not always guarantee that such extraordinary situations can ever truly manifest in the physical universe. We know that black holes form and violently merge. We know, too, that quantum physics strictly governs the microscopic systems of our world. Yet, we do not know whether spacetime is composed of fundamental, indivisible pieces. We do not know exactly what physical reality replaces a black hole singularity. We do not know whether time itself truly exists at the deepest, most fundamental level of reality. We do not know whether a geometric connection can ever be fully destroyed in a physically realizable actual process. These haunting uncertainties do not render the quest useless. Rather, they show us exactly where the grand, untamed frontier of human knowledge lies. The titanic force required to break spacetime may not actually be a physical force at all. The closest known threshold we can conceive is that extreme concentration of energy where quantum gravity takes absolute control, and our comforting assumption of a smooth geometry can no longer be held. Whether that profound transition creates in our quest for understanding, a useful and disciplined scientific habit is to carefully separate three fundamental questions. Boundary, a dramatic quantum bounce, a completely new phase of existence, a deeply hidden network, or perhaps no space-time at all in our familiar sense remains an open, whispering mystery. To truly finish this long journey, we must carefully gather the different meanings of what it means to break, and gently decide which of these nature clearly allows, which remain mere elegant mathematical possibilities, and which may only reflect the fragile limits of the very language we use to describe the vast universe. After following the silent pull of gravity from swirling planets to burning stars, from collapsing stellar cores to dark, enigmatic black holes, and from faint gravitational waves to the incomprehensibly small Planck scale, we can finally return to the haunting question that started this entire journey. Can space-time truly and irrevocably break? The most honest and humble answer is that we do not yet know. Physics generously offers us several profound situations that closely resemble breaking, but none of them can be confidently confirmed as a literal, physical tear in the cosmic fabric of spacetime. Some are merely dramatic changes in geometry. Others are invisible boundaries that stubbornly prevent information from ever escaping. Can the mathematics elegantly describe it? Some are quiet places where our most cherished equations simply stop working. And others still are purely theoretical possibilities that may never actually occur in the real, tangible universe. The true difficulty begins with the simple word break. A physical, everyday object breaks when the subtle forces holding its parts together can no longer resist external stress. Fragile glass develops sharp cracks because the molecular bonds in the material suddenly fail. Strong metal bends and eventually separates when its internal crystalline structure can no longer support the heavily applied load. Even a simple biscuit breaks because warm tea has quietly, almost poetically, completed the work that gravity first began. Yet, spacetime is not known to be a tangible material made from ordinary particles and chemical bonds. It does not possess a measurable strength in the same familiar way as forged steel, solid stone, or delicate glass. There is no confirmed experimental test showing that a certain massive amount of pressure causes it to split into jagged pieces. Can nature actually produce it? This ultimately means there is no universally accepted value for the immense force needed to break the continuum of spacetime. What physics can beautifully describe, however, is curvature. Matter and energy gently alter and mold the silent geometry of space and time. A small amount creates a subtle, almost unnoticeable effect. A vast, concentrated mass creates a much more powerful and undeniable effect. Planets curve spacetime just enough to cradle moons in their orbits. Stars curve it deeply enough to guide wandering planets and gently bend traveling starlight. Dense neutron stars create an immensely stronger and more violent curvature. And black holes create dark, absolute regions where escape itself becomes utterly impossible. Yet, absolutely none of these extreme examples require spacetime to actually tear. Can we eventually observe clear evidence for it? A black hole is often treated as the absolute clearest candidate for a broken spacetime, but the mysterious event horizon itself is not a physical crack. It is merely a silent boundary separating events that can still communicate with the wide, outside universe from those lonely events that cannot. A traveling object can cross this horizon peacefully without ever striking a solid surface. For a sufficiently large and majestic black hole, an observer may cross it without feeling anything sudden or violent at that exact, fateful location. The geometry at the horizon can remain perfectly smooth, and general relativity describes this transition beautifully. The truly serious problem lies much deeper inside, where the classical theory inevitably predicts a singularity. A singularity is often described, rather simply, as a point of infinite density. That stark description captures a significant part of the problem, but it can easily create the wrong mental picture. It may sound like a tiny, infinitely heavy object sitting quietly at the center of the black hole, with an unlimited, unimaginable amount of matter packed tightly into it. A more careful and precise description is that the spacetime paths in our theory become abruptly incomplete. These three questions, simple as they seem, often yield vastly different answers. They reach a sudden end, and the mathematical theory offers absolutely no ordinary continuation. If a falling observer reaches that mysterious end after a finite, fleeting amount of personal time, spacetime simply appears to stop providing any future path at all. That quiet cessation is much closer to what a true breaking might mean. The geometry no longer behaves as a harmonious, complete structure. Still, we must remember this stark prediction comes from general relativity alone. General relativity does not include a full, delicate quantum description of gravity. Near the singularity, matter and geometry would inevitably reach extreme conditions where subtle quantum effects must become essential. Using the classical theory, there may be very much like using the broad, smooth rules of ordinary water flow to describe the chaotic dance of individual molecules. While this magnificent theory remains immensely successful when applied to the grand, sweeping scales of the cosmos, it may simply lack the vital, delicate ingredients required to describe the infinitesimally small. This profound limitation leaves us poised between two fascinating possibilities. An imaginative model may perfectly allow for a traversable spacetime tunnel, while realistic, everyday matter cannot possibly keep it open. The dark singularity could represent a genuine, absolute boundary where spacetime itself comes to an abrupt end, or it might merely expose the precise threshold where general relativity finally ceases to be a reliable guide. Most contemporary researchers naturally anticipate this second, more hopeful possibility. They patiently expect that a yet unrealized theory of quantum gravity will eventually step forward to replace the infinite dread of the singularity with something elegantly finite, even though no fully confirmed theory has yet revealed the exact nature of this elusive replacement. If the singularity indeed dissolves within the embrace of a deeper, more fundamental theory, then black holes might not actually tear or break the fabric of spacetime at all. Instead, they may simply press and warp it into a highly unusual state that can no longer be described by our familiar, smooth geometry. Deep within the hidden interior, there could lie a chaotic quantum realm, a finely textured discrete structure, a gentle phase transition, or perhaps an entirely new form of cosmic connection. In this strange domain, our comfortable, intuitive concept of a specific location may utterly cease to apply, yet without requiring reality itself to come to a tragic end. This subtle distinction matters immensely. A map can easily fail and fade without the underlying land itself failing. A classical theory may predict a harsh singularity, while a future, more refined quantum theory gracefully removes it. If a dusty old map depicts no route beyond a certain mysterious point, the physical road may still wind patiently onward. The map may simply be incomplete, crudely drawn, or based on outdated assumptions that do not hold true in that wild, unexplored region. Our current, cherished picture of spacetime may be precisely such a limited map. This very same profound challenge arises when we cast our gaze backward, peering toward the ancient dawn of our observable universe. The equations of general relativity clearly suggest that the primordial universe was once unimaginably hotter and vastly denser than it is today. Yet, if we follow these classical equations far enough into the deep, echoing past, they inevitably lead us to another insurmountable singularity. This cosmic threshold is commonly known as the Big Bang singularity, but we must be careful not to picture it as a simple, violent explosion erupting at one specific location within a pre-existing empty void. The miraculous early universe involved the dramatic expansion of space itself. Indeed, every vast region we observe today was once nestled intimately close together in a tiny, collective embrace. Eventually, the classical mathematical description drags us to extreme conditions where cosmic density and spacetime curvature become utterly unbounded. An extraordinary event may unfold silently behind a dark horizon, while no direct signal can ever hope to escape. Once again, our finest theory abruptly falls silent, failing to provide a complete, satisfying answer. It cannot tell us whether time itself truly sparked into existence, whether another mysterious state quietly existed before the Great Expansion, or whether the very word before retains any coherent meaning at such a fundamental level. A fully realized theory of quantum gravity might beautifully replace this abrupt beginning with a rhythmic cosmic bounce originating from an earlier, contracting state of existence. It might describe an exotic epoch entirely devoid of ordinary space or linear time. Ultimately, it could show that our singular beginning is merely a crude approximation, born from bravely but mistakenly extending the reach of general relativity far beyond its natural limits. If spacetime itself gradually emerged during the dawn of the early universe, then asking whether it broke or shattered before that creative moment may simply be the wrong question to ask. After all, something cannot break before it has even begun to exist in a recognizable form. Instead, the deeper, underlying system might undergo a profound phase transition that slowly crystallizes and produces our familiar spacetime. This is much like how cooling matter can gradually produce a beautifully rigid solid structure that was entirely absent in its chaotic, hotter state. This exciting possibility completely shifts the focus of our central problem. Keeping these crucial distinctions clear will help us avoid the temptation of turning every unusual, exotic equation into a sensational claim that physical reality has somehow developed a crack. Instead of asking what cataclysmic force breaks spacetime apart, we are led to ask what extreme conditions cause our smooth, geometric description of spacetime to softly fade away. The most likely answer points to an enormous, unimaginable concentration of energy gathered within an extremely minute region. The mysterious Planck scale marks the precise, dramatic boundary where the massive grip of gravity and the subtle whispers of quantum effects can no longer be kept apart. At that extreme scale, our comfortable, ordinary ideas of distance, duration, and fixed position may become completely unreliable. Any bold attempt to inspect an even smaller region inevitably demands a much greater concentration of energy. Yet, focusing that intense energy also dramatically increases its own gravitational influence. Eventually, The very act of measurement may trigger the creation of a tiny horizon, forever hiding the delicate region being examined from our view. This gives spacetime an unusual, almost poetic kind of resistance. While a common physical material resists external forces by physically pushing back against mechanical stress, spacetime may subtly resist our precise, invasive probing by quietly collapsing to form a microscopic black hole. The more energy we desperately pour in to examine an incredibly tiny distance, the more the local geometry itself dramatically warps and changes. For the present moment, we can already offer a quiet, cautious answer to the profound question we began with. While this does not definitively prove that the Planck scale represents a hard, unyielding minimum length, it beautifully demonstrates why our ordinary method of using ever greater energy to observe ever smaller structures simply cannot continue without limit. In this extreme realm, gravity itself inevitably becomes an active participant in the very process of measurement. One cannot help but wonder, could a highly advanced civilization someday muster enough immense energy to deliberately breach that elusive regime? In theory, the fundamental laws of physics do not strictly forbid the concentration of such extraordinarily vast amounts of energy into a single point. In actual practice, however, the extreme conditions required to achieve this are far beyond the reach of any technology currently possessed by humankind. While the energies unleashed by our most advanced modern particle accelerators are truly colossal compared to mundane chemical reactions, they still remain infinitesimally small, lingering far below the threshold of the standard Planck energy. Even if such unimaginable energy could somehow be generated, safely controlling and compressing it would present an entirely different, insurmountable challenge. The experimental apparatus itself would have to endure hostile conditions capable of producing blindingly intense radiation, highly unstable exotic matter, or even a tiny, microscopic event horizon. Thus, the experiment might tragically swallow and conceal its own hard-won results before any readable signal could ever escape to the outside world. There is absolutely no known ordinary force in the universe that can simply snap spacetime as if it were a fragile thread. Thankfully, nature possesses effortless access to far grander, more violent scales than those we can ever hope to recreate within our modest laboratories. The unsearchable depths of black hole interiors and the fiercely hot, infant moments of the early universe are the most probable sanctuaries where quantum spacetime has already played out its mysterious dance. Yet, the tragic beauty of this reality is that these cosmic theaters are either locked away forever behind impenetrable event horizons, or separated from our gaze by the vast, unbridgeable expanse of cosmic history. Tremors of gravitational waves do bring us tantalizingly close to the heart of extreme gravity, but even they fail to reveal any fundamental tear in the fabric of the universe. When two monstrous black holes merge, they release a truly staggering torrent of gravitational energy. Their horizons violently distort, gracefully stretching and ultimately melting into one. In those fleeting moments, the surrounding geometry of spacetime shifts with breathtaking speed, sending ripples cascading across billions of light-years, carrying silent whispers of information about the violent cosmic collision. Throughout all this chaos, the exterior spacetime remains perfectly, elegantly describable. The propagating waves retain a remarkably orderly, regular structure, and the newly formed, quiescent black hole eventually settles back into a calm, highly predictable state. Einstein's general relativity continues to function flawlessly under extreme conditions that would instantly pulverize any ordinary physical object. This remarkable resilience suggests that spacetime can endure far more violent disturbances than the delicate word fabric might ever lead us to believe. To be sure, extreme concentrations of mass and energy can bend and curve it quite dramatically. It can bend, stretch, ripple with waves, and seamlessly reorganize itself around colliding horizons, all without ever revealing a single raw or exposed crack. To be sure, an exceptionally powerful gravitational wave would wreak havoc on any physical matter unlucky enough to be nearby. It could violently stretch an entire planet, tear a massive star apart, or dramatically bend the very trajectory of passing light. Yet, the matter breaks only because its weak internal electromagnetic and nuclear forces ultimately fail. Meanwhile, resilient spacetime continues to carry the wave smoothly, strictly obeying its own immutable laws. The exact same truth holds near the edge of a black hole. Relentless tidal forces can mercilessly pull a falling object apart, because the side closer to the abyss is drawn along a drastically different gravitational path than the side slightly farther away. Bound molecules violently separate, complex structures instantly collapse, and ultimately, even the most fundamental particles are torn away from one another in a silent scream. The physical object is shattered to pieces, yet the underlying geometry of spacetime itself does not necessarily suffer a similar fate. Similarly, a theoretical Big Rip, should the relentless expansion of our universe ever accelerate in that terrifying direction, would also tear cosmic structures to shreds. Majestic galaxies would be isolated, and stable solar systems would be ruthlessly pulled apart. Catastrophic stellar collapse can give birth to mysterious black holes. Even the very atoms of matter itself might eventually fail to remain bound together in the cold dark. Of course, this dark scenario depends entirely on the still mysterious nature of dark energy, and our current scientific evidence does not guarantee that such a tragic, lonely ending will ever occur. Yet, even if it did transpire, the cataclysm would still be mathematically described as an extreme, albeit smooth, evolution of spacetime, rather than a literal fracture or crack tearing through its continuum. There is, however, another profound way to interpret the breaking of spacetime, and it lies within the sacred realm of causality. It is spacetime that dictates the cosmic order, determining precisely which events are permitted to influence one another across the cosmos. Under normal circumstances, light cannot exceed the absolute, local cosmic speed limit set by the laws of relativity. For any observer traveling along ordinary, well-behaved paths through the cosmos, causes must always precede their corresponding effects. Yet, certain exotic mathematical solutions hidden within general relativity contain bizarre, loop-like paths that actually lead back to an earlier event in time. These mesmerizing, theoretical trajectories are known to physicists as closed time-like curves. If such curves could physically exist in our reality, a daring observer might journey along a path that feels locally future-directed, only to miraculously arrive back in their own distant past. Violent cosmic collisions can send powerful, whispering ripples of gravity surging through the vast universe. Such a journey would not literally shatter spacetime into jagged, visible fragments, but it would utterly ruin the beautiful, logical tapestry of cause and effect that governs our lives. A traveler could theoretically interfere with the very conditions that set them upon their journey in the first place, and in doing so, all the familiar, mind-bending paradoxes of time travel would inevitably unfold. Surprisingly, the elegant mathematics of relativity permits the existence of these fragile structures, but only under highly specialized and extreme conditions. Indeed, rotating universes spinning in the vast cosmic dark, highly idealized cylinders of infinite length, mysterious wormholes, and certain complex black hole solutions are mathematically capable of harboring these highly unusual, swirling causal paths. Yet, the real, tangible universe we inhabit might possess elegant mechanisms to prevent such anomalies from ever fully forming. Perhaps the exotic matter required to sustain them is physically impossible to gather, or delicate quantum effects might swiftly destabilize the fragile geometry of these passages. Even the smallest, most infinitesimal disturbances could grow exponentially, collapsing the fragile pathway before it can ever close. Some profound, yet undiscovered law of physics may eternally protect the sacred order of cause and effect. If this fundamental causality were to fail, one might quite reasonably perceive such a disruption as a tragic, broken fracture in the very fabric of spacetime. Our classical descriptions may indeed reach points of absolute singularity where they cease to be complete or useful. The physical structure would continue to exist, but the delicate, linear relationship between past and future would cease to behave in its familiar, orderly fashion. As of today, there remains absolutely no observational evidence that such wild, circular paths truly exist in the quiet reality of nature. Wormholes present us with another evocative image of structural damage. In theory, a wormhole would connect immensely distant regions of the cosmos through a drastically shorter, secret internal route. It is most often described as a cosmic tunnel, or a profound shortcut torn directly through the fabric of spacetime. However, the simplest wormholes mathematically associated with black hole solutions are notoriously unstable, they do not remain open nearly long enough for any traveler to cross. Truly traversable versions would seemingly require highly unusual, exotic energy conditions to survive. While subtle quantum fields can produce limited, fleeting negative energy effects in very specific laboratory settings, we possess no known method for gathering and precisely arranging such ephemeral forces to hold open a vast, human-sized tunnel. And yet, a wormhole would not necessarily represent a true breakage. It might simply be a perfectly valid, alternative shape of spacetime, much like a carefully carved tunnel through a towering mountain is an integral part of the majestic landscape rather than a sudden failure of geography. At unimaginably microscopic scales, the fabric of spacetime may well lose the beautifully smooth character we so comfortably assume in our everyday physics. The truly crucial question remains whether such an exotic structure can ever be intrinsically stable and physically possible in our universe. Spacetime might also fracture in a far more fundamental sense if it is ultimately constructed from tiny, discrete elements. In that quiet, microscopic realm, our familiar, smooth geometry would merely be a convenient macroscale approximation. These fundamental, underlying units might weave intricate networks, loops, causal threads, or some other mysterious tapestry-like structure. Breaking spacetime would simply mean altering those microscopic connections until one vast region is no longer linked to another. The grand, large-scale geometry would cleanly divide, solely because the silent microscopic relationships that once produced it had been utterly removed or drastically rearranged. Some elegant modern models directly connect this spatial geometry with the profound mystery of quantum entanglement. Entanglement, at its heart, describes ghostly correlations between quantum systems that can never be explained by treating them as fully separate or independent entities. In certain theoretical settings, a stronger degree of entanglement directly corresponds to a more tightly connected geometry. If you gently reduce this entanglement, the geometric connection visibly narrows. Remove it completely within the model, and the regions inevitably separate. Yet, absolutely none of these dramatic phenomena is truly like fracturing a physical, solid object. This elegant concept stands as one of our closest theoretical examples of spacetime being gently pulled apart. Notably, it does not involve any violent mechanical force, but rather a quiet, profound rearrangement of the informational structure that underlies all geometry. Of course, there is no known machine capable of performing such a delicate operation on a real region of our vast universe. These models remain highly simplified, and they do not yet show us how one might actually disconnect the local spacetime surrounding an ordinary person, a planet, or a distant star. Yet, they beautifully suggest that the smooth continuity of our world may be quietly produced by delicate quantum relationships rather than guaranteed at the deepest level of reality. If this radical view is correct, then physical force becomes merely a secondary, emergent concept. After all, force only truly makes sense once space, time, motion, and energy are already established. Therefore, the subtle process that dissolves spacetime connectivity may ultimately need to be described without relying on our everyday intuitive ideas of pushing or pulling. A remarkably similar concept appears if we imagine spacetime as merely one temporary phase of a much deeper underlying system. In our everyday world, a physical material can smoothly transition from a solid to a liquid when its temperature crosses a certain threshold. The far more useful and profound question is what spacetime is capable of enduring before our familiar, elegant descriptions utterly fail. The rigid solid structure vanishes entirely, yet the fundamental molecules remain untouched. In much the same way, spacetime itself might undergo a dramatic phase transition under truly extreme conditions. The familiar tapestry of smooth distance and flowing duration could utterly disappear, even as the more fundamental quantum degrees of freedom continue to exist beneath the surface. From our limited perspective inside this smooth, peaceful phase, such a transition would inevitably look like a catastrophic breakdown. Yet, from a deeper, more fundamental viewpoint, it would merely be a completely ordinary natural change of state. The hot, nascent early universe may well have experienced such a profound cosmic change. The mysterious, hidden interiors of black holes may contain another. If so, spacetime does not break into empty nothingness. It becomes, instead, a profound state where classical geometry is no longer the correct or adequate description. This shift in perspective moves us away from the crude image of an aggressive cosmic hammer, guiding us gently toward the actual beautiful physics of the cosmos. This subtle shift in our understanding leads us toward a deeply useful answer. Space-time can certainly be pushed far beyond the extreme conditions where our current classical theories can hope to function. The enigmatic depths of black holes and the violent crucible of the early universe show us exactly that. General relativity confidently predicts singularities, and those very singularities quietly mark the boundaries of our incomplete description. We do not truly know whether the fabric of space-time itself fails entirely at those mysterious points. There has never been an observed event in which a literal crack in space-time opens to expose some forbidden outside region. There is no scientific measurement of separate, disconnected pieces of space drifting silently apart. No physical experiment has ever found a maximum structural load beyond which the geometry of the cosmos abruptly snaps. The dramatic phrase breaking spacetime is therefore best treated as a poetic shorthand for a group of vastly different possibilities. One compelling possibility is extreme curvature. We need to deeply understand what bending truly means in a formless void, how curvature can be measured without falsely treating spacetime as a physical substance, why mass and energy so profoundly alter geometry. That occurs intensely around black holes, but mere curvature alone is not a true breaking of the cosmic fabric. Another possibility is the quiet formation of an event horizon. Horizons effectively trap information, yet the underlying geometry at the boundary can remain perfectly smooth and continuous. A third possibility is singularity formation. While classical relativity predicts it, the elusive laws of quantum gravity may ultimately erase the singularity altogether. A fourth is the bewildering loss of causal order. Pure mathematics gracefully allows such examples, but nature may strictly forbid them in reality. A fifth possibility is the destruction of the microscopic, delicate connections from which the tapestry of spacetime itself emerges. This fascinating phenomenon appears in theoretical models, but it has not yet been experimentally demonstrated. A sixth possibility is a phase transition into a completely non-geometric state. And precisely how much distortion can occur before horizons, singularities, or elusive quantum effects enter the grand picture. This is entirely possible within several sophisticated approaches to quantum gravity, though no single model has been definitively confirmed. These various possibilities share one profound feature. None can be adequately described by a simple, singular value of force. The sheer amount of force applied is simply not enough to determine the ultimate result. The precise location, distribution, concentration, motion, pressure, and the delicate quantum state of the energy all matter immensely. A huge, vast amount of mass spread across an entire galaxy does not form a single black hole. Yet a much smaller amount tightly compressed within a sufficiently small region easily can. A powerful, cataclysmic collision may send ripples of gravitational waves outward without ever creating an exposed structural failure. A dense, collapsing stellar core may quietly form an event horizon. An even smaller, highly concentrated region may inevitably require the intervention of quantum gravity. So, by all means, keep the comforting image of the soft cushion if it helps your imagination, but do not trust it too completely. The ultimate outcome depends entirely on how the energy is intricately arranged, and not only on how much of it exists in the universe. If someone demanded one single, practical answer, the closest useful statement we could make would be this. Spacetime is expected to stop behaving as a smooth, classical geometry when energy becomes incredibly concentrated near the microscopic Planck scale. That is not a measured physical breaking point, nor is it a simple force rating. It is merely the threshold range where our current theories can no longer provide a complete, separate description of gravity and quantum physics. The true underlying threshold may differ substantially. A fully correct theory could show that the geometry of space survives in some modified, elegant form. It could reveal a fundamental minimum length, a strict maximum curvature, or a smooth transition that prevents mathematical infinities from ever occurring. It may even show that singularities are physically impossible. Indeed, there are theories in which curvature simply cannot grow without limit. Spacetime is not a simple rubber sheet and, Delicate quantum effects create a natural maximum and cause a dramatic cosmic bounce. In those elegant models, nature avoids breaking spacetime altogether by subtly changing the rules before the classical endpoint is ever reached. Other theories suggest that the dark interior of a black hole contains no smooth, empty region in the familiar sense. Instead, a complex quantum state fully fills the space where the classical interior would have been expected. The apparent singularity vanishes entirely because the original, simple geometric picture was never exact to begin with. Still, other theories suggest that the rich information describing a physical region is stored holographic-like on its outer boundary. The interior geometry then beautifully emerges from that encoded information. Breaking this geometry would therefore require fundamentally altering the quantum description rather than merely applying a larger mechanical load. These grand ideas are not easily interchangeable. They make profoundly different claims and may eventually lead us to entirely different observations. The grand, silent universe is certainly not resting upon some cosmic table beneath it. Future, precise measurements of black holes, sweeping gravitational waves, and the early cosmic radiation, and the elusive behavior of fundamental particles may eventually eliminate many of these competing hypotheses. In the coming years, more sensitive and sophisticated gravitational wave detectors could reveal infinitesimally small departures from the elegant predictions of general relativity. These advanced instruments will test whether colliding black holes ring down exactly as Einstein's equations expect them to do. They could search with exquisite precision for additional, subtle wave patterns, unusual cosmic echoes, or some tangible evidence that event horizons possess an unexpected, exotic structure. At the same time, careful observations of the infant universe may finally show the faint, ancient traces of quantum gravity. Delicate patterns imprinted in the ancient cosmic microwave background radiation could reveal the violent, high-energy processes that occurred when the universe was unimaginably young. Even the vast cosmic web and the distribution of galaxies may preserve invaluable information about those earliest quantum fluctuations. The elusive phenomenon of black hole evaporation would be especially valuable to observe, but astronomical black holes are far too massive and evaporate far too slowly for us to witness directly in our fleeting lifetimes. If primordial, very small black holes exist, their final bursts of Hawking radiation might offer vital clues, though no confirmed examples of such tiny remnants have ever been found in the cold expanse of space. This familiar comparison is merely a fleeting doorway, not the vast, intricate room itself. Meanwhile, delicate laboratory experiments continue tirelessly testing whether gravity behaves normally at incredibly short distances. These precision measurements search relentlessly for hidden, additional dimensions, undiscovered fundamental particles, or tiny violations of long-standing cosmic symmetries. Yet, so far, the grand fabric of spacetime behaves with an impressive and stubborn consistency. That seamless consistency is far too easy to overlook. Albert Einstein formulated general relativity more than a century ago, yet this singular theory still successfully predicts precise satellite navigation corrections, the graceful bending of starlight, the complex motion of black holes, and the faint gravitational wave signals arriving from cataclysmic, distant cosmic mergers. The theory is admittedly incomplete at infinitesimal quantum scales, but it remains remarkably and beautifully accurate everywhere it has been directly put to the test. The definitive answer to our profound question is therefore somewhat less dramatic than the title first suggests, but it is infinitely more interesting. We do not yet know how to break the resilient fabric of spacetime with mere physical force, but we do know how nature gracefully bends it. To journey closer toward a true answer, we must first look deeply at what physicists actually mean when they whisper that spacetime bends, because only then can we gracefully decide whether such bending can ever truly become a breaking. We understand how massive stars create extreme, plunging curvature. We know how inescapable horizons form, and we understand how violent mergers send rippling waves through the smooth geometry of the cosmos. Crucially, we also know precisely where classical relativity begins to falter and produce incomplete, fragile answers. The likely breaking point is not a cataclysmic explosion that tears the physical universe wide open. Instead, it is a subtle, profound transition where the very notions of space and time stop being the right concepts to describe reality. Beyond that quiet transition, there may still exist a rich physical system. It may harbor dense quantum information, discrete connections, extended multidimensional objects, or elegant structures that have not yet been discovered by human minds. What ultimately disappears is the smooth, continuous stage on which ordinary, everyday events seem to happen. This is precisely why our inquiry remains so profoundly valuable. It gently leads us from a simple, familiar image of a torn fabric to the deepest, most beautiful problem in modern theoretical physics. That profound question sounds, at least on the surface, as though it ought to yield a wonderfully simple answer. What is the grand tapestry of spacetime actually made from, if indeed it is made of anything at all? Why does it behave so smoothly and continuously on our scale? How does it store its vast wealth of cosmic information? And what truly happens when the familiar force of gravity reaches the elusive quantum scale? Until those fundamental questions are finally answered, we cannot confidently declare that spacetime is unbreakable. Yet, we also cannot say with certainty that black holes have already broken it. The safest, most honest conclusion we can draw is that spacetime appears to be extremely difficult to damage. It effortlessly survives the profound bending by massive stars, the violent shaking caused by stellar mergers, and the relentless stretching of cosmic expansion. It faithfully carries gravitational waves across the vastness of the universe. It allows dark horizons to form without producing any visible seams or tears in reality. If spacetime indeed bends, then surely it must flex in the very same intuitive way as a supple sheet, a resilient branch, or the soft cushion we fondly mentioned just a moment ago. Wherever it may eventually fail, it quietly hides the evidence behind an impenetrable event horizon, or cleverly places it at microscopic scales we cannot directly reach. That may feel slightly unfair to those who seek the truth. The universe playfully provides the question, designs the grand experiments, and then stores the ultimate results in remote locations with no possible return service. Even so, precious evidence continues to arrive from the dark. Every successful gravitational wave detection tests the dynamic nature of our spacetime. Every breathtaking image of matter swirling near a black hole tests the limits of strong gravity. Every precise atomic clock comparison patiently confirms that time itself responds to the underlying geometry of the universe. Each new observation gently narrows the infinite possibilities. Perhaps some future, revolutionary theory will show that spacetime cannot break simply because it is not a fundamental entity. Perhaps it will reveal a natural maximum curvature that gracefully prevents the formation of physical singularities. Place something heavy upon it, watch it gently sag under the weight, and there you have it, gravity neatly explained. Or perhaps it will show that geometry itself can disconnect under extreme, exotic conditions that no advanced civilization could ever hope to create. Perhaps, in the grand sweep of intellectual history, the very term spacetime will eventually be replaced by some profoundly deeper, more fundamental concept, a fertile ground from which both our notions of space and time beautifully emerge. Tonight, however, the answer can afford to remain careful, wrapped in patient contemplation. No known force in the cosmos has ever been proven to truly tear this resilient fabric. To be sure, extreme and unimaginable energies can warp it, stretch it, violently shake it, trap fleeting light within its deep wells, and inevitably push our current fragile theories far beyond their comfortable limits. Yet, whether reality itself ultimately breaks apart at those extreme boundaries remains shrouded in the unknown. And so, that brings us gently back to the very place where we first began. You are still resting safely in your own small, cozy region of curved spacetime, held tenderly near the Earth by gravity's invisible embrace, quietly moving with the planet around the sun, and journeying with the sun through the vast, silent galaxy, all while the familiar clocks around you continue measuring their steady, local path through time. Nothing in this quiet room feels stretched or unstable. This is the comforting picture many of us first encounter in our youth, and it remains remarkably useful, so long as we quietly remind ourselves that it is, after all, only a picture. The surrounding curvature is remarkably gentle, and the distances between objects remain comforting and dependable. Soft light easily crosses the room without ever encountering a dark, inescapable horizon. Your warm cup of tea, should you have made any to keep you company, is quietly cooling in the usual, predictable direction of thermodynamic time. If this vast journey through dying stars, swallowing black holes, elusive gravitational waves, and the unimaginably small scales of quantum physics has given you something truly useful or comforting to think about, you can choose to leave a warm like and subscribe to Physics with William. Doing so helps this quiet, contemplative collection of questions reach other curious listeners who may also enjoy gently considering the possible, magnificent failure of reality shortly before drifting off to sleep. Wherever you are listening from tonight, and whatever hour your nearest clock is currently showing, Spacetime is steadily carrying you forward without any obvious sign of strain or fatigue. It has, after all, resiliently survived violently exploding stars, colliding giant black holes, and the relentless, ongoing expansion of the universe for billions of years. Whether it can ever truly break remains one of those beautiful, unanswered questions still waiting patiently just beyond the furthest edge of what our physics can currently explain. The real, underlying meaning of curved spacetime is far more precise, infinitely more practical, and, in some ways, beautifully stranger. Let us begin with something gently familiar. Imagine yourself walking thoughtfully across a vast, flat field. If you choose a single direction and continue resolutely in a straight line, you naturally expect your quiet path to remain perfectly straight. Two people starting side by side, walking in exactly the same direction, should always stay precisely the same distance apart, assuming, of course, that neither of them is suddenly distracted by a particularly confident, wandering goose. This is precisely how flat, predictable geometry behaves. The rules are elegant and simple, matching perfectly the familiar sort of geometry we were once taught in school. Straight lines remain stubbornly straight. Parallel paths remain eternally parallel. The shortest, most honest route between two nearby points is always the direct one. Now, imagine embarking on the very same journey across the curved surface of our Earth. The ground may feel reassuringly flat beneath your feet, but the planet as a whole is curved. Two lone travelers can begin at completely different places along the warm equator, both walking directly and faithfully north, and eventually they will meet near the icy North Pole. Neither traveler ever turned toward the other. Each merely followed the straightest, most natural route available on that gently curved surface. Their paths inevitably came together simply because the ancient surface beneath them was not flat. That simple example beautifully shows what curvature can do, without ever requiring a visible, dramatic bend from the perspective of those upon it. A tiny, patient insect walking along the surface of a large ball might never possess the ability to see the ball from the outside, yet it could still discover the underlying curvature by carefully making local measurements. It could painstakingly draw large triangles upon the surface and notice that the sum of the angles does not behave at all as they would on a flat, lifeless page. It could send two of its companions along paths that begin perfectly parallel, only to watch those paths gradually converge in the distance. The clever creature would not need to step into some mysterious higher dimension to admire the ball from far above. The geometry could be completely understood from deep within. In truth, the curvature of spacetime works in a remarkably related way. We do not need to stretch our minds to imagine our universe bending into some larger, mystical external space. Instead, we simply observe how silent objects move, how starlight travels, how steady clocks run, and how spatial distances behave. When those subtle relationships differ from what a cold, flat spacetime would predict, we say that the underlying geometry is curved. The single word spacetime elegantly joins two profound ideas that once seemed entirely separate. Space tells us exactly where an event happens, while time tells us precisely when it unfolds. In the quiet routine of ordinary life, separating the two feels entirely natural. You might casually say a warm meeting is in the kitchen and begins at 8 o'clock in the evening. One simple part of the description gives the cozy place, and the other gives the precise time. Einstein's relativity shows us that these separate parts belong to a single, beautifully unified structure. Different observers, moving at different speeds, can disagree about physical distances and fleeting durations, but they will always agree on the deeper, unchanging space-time relationship between events. An event, in the language of physics, is simply something that transpires at a particular, unique place and time. A light switch is clicked on. A distant, brilliant star explodes in the dark. A silver spoonful slips and falls from the kitchen table after being placed slightly too close to the precarious edge. Each event possesses its own quiet location and fleeting moment, and spacetime is the grand, harmonious arrangement in which all such cosmic events are intimately related. When spacetime is perfectly flat and no outside forces interfere, an object moves gracefully along the most direct possible route through this combined, elegant structure. That route is not merely a simple, cold line through empty space. It is a beautiful woven path through space and time, traveling together as one. Physicists call such an intricate path a world line, though the actual concept feels somewhat less dramatic than its grand, evocative name suggests. Your own world line is simply the continuous, silent sequence of events that quietly trace your motion through the vast universe. Even sitting perfectly still in a quiet chair still counts as motion through this unified spacetime, because time relentlessly continues to pass, even if the comfortable chair itself is doing very little to actively improve your situation. The subtle curvature of spacetime changes the paths available to everything. A majestic planet orbiting a distant star is not being forcibly pulled along by some invisible, hidden cable. Instead, it is merely following its most natural, effortless route through the curved spacetime gracefully bent by the presence of that star. To our eyes, the orbit looks like a curved path through empty space, but within the deeper reality of spacetime, it is simply the result of moving as freely and unhindered as possible through a grand geometry that is fundamentally not flat. This profound shift is one of the most intellectually important changes introduced to our understanding by the theory of general relativity. Gravity gently stops being treated as a mere ordinary force acting across cold, empty space. Instead, matter and energy intimately influence the local geometry of spacetime, and that very geometry, in turn, beautifully guides the motion of both matter and light. The famously familiar statement captures this perfectly. Matter tells spacetime how to curve, while curved spacetime tells matter how to move. It remains a highly convenient and elegant summary, though the complete physics underlying it also includes pressure, the dynamic flow of energy, and other subtle physical properties as well as mass. Consider, for a moment, the steady motion of our Earth moving around the Sun. In an older, more traditional picture, the Sun constantly pulls the Earth inward while the Earth moves sideways, mechanically producing a stable orbit. While this classic picture works remarkably well for many everyday calculations, general relativity provides a far deeper, more poetic description. The massive Sun gently alters the geometry of the space around it, and the Earth simply follows its natural path through that invisible, curved geometry. If the Sun could suddenly and magically vanish, which it certainly cannot do without causing several rather serious scheduling problems for our planet, the Earth would not respond instantly to this sudden absence. For changes in the fabric of gravity travel outward at the finite speed of light. The altered geometry would adjust progressively outward, and only after that shifting ripple finally reached Earth would our planet drift away from its former orbit. This very same geometry affects even light, even though a beam of light possesses no rest mass at all. This was one of the most striking and beautiful predictions of general relativity. Light passing near a massive cosmic object diligently follows the straightest path available to it, yet the very spacetime through which it travels is inherently curved. To a distant observer, this light appears to bend. Astronomers frequently observe this mesmerizing effect when a massive galaxy or a dense cluster lies directly between Earth and a much more distant stellar object. This intervening foreground mass can bend the traveling light from the background source, producing ghostly stretched arcs, repeated mirror images, or perfect, glowing rings of light. This phenomenon is known as gravitational lensing. It allows scientists to detect elusive dark matter that does not shine, accurately estimate the immense mass of galaxy clusters, and study cosmic objects far too distant to see clearly without nature generously providing an enormous, if rather inconveniently placed, cosmic telescope. Yet, none of this requires spacetime to behave like a tangible physical substance. The comforting word fabric is commonly used because it gives our minds a visual metaphor to work with, but real spacetime has no known physical threads. It does not flap in a cosmic wind, crease with age, or ever need ironing. Curvature is, in truth, a precise statement about measurements and spatial relationships. It simply tells us how neighboring paths separate or converge, how distant clocks compare, and how the silent direction of motion changes from one place to another. Timekeeping clocks provide one of the clearest, most elegant signs of this reality. A clock nestled closer to a massive object runs measurably more slowly relative to a matching clock positioned much farther away. This does not mean the lower clock is somehow damaged or struggling under some heavy physical pressure. Rather, every local process at that lower position follows the exact same slowed, steady rate when compared with the distant, faster clock. Gentle chemical reactions, swift electronic signals, gradual biological aging, and the physical motion of the clock mechanism itself all perfectly agree. A person standing quietly beside that lower clock notices absolutely nothing unusual in their immediate surroundings. Their heartbeat feels perfectly normal, and their thoughts proceed with their usual familiar rhythm. It is only when signals are directly compared between these differing gravitational conditions that the subtle discrepancy finally appears. This quiet, remarkable effect exists right here on Earth. A delicate clock resting at sea level runs just a fraction more slowly than its counterpart stationed high upon a mountain peak, simply because it resides deeper within the Earth's invisible gravitational embrace. Though this fleeting discrepancy remains extraordinarily tiny, modern atomic clocks possess a wondrous sensitivity, capable of measuring the minute shifts brought about by even the most surprisingly modest differences in elevation. Gently lift a sufficiently precise timepiece upward, and it gradually gains time, pulling ahead of the sibling clock left patiently below. To many, this phenomenon might sound like a mere laboratory curiosity, yet it plays a profoundly vital role in our everyday modern technology. The silent satellites we send into the heavens for navigation must carry exquisitely accurate clocks. Their swift, ceaseless motion and their loftier positions far above in the Earth's gravitational field both work to alter their ticking rates relative to the stationary clocks resting on the ground. Consequently, the entire positioning system must continuously and meticulously correct for these subtle relativistic effects. Without these vital adjustments, navigational errors would compound with alarming speed, and a simple device attempting to guide you to a nearby address would soon become stubbornly, increasingly confident about a distant destination you never once intended to visit. This cosmic curvature also reveals its presence through the gentle pulling of tidal effects. Imagine, for a moment, that two small objects are released side by side, high above the turning Earth. Both begin their downward journey, and because their falling paths converge toward the Earth's deep center, they drift ever so slightly closer together as they descend through the quiet air. Locally, each object experiences the weightless grace of free fall. Neither feels any physical force nudging it sideways, and yet, the silent distance between their descending paths inevitably narrows. This quiet, relative change is the unmistakable signature of curved spacetime itself. Now, let us imagine a single, elongated object falling toward a highly compact, massive body. The leading end, positioned closer to the mass, experiences a noticeably different gravitational pull than the trailing end suspended further away. Under this stress, the object is gradually stretched along its length and squeezed inward across its width. Near the formidable threshold of a black hole, these tidal forces escalate until they become absolutely enormous. Such violent distortions do not arise merely because gravity is immensely strong at a single point. Rather, they exist because the strength of gravity changes dramatically from one part of the object to another. This subtle distinction helps us separate the concept of strong gravity from that of intense geometric curvature. It is entirely possible to find oneself in a region of space where the gravitational pull is incredibly large, yet nearly uniform across the entire span of your body. In such a state, you would feel almost no painful tidal stress while drifting in free fall. Conversely, it is also possible for the local curvature to be so severe that adjacent paths rapidly tear apart or violently converge. Ultimately, what determines structural damage is often not the sheer magnitude of the overall pull, but rather how steeply and quickly that pull changes across a given distance. The mysterious event horizon of a supermassive black hole illustrates this cosmic truth beautifully. Viewed from a safe distance, this horizon marks the absolute, haunting boundary beyond which no signals can ever hope to return. Yet, For a lonely traveler falling into a truly colossal black hole, crossing that fateful boundary might involve absolutely no sudden or dramatic local event. There is no solid barrier to strike, no brilliant flash of light, and no warning sign declaring that all exits are now forever closed. The traveler simply continues to fall peacefully inward. The profound transition they undergo is global in nature rather than locally disruptive. Once they have crossed, however, every possible future-directed path through spacetime bends inexorably and deeper inward. Meanwhile, a distant observer watching from afar would describe this descent in a starkly different manner. The delicate light signals sent by the falling traveler arrive increasingly delayed, stretched thin and growing steadily redder. To the observer, the traveler appears to freeze in slow motion near the edge of the horizon, gradually fading into a ghostly silence. The traveler, however, experiences none of this frozen eternity, crossing the horizon in a perfectly finite, fleeting span of their own personal time. Both of these seemingly contradictory descriptions are entirely consistent because they merely refer to different ways of measuring time and comparing physical events within a deeply curved spacetime. This is precisely why our ordinary, everyday language struggles to capture these truths. We are inherently accustomed to a single, shared cosmic clock and one seemingly obvious description of motion. Yet, a curved spacetime does not always offer us the luxury of either. Time itself can flow at wildly different rates in different regions of the cosmos. Different observers can employ vastly different coordinate systems while still agreeing perfectly on the underlying physical reality of events. A chosen coordinate system can behave terribly and break down mathematically, even when the underlying geometry of spacetime is perfectly smooth and regular. The event horizon was once deeply confused with a physical singularity partly for this very reason. When viewed through certain mathematical coordinates, the equations appear to misbehave and fail at the horizon's edge. However, choosing more elegant coordinates easily removes the illusion of this mathematical breakdown, beautifully demonstrating that the horizon itself is not a place where the fabric of spacetime must necessarily tear or break. Yet, the enigmatic singularity at the very center is profoundly different. There, the undeniable signs of mathematical trouble cannot be simply brushed away or resolved merely by changing the arbitrary labels we use to describe physical events. To truly understand why this dramatic bending of spacetime does not require a sharp edge, we can return to the familiar surface of our own Earth. This vast surface is curved, yet a weary traveler can keep moving indefinitely without ever reaching a sudden crack where geometry abruptly stops. Curvature, in its purest essence, can be beautifully smooth and continuous. Spacetime draped around the brilliant sun is curved in this very same general sense. It does not possess a visible, jagged seam where the curved region suddenly begins. Instead, the gravitational effect weakens gradually and gracefully with distance. Remarkably, even seemingly empty regions of the cosmos can contain this silent, invisible curvature. A phantom gravitational wave can journey through a desolate region with absolutely no nearby matter, subtly altering physical distances as it silently passes. Two freely floating objects in its path may move slightly closer and then farther apart in a gentle, repeating pattern. This wave is not physical matter traveling through space in the usual way. It is a propagating, dynamic change in the geometry of spacetime itself. Calling this cosmic phenomenon a ripple is undeniably helpful for our imagination, but once again the comparison has its strict limits. Water waves must move through water. Sound waves must travel through air or another physical material. Gravitational waves, however, do not require any separate, underlying substance to carry them. They are intrinsic, shifting changes in the very fabric of spacetime geometry, rippling outward from accelerating masses. When two colossal black holes dance and orbit each other, their rapidly changing gravitational field produces these elusive waves. These waves steadily carry orbital energy away, inevitably causing their mutual orbit to shrink. The black holes spiral faster, the celestial signal grows ever stronger, and eventually, the massive objects merge into one. Afterward, the newly formed black hole gradually settles into a stable, quiet shape by sending out a final, fading pattern of waves. Highly sensitive detectors measure these disturbances by carefully comparing lengths in different directions. As a cosmic wave passes through, one spatial separation can slightly increase while another perpendicular to it decreases, and then the delicate pattern reverses. By the time these ripples finally reach Earth, the physical changes are extraordinarily small. Detecting them requires deeply isolated instruments, a meticulous control of environmental noise, and a profound willingness to take these microscopic movements very seriously. A passing gravitational wave does not usually damage anything in its path, for its residual effect is far too weak by the time it washes over Earth. Closer to the violent source, the geometric distortion can be much stronger, but the local geometry still behaves perfectly according to Einstein's theory. It changes rapidly and dramatically without tearing. This profound resilience suggests that bending, stretching, and vibrating are normal, inherent abilities of spacetime rather than alarming signs of structural failure. How far can that cosmic bending actually go? General relativity does not impose a simple, rigid maximum curvature in the way a sturdy metal beam has a rated structural load. The elegant equations allow physical curvature to grow indefinitely as matter and energy become more densely concentrated. Under certain extreme conditions, gravitational collapse continues relentlessly toward a singularity. That is the mysterious threshold where our theoretical predictions become incomplete, and where many physicists expect quantum effects to finally become essential. Before reaching that ultimate limit, however, curved spacetime can produce many breathtakingly extreme results while remaining perfectly describable by our mathematics. Can slow down ticking clocks. Can trap traveling light. It can warp and change the apparent shape of distant, glowing galaxies. It can force planetary orbits to rotate in strange ways never predicted by older Newtonian gravity. It can carry energetic waves across the vast emptiness of the universe. Furthermore, it can easily allow two different observers to disagree about spatial distances and temporal durations, all while maintaining a beautifully consistent, unbroken account of cause and effect. One famous, historic test of this theory involved the wandering orbit of Mercury. The point of Mercury's closest approach to the massive Sun slowly shifts over time. Most of that subtle motion can be easily explained through the gravitational influence of neighboring planets, but a small, stubborn remainder resisted a complete explanation using traditional Newtonian gravity. General relativity brilliantly accounted for this extra shift through the subtle curvature of spacetime near the Sun. It was not a huge effect, but it was exactly the sort of minute, elegant detail that reveals when a deeper, more profound theory is truly needed. Another early, triumphant test came from carefully observing distant starlight passing near the Sun. During a total solar eclipse, stars close to the Sun's position could be seen and, compared with their usual serene locations in the night sky, their delicate starlight appeared subtly displaced, gently bent from its course because it had journeyed through the deeply curved fabric of spacetime hugging the massive Sun. In later years, measurements grew far more precise and sophisticated, yet the fundamental, elegant principle remained beautifully unchanged. These luminous examples reveal that cosmic curvature is not merely a theoretical abstraction reserved for distant black holes or the fiery dawn of the universe. Instead, it is quietly present everywhere, around the Earth, the Sun, your own physical body, and indeed every single object that harbors energy. The subtle curvature whispered into existence by a human body is far too minuscule to ever notice without impossibly sensitive instruments, yet it is never exactly zero. Gently moving a simple cup from one side of a wooden table to the other slightly shifts the distribution of energy in the room, and therefore, in its own quiet way, slightly alters the very geometry of the cosmos. The vast universe copes with these tiny movements without a whisper of complaint. Furthermore, internal pressure also contributes its own share to this cosmic curvature. In our mundane daily lives, we intuitively think of gravity as a pull arising solely from physical mass. Yet general relativity embraces a far broader, more generous source. Energy, momentum, pressure, and internal stress all play their vital, interconnected roles. Deep inside the heart of a dense, collapsing star, this internal pressure can become absolutely enormous, and its contribution to gravity can no longer be ignored. This inevitably creates a strange, deeply unusual situation. While outward pressure desperately helps support a dying star against a catastrophic gravitational collapse, the very energy associated with that intense pressure ironically adds to the inward gravitational pull. For ordinary, shining stars, stable balances are beautifully possible, as radiating heat and fierce internal pressure successfully resist the relentless grasp of gravity. In the exotic realms of white dwarfs and dense neutron stars, the strange quantum properties of matter provide additional, resilient forms of support. Yet even here, immutable limits exist. If a collapsed stellar core is simply too massive, no known force or pressure can hope to hold it up. The local geometry continues to fold and warp relentlessly, and a dark black hole inevitably forms. This dramatic process is not merely a heavy object pressing downward onto a flat cosmic sheet. Rather, the collapse implodes spectacularly in all directions at once. Space and time surrounding the collapsing matter warp and change together in a seamless, cosmic dance. The future paths available to any wandering particles tilt inexorably inward, steeper and steeper, until escape is no longer possible. The simple phrase tilting inward is merely another visual aid, yet it elegantly captures a profound, essential truth. Once inside the dark event horizon, moving toward a smaller distance from the singular center becomes just as utterly unavoidable as moving toward tomorrow is for us living out here in the free universe. That is a far stronger, more absolute statement than merely saying the immense gravitational pull is exceptionally difficult to resist. Even a phenomenally powerful rocket cannot simply point its nose outward and escape from the dark clutches within the horizon. The fundamental issue is not a mere lack of engine power. Rather, there simply exists no future-directed route leading back to the outside world. Trying to escape from within would be like desperately trying to travel back to yesterday by driving resolutely north. More speed cannot solve a fundamental problem created by the very geometry of available directions. This profound realization helps us understand the crucial difference between merely bending the fabric of spacetime and completely breaking it. Bending gently changes the intricate relationships among physical paths, ticking clocks, and unfolding cosmic events. It can produce extreme conditions that look utterly extraordinary from our ordinary human viewpoint, yet the underlying geometry may remain perfectly smooth and continuous. Breaking, however, would require something far more radical. It might mean that the geometry abruptly ends, becomes entirely undefined, changes its basic character altogether, or can no longer support any predictable, coherent connection between the past and the future. A black hole's silent horizon does not automatically meet that dramatic definition. A passing gravitational wave does not meet it. Extreme time dilation does not meet it, and neither does the graceful bending of light around a distant galaxy. These are all beautiful examples of spacetime working precisely as the laws of general relativity dictate it should. The mysterious singularity predicted to lie deep inside a black hole is a far more serious candidate for such a rupture. So, too, is the ultradense, unimaginably hot early stage of the newborn universe, when densities and temperatures were so extreme that our familiar classical geometry may no longer hold true. In those extreme, primordial settings, our elegant picture of smooth spacetime could be fundamentally incomplete. The profound difficulty is that we cannot truly answer what replaces it until we finally understand the nature of gravity at its deepest quantum level. Indeed, there may be no literal physical object called spacetime lurking underneath the beautiful mathematics. Geometry itself could be fundamental, or perhaps it quietly emerges from something even deeper and more mysterious. If it indeed emerges, cosmic curvature may be the grand, large-scale behavior of those intricate, microscopic relationships that we have not yet fully identified. The bending of spacetime would then simply be a subtle shift in how those underlying, fundamental parts are arranged. While a complete breaking might signify a profound transition into a strange, unimaginable state where our familiar ideas of distance and duration no longer hold any meaning. For now, our safest, most grounded understanding remains elegantly direct and practical. Spacetime bends whenever the measured relationships among motion, distance, and time begin to differ from the pristine uniformity of flat spacetime, purely because matter and energy are present. Under this quiet influence, objects naturally follow altered, winding paths, Light subtly bends and changes its direction. Highly sensitive clocks disagree after traveling through different, uneven gravitational conditions. Nearby falling paths gently converge or slowly drift apart. These profound effects are not mere decorative metaphors. They are real, precisely measured features of our physical universe. The classic image of a stretching rubber sheet can help us begin to visualize this, but it unfortunately leaves out the crucial element of time, relies awkwardly on Earth's own gravity to demonstrate gravity itself, and misleadingly suggests an outside space that the real, elegant theory does not actually require. A far better, more honest picture is a vast, imaginary network of synchronized clocks and freely moving objects spread throughout a cosmic region. Observe closely how these clocks compare with one another. Watch how the objects move in relation to one another. Send delicate beams of light traveling between them. If their intricate spatial relationships cannot be fully described by flat Euclidean geometry, then curvature is undeniably present. Once curvature is deeply understood in that intuitive way, our next question becomes much more focused. What exactly creates enough profound curvature to transition from the gentle, whispering fields around quiet planets into the unimaginably extreme conditions around collapsed, dying stars? The answer begins with gravity, acting as the universe's quiet, invisible sculptor, masterfully shaping paths and clocks everywhere. It works, most of the time, so incredibly gently that we easily mistake its constant artistry for the ordinary, silent background of daily life. Gravity is tirelessly working even when absolutely nothing seems to be happening. It securely holds the vast oceans against the spinning Earth, keeps the faithful moon in its steady orbit, guides the heavy planets around the burning sun, and gently gathers enormous, drifting clouds of gas into bright new stars. It shapes entire galaxies over billions of patient years and subtly influences the path of every single beam of light that crosses the vastness of the universe. Yet, most of the time, it accomplishes all of this with a quiet, breathtaking grace. There is no dramatic sound of space bending, no visible hand physically pulling objects together, and no warning bell to signal when one massive body begins to influence another. Gravity simply, silently changes the invisible routes that both matter and light are permitted to follow. This persistent, serene quietness can easily make gravity seem far less dramatic than it truly is. Electromagnetism brilliantly gives us dazzling lightning, wild sparks, glowing digital screens, and the small but memorably sharp shock of touching a cold metal handle after walking across a dry carpet. The fierce, strong nuclear force helps power the colossal, raging reactions deep inside stars. By contrast, gravity often appears to do little more than keep our feet securely planted on the ground and cause dropped objects to stubbornly choose the least convenient possible landing place. Yet, on the grand scale of massive planets, brilliant stars, whirling galaxies, and the cosmos itself, gravity confidently becomes the master architect. Its immense influence begins with the simple, profound fact that every single form of mass and energy contributes to the curvature of spacetime. A tiny, solitary grain of sand subtly curves spacetime. A quiet person sitting in a chair curves spacetime. The wooden chair contributes its own small part too, and although these individual effects are far too minuscule to demand our daily recognition, they are undeniably real. Yet, when you add enough of this matter together, the collective curvature becomes strong enough to guide celestial moons, bend passing starlight, and slow down ticking clocks by measurable scientific amounts. The shape created by gravity is never fixed in the same permanent way as a static sculpture carved from cold stone. Matter constantly moves, energy dynamically flows, stars fiercely burn, planets orbit, and massive galaxies violently collide. The underlying geometry of the universe continuously shifts and changes in immediate response. Gravity is therefore far less like a finished, silent statue, and much more like an active sculptor who never stops working. It pushes absolutely nothing with physical hands, yet it continuously and elegantly reshapes the possible paths through space and time. Near our own Earth, this shaping effect is gentle enough that Isaac Newton's classic description of gravity still works remarkably well. Physical objects fall with a highly predictable acceleration, and the faithful moon follows its orbit with serene regularity. artificial satellites can be carefully guided around the blue planet. Engineers can construct magnificent bridges, launch soaring rockets, and calculate precise trajectories without ever needing to treat every single practical problem as a deeply complex investigation of curved spacetime. While general relativity silently remains underneath this entire process, its subtle corrections are often so infinitesimally small that they can be safely and comfortably ignored in our daily endeavors. This simplification is immensely useful because describing the complete, intricate geometry of spacetime can be extraordinarily difficult to capture. Nature, in her quiet wisdom, does not insist that we employ her most advanced theories for every ordinary task. Just as you would not require a highly detailed model of molecular chemistry simply to decide whether a cup of water is completely full, so Newtonian gravity is usually more than enough to understand the simple descent of a falling apple, although the humble apple itself might not entirely appreciate being used as a perpetual example in so many physics lectures. The grander, deeper picture becomes absolutely necessary only when gravity grows exceedingly strong, when ultra-precise measurements are vital, or when massive objects move at dizzyingly high speeds. The peculiar, shifting orbit of Mercury inevitably required it. The delicate behavior of timekeeping clocks in modern navigation satellites demands it. And the mysterious, crushing depths of black holes demand it absolutely and completely. In these extreme situations, gravity can no longer be treated merely as a simple, invisible pulling force without losing vital, profound parts of what is truly happening in the cosmos. To truly appreciate how gravity sculpts on a cosmic scale, imagine an unimaginably vast region of space filled only with a thin, whispering haze of primordial gas. This gas is not perfectly, flawlessly smooth. By sheer chance, some quiet areas contain slightly more matter than others. These slightly denser regions naturally exert a gently stronger gravitational influence. Nearby gas slowly drifts toward these gravitational wells, making them even denser and more concentrated. As more and more material steadily gathers, the irresistible pull of their attraction grows stronger. Thus, a tiny, almost imperceptible unevenness can gradually grow into a magnificent, large-scale structure. This elegant, patient process played a defining role in shaping the early formative universe. Cosmic matter slowly collected around these minute, subtle differences in density. Over immense, unfathomable spans of time, those quiet differences slowly developed into the colossal structures that would eventually become majestic galaxies and sprawling galaxy clusters. Gravity gently took a young universe that was once far smoother and systematically drew matter into luminous filaments, cosmic sheets, dense knots, and vast, breathtaking empty regions. The stunning result closely resembles a delicate, glowing web on the largest observable scales of the cosmos. Galaxies are not scattered entirely at random across the dark void. Instead, they gather gracefully along vast, sweeping structures, with dense clusters sitting precisely where several glowing filaments intersect. Between these magnificent structures lie enormous, desolate voids containing far less matter. Gravity patiently created this cosmic pattern over eons, quietly drawing material toward those fortunate regions that already possessed a slight gravitational advantage. The mysterious presence of dark matter played an absolutely major role in this grand cosmic growth. It does not emit, reflect, or absorb light in any conventional way, which makes it hauntingly difficult to observe directly. Its undeniable gravitational influence, however, can be clearly and precisely measured. Galaxies spin and rotate as though they contain far more hidden mass than their visible stars and swirling gas could ever provide. Faint light from incredibly distant objects bends dramatically around massive galaxy clusters, far more strongly than the presence of visible material alone could ever explain. The grand, large-scale structure of our universe also perfectly fits theoretical models in which dark matter provided the invisible, essential gravitational framework around which ordinary matter eventually gathered. In that profound sense, many of the galaxies we see today grew quietly inside these invisible, protective gravitational scaffolding structures. Cold gas fell steadily inward, cooled further, and ignited to form the very first stars. Those brilliant stars gathered into beautiful, rotating systems. More interstellar gas constantly arrived, and smaller, youthful galaxies gradually merged into larger, grander ones. Gravity possessed no conscious plan for this final result. Yet over vast stretches of time, it beautifully produced majestic spirals, smooth elliptical galaxies, dense clusters, and long, elegant streams of stars pulled gently from one passing system by another. Our very own galaxy carries the unmistakable, living evidence of this ongoing cosmic work. The Milky Way boasts a broad, shimmering disk of stars, gas, and cosmic dust, all surrounded by an incomparably larger halo-like region deeply influenced by unseen dark matter. Smaller, neighboring galaxies orbit closely by. Some are being slowly, inexorably disrupted by our presence. Their stars are gradually stretched into long, luminous stellar streams as the Milky Way's immense gravity pulls different parts of them with subtly different strengths. Once again, these gentle yet powerful tidal effects are actively doing the master sculpting. The vulnerable side of a small galaxy closer to the Milky Way feels a noticeably stronger gravitational influence than its far, distant side. Over countless slow orbits, this subtle difference gently but inevitably draws stars away from their home. A galaxy that once proudly held itself together gradually becomes a faint, ghostly trail of stardust spread quietly across the vastness of space. Absolutely nothing struck it in anger. There was no sudden, violent collision. Instead, gravity silently changed its shape, applying slightly different conditions across its vast width over an immensely long period of time. The familiar tides on Earth are merely a closer, gentler version of this very same cosmic idea. Our silver moon pulls a little more strongly on the side of Earth nearest to it, and somewhat less strongly on the far side. This delicate difference directly contributes to the eternal, rhythmic rise and fall of our vast oceans. The distant sun also quietly affects these tides. The final result depends beautifully on the relative positions of the Earth, Moon, and Sun, as well as the unique shape of our coastlines and the mysterious depth of the surrounding seas. It is always tempting to say that the Moon simply pulls the water directly upward, but the full, majestic motion actually involves the entire Earth and its deep oceans responding in unison to a constantly changing gravitational field. This same fundamental principle that gently stretches a moon, restlessly disturbs an ocean, or tears ancient stars from a dying galaxy can become far more severe and violent near highly compact cosmic objects. Yet, long before reaching those terrifying extremes, gravity first gently shapes the very stars themselves. A newborn star begins its journey in a dark, cold cosmic cloud containing quiet gas and drifting dust. This silent cloud may suddenly be disturbed by a nearby stellar explosion, a slow collision with another passing cloud, or the gradual, quiet growth of an already dense region. Once enough primal material gathers, gravity relentlessly draws the cloud inward. As it steadily collapses, the gas becomes significantly denser. Tiny particles collide much more often, and the internal temperature begins to rise. Sometimes, the vast cloud may fragment into several smaller collapsing regions, beautifully creating multiple sister stars rather than just one. Swirling disks of dark material can then form around these young, glowing stars. Within those dusty disks, microscopic grains collide and stick together, eventually building ancient rocks, drifting asteroids, planets, and moons. Absolutely everything in a solar system therefore carries the deep, silent history of this gravitational gathering. The very material that makes up our Earth was once widely spread through a cold, ancient cloud. Gravity patiently helped bring it all together, though the intricate details also involved violent collisions, complex chemistry, intense heat, and the unpredictable behavior of gas and dust. The solid planet beneath your feet is part of a grand structure slowly assembled through countless, quiet interactions over a period of time far longer than any human life can easily picture or comprehend. Deep at the center of a forming star, pressure and temperature continue their relentless rise. Eventually, these conditions become intense enough for the miracle of nuclear fusion to begin. Light atomic nuclei combine into heavier ones, releasing immense amounts of pure energy. That radiant energy moves steadily outward, helping to resist any further inward collapse. A stable star thus lives in a long, exquisite balance between gravity pulling inward and pressure pushing outward. Neither side ever wins completely. If gravity won, the star would instantly collapse into darkness. If outward pressure won, the star would wildly disperse into the void. Instead, these two opposing tendencies maintain a harmonious structure that can remain remarkably steady for millions, billions, or even much longer cosmic periods, depending entirely on the star's unique mass. Our own sun has faithfully maintained this delicate balance for billions of years. Deep within its glowing core, nuclear fusion constantly releases energy. That energy slowly and painfully makes its way outward over thousands of years before finally escaping as warm sunlight. Gravity firmly holds the star together while internal pressure keeps the core from collapsing any further. The gentle sunlight warming Earth today actually began as raw energy produced in a dense region where matter is heavily compressed by the immense weight of everything resting above it. Stars of different masses live vastly different lives simply because gravity dictates the precise conditions within their cores. A low-mass star compresses its quiet center far less severely, burning its fuel with slow, deliberate care. Consequently, it can remain active and glowing for an extremely long period of time. A gasp's high-mass star, however, possesses a much stronger, more demanding gravity. Its core becomes incredibly hot and dense, allowing fusion to proceed at a rapid, furious pace. It shines with brilliant, breathtaking splendor, but uses its precious fuel far too quickly. This creates one of the universe's most poignant reversals. Having more fuel does not always mean living a longer life. A massive star contains far more stellar material than our sun, yet it may survive for only a tiny, fleeting fraction of the sun's majestic lifetime. Its immense gravity relentlessly drives a far more rapid, furious rate of nuclear fusion. Indeed, such a star lives with the extravagant energy habits of a reckless diner who has stumbled upon an apparently unlimited buffet and tragically misunderstood the true meaning of the word unlimited. As these celestial bodies age, gravity continuously and silently shapes their intricate internal structure. When precious hydrogen finally becomes scarce within the deep core, the delicate cosmic balance shifts dramatically. The core contracts tightly and heats to extreme temperatures, while the outermost layers swell outward. A star very much like our own sun will eventually expand into a swollen red giant. Its thin, outer atmosphere will gently spread far beyond its current boundaries, even as the dense center quietly prepares itself for a new, desperate stage of fusion. Eventually, this sun-like star gracefully releases its outer layers, letting them drift away as glowing cosmic shrouds into the cold void of space. The quiet, remaining core is transformed into a dense white dwarf. This singular object contains an astonishingly large amount of mass, tightly compressed into a small, silent volume roughly comparable to that of our Earth. It no longer produces radiant energy through the normal channels of stellar fusion. Instead, it remains stubbornly supported against further gravitational collapse by a subtle quantum effect associated with its tightly packed electrons. This microscopic support does not behave like ordinary gas pressure at all. Rather, it arises beautifully because identical subatomic particles simply cannot occupy the exact same quantum state. Relentlessly compressing this dense matter forces the electrons into increasingly energetic, frantic arrangements. Their collective quantum resistance can successfully support the cooling white dwarf, but only up to a strict, inescapable limit of mass. Here, the formidable power of gravity meets its first truly major obstacle within the strange, invisible quantum behavior of matter. If the quiet white dwarf remains safely below this limiting mass, it can exist peacefully for an unimaginably long time, gradually and silently cooling into the dark. Yet, if one adds too much material, perhaps by greedily drawing gas away from a nearby companion star, this fragile balance will suddenly fail. The catastrophic result may be a blindingly powerful explosion or a swift, further collapse, depending entirely on the surrounding circumstances. Far more massive stars develop even hotter, more turbulent cores, enabling them to fuse progressively heavier elements. They gradually build complex, layered structures resembling celestial onions, with different nuclear processes occurring simultaneously at different depths. Yet, This grand sequence cannot continue forever. The final fusion processes involving iron do not provide the vital outward energy benefit that sustained the star during its earlier stages. Once the heavy, iron-rich core becomes too massive to sustain itself, the dying star suddenly loses its crucial life-supporting source of outward pressure. A catastrophic collapse then proceeds with terrifying swiftness. The iron core contracts violently under the crushing weight of gravity. Subatomic particles are brutally forced into extreme and unnatural conditions, and the outer parts of the star fall helplessly inward. A violent, spectacular rebound and the sudden release of truly enormous amounts of energy can produce a brilliant supernova. For a brief, shining period, this single exploding star may radiate with the breathtaking brightness of an entire galaxy. This cosmic explosion wildly spreads newly formed, precious elements into the deep silence of space. Carbon, oxygen, silicon, iron, and many even heavier elements eventually become integral parts of future dust clouds, newborn stars, wandering planets, and ultimately, living things. Gravity patiently gathers raw matter. Massive stars transform it. Violent explosions distribute it. And gravity gathers it once again. The sturdy calcium in our bones, the iron flowing in our blood, and so many of the common elements around us passed through these ancient stellar processes long before our own solar system ever existed. What mysterious remnant remains after a massive star's dramatic collapse depends almost entirely on the final mass of its ruined core. In some fascinating cases, this remnant becomes an ultra-dense neutron star. Here, relentless gravity has compressed matter far beyond the already staggering density of a white dwarf. Electrons and protons are violently forced into reactions that produce neutrons, leaving a tiny, remaining object that can contain more total mass than our entire sun, packed tightly within a sphere roughly the size of a terrestrial city. Even a remarkably small amount of this neutron star material would possess an utterly astonishing, unimaginable mass under ordinary Earth conditions. While the exact physical comparison depends on the specific object and the precise amount chosen, the central, profound point remains perfectly clear. Matter has been compressed into an extreme state that simply cannot be reproduced in any kitchen, no matter how remarkably ambitious one's collection of culinary appliances might be. The surface gravity of such a neutron star is truly immense. A falling object would reach an absolutely tremendous, lethal speed just before impact. Even the pure light leaving its dark surface loses precious energy as it struggles to climb outward, gradually shifting toward much longer, redder wavelengths. Time itself is warped, so that clocks placed near the surface run perceptibly more slowly relative to distant, unaffected clocks. The star also bends the paths of light, so profoundly that an observer might gaze upon hidden portions of the far surface, normally tucked away in secret around the star's steep curve. Certain neutron stars spin with a dizzying rapidity, projecting intense, focused beams of radiation outward from the regions near their powerful magnetic poles. When these cosmic searchlights sweep across the vast distance to Earth, watchful astronomers detect them as remarkably regular, rhythmic pulses. These mesmerizing objects are known to us as pulsars. Their celestial signals can be extraordinarily stable, transforming the silent remnants of dead stars into some of the most unimaginably precise natural timekeepers in the known universe. Others, however, possess magnetic fields of truly staggering, incomprehensible strength. These formidable magnetars can suddenly unleash ferocious bursts of high-energy radiation into the void. Their solid outer crusts may violently rupture and crack as the intense magnetic field shifts, triggering colossal events eloquently described as starquakes. The delicate fabric of spacetime around them remains deeply warped by the star's immense mass, while the dense material within is severely strained by extreme forces impossible to replicate anywhere else in the cosmos. A neutron star beautifully demonstrates just how far relentless gravity can compress physical matter without inevitably collapsing into a black hole. It is a chaotic cosmic arena where gravity, quantum mechanics, nuclear forces, extreme pressure, and dizzying rotation all fiercely compete for dominance. The exact, mysterious behavior of matter buried deep within its heart remains tantalizingly uncertain. It may harbor exotic forms of subatomic particles or strange phases of matter that can never exist under ordinary terrestrial conditions. Yet, even for these resilient giants, there remains an absolute limit. If the dying core is too massive, even the stubborn resistance of neutrons cannot prevent a final catastrophic collapse. The escape velocity climbs sharply, the surrounding geometry warps to the absolute extreme, and a dark event horizon inevitably forms. Gravity has at last triumphed, fashioning a black hole. The familiar phrase escape speed remains useful from a safe, distant perspective, yet a black hole is far more than simply a massive object exerting an unusually powerful gravitational pull. It fundamentally alters the very causal structure of spacetime itself. Outside the dark boundary of the horizon, pathways leading outward still exist for the traveler. But at the horizon itself, a fateful boundary is drawn, marking the exact threshold where any escape back to the distant, familiar universe becomes forever impossible. Inside this boundary, all future-directed paths are inexorably bent inward, leading only toward smaller distances and the ultimate singularity at the center. A black hole can, remarkably, be described using an astonishingly small handful of observable properties. Its mass determines its size. The spin or rotation dictates its sway. Its electrical charge could theoretically play a role, though in the actual cosmos, astrophysical black holes are expected to carry very little lasting charge, as the surrounding dust and plasma would quickly act to neutralize it. Thus, much of the intricate, complicated history of the massive star that collapsed becomes forever hidden from the gaze of an outside observer. Gravity elegantly simplifies the exterior realm while leaving the dark interior shrouded in deep, profound uncertainty. From the safe vantage of the outside, the behavior of a black hole can be modeled mathematically with breathtaking precision. Swirling matter may orbit the abyss in a glowing accretion disk, where intense friction and magnetic turbulence heat the spiraling material until it shines with brilliant, violent luster. Spectacular, powerful jets can be launched far into space from the active regions near these abysses, energized by complex processes involving rapid rotation, twisted magnetic fields, and the hot, surrounding plasma. The silent black hole itself, of course, emits absolutely no ordinary light from within the silent sanctuary of its horizon. The dazzling cosmic display arises entirely from the doomed matter that has not yet crossed over. This crucial distinction is unfortunately often lost in our dramatic, popular depictions. A black hole encircled by a luminous disk is not itself glowing. Rather, it is the silent, shadow-draped abyss around which nearby material is having an exceptionally turbulent and difficult day. Colossal, supermassive black holes quietly reside at the very hearts of most large galaxies, harboring millions or even billions of times the massive weight of our own sun. Their mysterious origins and dramatic growth remain some of the most captivating and active areas of modern astronomical study. Some may have emerged from the primordial collapse of the universe's earliest massive stars, while others may have formed directly from the collapse of giant, pristine gas clouds. Titanic mergers and vast, epoch-long periods of gravitational feeding eventually allowed them to grow to such truly enormous proportions. Though their intense gravity profoundly influences the stars in their immediate neighborhood, it does not actually hold an entire, sprawling galaxy together on its own. Indeed, the mass of even a supermassive black hole is usually quite modest when compared with the staggering total mass of its host galaxy and its surrounding dark matter halo. It merely dominates its immediate central domain, whereas the grander, elegant galactic structure depends on a much more widely and gracefully distributed ocean of matter. When actively and voraciously feeding, these cosmic titans can power brilliant quasars, which shine as some of the most radiant objects in the grand tapestry of the universe. Vast streams of gas, falling relentlessly inward, release an immense torrent of gravitational energy just before crossing the fateful event horizon. This swirling, superheated disk of surrounding matter can easily outshine the collective brilliance of all the stars within the entire host galaxy. Thus, gravity, usually so quiet and unseen, becomes the sole architect behind a magnificent cosmic beacon visible across truly enormous, unfathomable distances. Yet, even in this grand display, gravity does not act entirely alone. Powerful magnetic fields twist and wind dynamically through the glowing disk. Fierce radiation pushes relentlessly against the falling matter, while violent collisions heat the dense gas to extreme temperatures. Countless particles interact in deeply complicated, intricate ways. Gravity masterfully creates the grand environment and controls the overall cosmic motion, while these other fundamental forces delicately shape the finer details. This harmonious partnership appears endlessly throughout the vast universe. Gravity gracefully gathers, patiently compresses, and methodically organizes the cosmos. Meanwhile, other forces subtly determine exactly how matter resists, heats, shines, reacts, and transforms its state. A serene planet exists primarily because gravity pulled primordial material together into a sphere, yet its solid, enduring surface depends entirely on the delicate electromagnetic bonds holding atoms together. A majestic star exists because gravity relentlessly compresses its dense core, but its radiant, life-giving energy flows from profound nuclear reactions. A mysterious neutron star survives only because quantum and nuclear effects stubbornly resist further gravitational collapse. Gravity becomes overwhelmingly dominant at truly large scales, partly because it always, without exception, attracts under ordinary physical conditions. While positive and negative electrical charges can easily cancel one another out, rendering cosmic matter almost completely neutral overall, gravity knows no such balance. It has no familiar negative mass to cancel out its positive influence. Consequently, every single contribution adds incrementally to the total gravitational pull. It is also remarkably long-ranged. Though its strength naturally decreases with immense distance, it never reaches a definitive, simple edge where its presence becomes completely absent. The Sun quietly influences distant, lonely objects. The massive Milky Way affects its nearby satellite galaxies. Colossal galaxy clusters pull gently yet inexorably on one another across unimaginably vast regions of space. Over immense stretches of time, even the weakest gravitational effect can completely reshape cosmic motion, for this extraordinarily long reach allows gravity to sculpt the universe slowly and patiently. A violent collision is not always needed to enact change. Planetary orbits can shift and drift over millions of quiet years. Majestic galaxies can slowly draw closer together over billions of years. Stars crowded in dense, ancient clusters can dynamically exchange kinetic energy through repeated, close encounters. Young planets can gradually migrate through their parental disks of gas and dust. Moons can drift slowly outward or inward as shifting tides quietly transfer energy and rotational momentum. Our own Earth and the Moon provide a beautifully gentle example of this cosmic dance. The Moon's gravity continuously raises tides across Earth's oceans. Because Earth rotates much faster than the Moon completes its orbit, the rising tidal bulges are carried slightly ahead of the direct gravitational line connecting them. Through this subtle offset, their mutual gravitational influence gradually transfers precious rotational energy from the Earth to the Moon. Consequently, Earth's rotation slowly decreases over time, while the Moon gradually moves farther away into space. These changes are imperceptibly small over a single human lifetime, but gravity has no objection to eternal patience. Given enough time, even the tiniest transfers of energy can become monumentally important. Days on the early, primordial Earth were significantly shorter, and the Moon hung much closer in our night sky. This beautiful system has been evolving continuously ever since. These very same tidal processes can also intensely heat moons orbiting the solar system's giant planets. A moon following a slightly stretched, eccentric orbit experiences constantly changing gravitational stress. As its interior flexes under these forces, friction produces immense internal heat. This deep warmth can drive spectacular volcanic activity or help maintain vast, liquid oceans beneath an otherwise frozen, icy surface. Gravity therefore shapes not only celestial paths, but also the internal, hidden environments that may ultimately affect whether a world can support intriguing prebiotic chemistry. Jupiter's volcanic moon Io is heated intensely by this constant tidal flexing and is entirely covered with active, glowing volcanoes. Nearby Europa may well contain a vast, global ocean beneath its cracked ice sheet, with tidal energy helping to prevent complete freezing. Far from the nurturing warmth of the sun, gravity beautifully provides another vital source of energy. Yet, near the ravenous depths of black holes, this tidal sculpting turns violently destructive. A wandering star passing just a bit too close can be violently pulled apart. Its near side accelerates much faster than its far side under the extreme gravitational gradient, until the star's own self-gravity can no longer hold its structure together. While some of the stellar material escapes into the dark void, a significant portion falls relentlessly toward the black hole, forming a hot, brilliantly bright stream of gas. These dramatic tidal disruption events serve as bright flares in the dark, allowing astronomers to study otherwise quiet, invisible black holes. In these silent depths, a black hole suddenly becomes noticeable only because an unsuspecting star has wandered into the wrong cosmic region, tragically converted into a fleeting, brilliant signal. Gravity does not need to deliver a physical strike to the star. Instead, it gently yet relentlessly separates the paths of its different parts until the fragile star can no longer remain a single, unified object. Still, even this cataclysmic destruction of a star does not mean that the underlying fabric of spacetime has somehow failed. The local geometry of the universe may become incredibly extreme, yet it faithfully continues guiding drifting matter according to highly predictable, elegant rules. This cosmic sculpture can be violent and chaotic without the sculpting medium itself ever truly breaking down. The true limits of nature begin to appear only when gravity ruthlessly compresses matter far beyond every known form of physical support, or when it drives the local curvature toward extreme conditions where the equations of general relativity ultimately predict a singularity. That is precisely where the quiet, patient sculptor begins to work with unimaginable pressures and staggering densities that deeply challenge the very scientific tools we use to describe them. A normal star can courageously resist this inward pull. A dense white dwarf can resist even more stubbornly. And a tightly packed neutron star can endure extreme conditions that would instantly crush ordinary matter beyond all recognition. Each successive stage reveals yet another heroic level of support, and each of these supports possesses its own absolute boundary. If one adds enough mass, removes enough vital energy, or disturbs the delicate balance severely enough, gravity inevitably resumes its relentless collapse. The next stage is not simply a stronger, denser version of an ordinary star. Rather, it represents a profound, fundamental change in the very structure of spacetime immediately surrounding the object. Dark horizons can form, and even swift light can become permanently trapped. The future paths of all nearby matter can be redirected inward in an absolute way that no physical pressure can ever reverse once that critical, invisible condition is crossed. To understand how incredibly close this process comes to breaking the very fabric of spacetime, we need to closely follow the majestic lives of the largest stars into their final, dramatic moments. There, in those extreme realms, gravity no longer shapes matter gently over billions of peaceful years. Instead, it acts in mere, fleeting seconds, violently compressing massive stellar cores, driving spectacular explosions, and relentlessly forcing matter towards exotic states where the familiar, reassuring structure of space and time begins to face its most severe and unforgiving test. The largest and most brilliant stars do not approach their final, fateful moments quietly. For most of their grand lives, they steadily maintain the same basic, harmonious agreement that keeps every stable star in the cosmos intact. Gravity constantly pulls the stellar material inward, while the immense thermal pressure from the hot, churning interior pushes resolutely outward. This delicate balance is never truly permanent, but it can wonderfully last for millions of quiet years. Then, inevitably, the precious nuclear fuel begins to run out. The internal structure begins to shift, and gravity starts asking demanding questions that matter can no longer easily answer. A massive star lives under far greater, more crushing pressure than a modest star like our Sun. Its own colossal weight compresses the core so incredibly strongly that nuclear reactions proceed at an extraordinary, frantic rate. Vast oceans of hydrogen are rapidly converted into helium. Later on, that very helium is used to build increasingly heavier elements. As one vital source of fuel becomes completely exhausted, The core contracts tightly and heats up intensely, making another, deeper stage of nuclear fusion possible. This continuous, desperate process creates a beautifully layered cosmic interior. Near the outer envelope, lighter elements quietly remain, while deeper down in the hot depths, much heavier elements are being rapidly produced. The aging star begins to closely resemble an onion, though an onion with a blazing surface hot enough to make any attempt at chopping it a fairly brief and perilous experience. Each distinct layer contains different nuclear reactions, and each unique reaction helps provide the essential energy needed to resist the constant pull of gravity. The sequence continues gracefully through several elements, but it eventually and inevitably reaches iron. Here, iron creates a sudden, serious problem. Earlier fusion reactions routinely release energy when lighter nuclei eagerly combine. That abundant energy helps heat the star and maintain its crucial, outward pressure. However, combining iron into heavier elements does not release energy in the same useful, life-sustaining way. Instead, it demands and absorbs precious energy. The core can therefore rapidly reach a point where it is still gaining iron, but is no longer gaining enough vital support to survive. Gravity, ever persistent, continues pressing relentlessly inward. The mighty pressure that once held the vast star stable begins to weaken and fade. The beautiful balance that lasted through the star's entire life can suddenly fail with remarkable, terrifying speed. The cold iron core does not need to be nearly as large as the whole star. It may contain an astonishing amount of mass, highly comparable to our own sun, tightly packed into a claustrophobic region much smaller than the Earth itself. This celestial material is unimaginably hot and incredibly dense. Yet sheer temperature alone cannot hope to stop the dramatic events that must follow. Once the fragile core finally passes its critical limit, it inevitably begins to collapse inward. At first, this sudden collapse makes the dying core grow intensely hotter. Under more ordinary physical conditions, heating a gas naturally increases its internal pressure, helping it stubbornly resist further compression. Yet deep inside the collapsing core, several relentless physical processes actively work against that saving grace. Fierce, high-energy light begins violently breaking the stubborn iron nuclei into much smaller pieces, a destructive process that greedily consumes precious thermal energy. Desperate electrons are forced deep into protons, swiftly producing neutrons and releasing ghostly particles known as neutrinos. This tragic transformation drastically reduces the outward pressure previously provided by those electrons. Thus, the vulnerable core loses its vital support at the very desperate moment when relentless gravity is demanding even more of it. Stellar matter falls precipitously inward at a significant, terrifying fraction of the speed of light. A massive structure far larger than a planet can change completely and utterly in less time than it takes a mortal mind to decide whether they just heard a faint sound outside. The catastrophic collapse continues relentlessly until the central matter reaches an absolutely enormous, unthinkable density. Familiar atomic structures can no longer survive in their gentle, everyday form. The core transforms into a dense sea of mostly neutron-rich matter, and strange new forms of quantum pressure begin desperately resisting further compression. The deepest inner region suddenly and violently stiffens. Outer material, still falling helplessly inward, violently strikes this newly compressed core and slows down with sharp, abrupt force. This monumental impact produces a powerful shockwave that immediately begins moving outward. A simplistic picture suggests that this shockwave should easily tear through the entire star, causing a spectacular explosion almost immediately. Yet in more detailed, realistic models, the shockwave can rapidly lose its vital energy and stall. The stubborn star is not so easily persuaded to explode merely because the first violent attempt looked highly promising. It is at this critical stage that neutrinos become profoundly important. Incomprehensibly huge numbers of them are frantically produced during the violent collapse. These ghostly particles usually pass effortlessly through ordinary matter with almost no interaction whatsoever, but the collapsing core has become so incredibly dense that even these swift neutrinos struggle desperately to escape immediately. As they slowly fight their way outward, a fraction of their immense energy can help miraculously revive the stalled shockwave. This full, magnificent process is deeply complicated and remains a highly active subject of modern scientific research. Stellar rotation, powerful magnetic fields, chaotic turbulence, the star's original complex structure, and the mysterious behavior of matter at extreme density all profoundly affect the final outcome. The glorious general result, when this cosmic explosion successfully occurs, is a breathtaking core collapse supernova. The outer layers of the dying star are violently thrown into deep space at a truly tremendous speed. For a fleetingly short period, this single explosion can shine far brighter than billions of ordinary, quiet stars combined. This cataclysmic event systematically produces and generously distributes countless heavy elements across the cosmos. Precious material that spent millions of silent years buried deep inside the star is scattered widely into the surrounding galaxy, where it may eventually become a vital part of new stars, newborn planets, solid rocks, vast oceans, and even complex living organisms. A supernova is therefore simultaneously a tragic ending and a magnificent, fertile source of raw cosmic material. The great star loses almost all of its familiar outer structure, but its liberated elements continue actively participating in the grand story of the universe. Patient gravity may eventually gather these scattered elements into another swirling cloud. A brand new star may form, and vibrant planets may slowly grow around it. Much later in time, a conscious being on one of those far-off planets might look wonderingly upward into the night sky and ask why the universe appears to have made everything so beautifully complicated. Yet it is within the dark central remnant where our fundamental question becomes far more serious. If the remaining, battered core is sufficiently light, it can eventually settle down as a quiet neutron star. This incredible collapse has compressed far more mass than our entire sun into a tiny, dense sphere spanning only a few tens of kilometers across. The exotic matter found there is entirely unlike anything naturally existing on our gentle Earth. A neutron star is not simply a giant, chaotic ball made from loose neutrons. Rather, its highly complex structure may include several distinct layers. The rigid outer crust contains tightly bound nuclei and electrons held under absolutely immense pressure. Deeper, mysterious regions become increasingly and profoundly neutron-rich. Even farther in, the extreme matter may contain flowing free neutrons, superconducting protons, exotic, unusual particles, or other bizarre states of matter that still remain deeply uncertain. Scientists can patiently study neutron stars. Through the meticulous measurement of their immense masses, their compact radii, their dizzying rotation, their faint radiation, their gradual cooling, and their violent behavior during cosmic collisions. These delicate observations help researchers gradually narrow the possible, yet still elusive, descriptions of matter under such extreme and unimaginable density. Even so, the exact, mysterious condition of the deepest, most secluded core remains profoundly unknown, shielded forever from our sight. Yet, what remains absolutely clear in this cosmic tapestry is that even these mighty neutron stars possess their own inevitable limits. The delicate quantum and nuclear effects supporting their colossal bulk can resist the relentless, crushing pull of gravity only up to a certain critical amount of mass. The exact maximum weight they can bear depends entirely on how this ultradense matter behaves under pressure, which is precisely why measuring these exceptionally heavy neutron stars is so incredibly important to modern physics. Each newly confirmed celestial object whispers to physicists that subatomic matter must be stiff and resilient enough to support at least that monumental amount of weight. A weary neutron star nearing its maximum theoretical mass is already pushing the very fabric of spacetime into a severe, dramatic curvature. Indeed, a clock placed near its glowing surface would run significantly and noticeably more slowly than a distant, unaffected clock ticking away in the quiet void. Even the swift light striving to leave the star's powerful grasp loses its vital energy, reddening as it climbs. The pathway of this escaping light bends so severely that a distant observer can marvel at more than half of the star's spherical surface all at once. The star may spin frantically, rotating hundreds of times each fleeting second. This rapid, dizzying rotation slightly flattens its shape at the poles and can help support its massive frame against an untimely gravitational collapse. Such a rapidly spinning object gains a crucial, though temporary, advantage because this furious rotation actively resists some of gravity's relentless inward pull. Yet, this is by no means an unlimited advantage. The star simply cannot rotate arbitrarily fast without eventually becoming violently unstable or flinging its precious matter away into the dark cosmos. Intense magnetic fields can also profoundly affect the star, especially in the rare, highly magnetized beasts known as magnetars. But even these titanic forces do not provide a simple or easy escape from the ultimate mass limit. If the dense core becomes too heavy, the patient hand of gravity eventually wins the struggle. There are several tragic ways this cosmic downfall can happen. The neutron star may be born predestined for doom with too much initial mass directly after a violent supernova. Alternatively, it may slowly siphon material from a helpless companion star. It may also tragically merge with another passing neutron star in a brilliant flash. Or it may begin its active life supported partly by its own rapid rotation, only to collapse much later as it slowly but surely loses its precious rotational energy. That delayed, quiet collapse would indeed be an incredibly strange and haunting event to witness. For a quiet, deceiving stretch of time, the star might appear perfectly stable. It would continue to spin gracefully, emit its steady radiation, and behave like an extremely compact but still recognizable luminous object. But as the silent friction of time slowed its rotation, that vital extra support would slowly weaken and fade. At a sudden, critical point of vulnerability, the star would catastrophically collapse into a black hole. From the safe distance of the outside universe, this dramatic transition might appear to happen in the blink of an eye. The glowing surface would rush inward, and the surrounding spacetime curvature would grow exponentially steep. A mysterious horizon would inevitably form once enough dense mass had been tightly compressed within a sufficiently, impossibly small region of space. Once that absolute boundary appeared, any light trying to escape from the dark inside could no longer reach the hopeful eyes of distant observers. Nothing needs to violently strike the dying star from the outside. No grand cosmic hammer is required to shatter it. The overwhelming, quiet weight of the star itself fully provides the necessary condition for its own demise. Gravity simply takes the tremendous energy and matter already present inside, concentrating them deeper and deeper until the very structure of local spacetime changes in a fundamental, irreversible way. This is the first profound place where the abstract idea of pushing spacetime too far begins to sound entirely reasonable and tangible. The collapsing star does not violently tear the fabric of spacetime like a piece of worn cloth. Instead, it elegantly curves and warps spacetime until a localized region becomes completely and causally separated from the rest of the outside universe. Events occurring inside this dark realm can still naturally influence other internal events, but they can never again send their desperate signals beyond the silent boundary of the horizon. The simple word horizon is deeply important here because it describes a soft boundary in information, rather than a hard, physical shell. An event horizon is not constructed from any physical matter. It does not possess a solid, rigid surface that a falling object would violently crash into. Rather, it solemnly marks the absolute point of no return, beyond which no future directed path can ever lead back to the outside world. For a relatively small black hole, the fierce tidal effects lurking near the horizon can be extremely and devastatingly strong. Any unfortunate object falling toward it would be stretched violently, because the side closer to the yawning black hole follows a noticeably faster and different path than the side farther away. This agonizing difference in gravitational pull can easily become strong enough to pull physical matter completely apart even before it crosses the dark threshold. Yet, a truly gargantuan, very large black hole can be surprisingly different. Its immense horizon lies comfortably farther from the dense central region, where the tidal changes across a fragile human body may feel relatively gentle and mild. Thus, a solitary, falling observer could slip quietly across the invisible threshold of the horizon without experiencing any sudden, violent jolt at that precise, fateful moment. Behind them, there would remain absolutely no route of escape, no path leading back to the familiar, welcoming universe. Yet the immediate local environment would whisper no warning, entirely failing to announce the solemn crossing. To our human minds, this seamless transition can feel deeply unsatisfying, for we instinctively expect great cosmic boundaries to possess some visible, dramatic form. A rugged coastline clearly delineates the solid land from the restless, churning sea, and a simple doorway separates one quiet room from another. In much the same way, the event horizon separates the possibility of a hopeful escape from the grim reality of an unavoidable inward descent. Yet this monumental boundary possesses no physical, local marker to denote its existence. Its true significance depends not on the passing moment, but on the unfolding, grand tapestry of the entire future of spacetime. To truly discern whether a specific event lies safely inside a black hole, we must ask a fundamental question. Can the fragile light emitted from that event ever escape to reach the distant, waiting cosmos? This profound requirement transforms the horizon into a global, rather than localized, feature of the universe. It is defined not merely by the fleeting occurrences happening nearby at a single moment, but by how the entire fabric of spacetime dynamically develops over eternity. During the cataclysmic, dying collapse of a massive star, this silent horizon can actually form well before the falling material ever reaches the dense central region. Any faint light emitted after that fateful formation remains hopelessly, eternally trapped within. Meanwhile, the doomed star continues its relentless inward collapse inside, forever hidden from the prying eyes of the distant universe. On the outside, the surrounding gravitational field slowly and serenely settles into the characteristic, smooth geometry of a quiet black hole. A patient, distant observer watching this dying stellar surface would see its outgoing signals grow increasingly weaker and more desperately delayed as the shrinking surface creeps closer to the horizon. The struggling light becomes progressively and heavily redshifted, stretching into longer, dimmer wavelengths. Viewed through the lens of the distant observer's chosen coordinate time, the falling surface appears to slow to a virtual standstill, gradually fading into a ghostly whisper. Yet, for the falling material itself, personal time flows quite normally, carrying it forward without hesitation. It effortlessly crosses the threshold of the horizon and continues its relentless, silent journey inward. There is no logical contradiction inherent in these two starkly different perspectives, because they merely compare events in fundamentally different ways. The beautiful mathematics of relativity gracefully allows both accounts to coexist, without requiring either brave observer to be mistaken. Once safely inside the horizon, the inexorable collapse continues unabated. Classical general relativity solemnly predicts that this falling matter must eventually reach a singular point of no return, a singularity. This mysterious state is not merely some ordinary point where the density of matter becomes inconveniently or unimaginably high. Rather, it represents a profound and catastrophic failure in our traditional description of space and time, a place where physical paths can abruptly end after a strictly finite amount of personal time. The very curvature of spacetime becomes infinitely unbounded within our classical mathematical model. At this threshold, the elegant theory can no longer provide a complete or meaningful continuation of the story. While that sounds very much like the violent tearing or breaking of spacetime itself, a great deal of intellectual caution is needed. The singularity may indeed be a genuine, terrifying feature of nature, or it may simply signal that the equations of general relativity have been stretched far beyond their valid, physical range. Most modern physicists expect that subtle quantum effects will begin to matter deeply before an actual, mathematically infinite density is ever reached. The daunting problem is that these extreme conditions are forever hidden behind the opaque horizon, lying far beyond anything our current, modest experiments can hope to reproduce. We simply cannot place our delicate instruments at the dark center of a black hole, nor can we ever receive a precious signal describing that final, mysterious state. Instead, we must patiently build elegant theories that agree with all known physics, while searching diligently for any subtle, lingering effects that might manifest on the outside. Several fascinating ideas have emerged to replace the bleakness of the classical singularity. Some theoretical models suggest that gravity itself becomes intensely repulsive at extremely small scales, halting the collapse in its tracks. Others propose that the fabric of spacetime is woven from discrete, fundamental structures that cannot be compressed without limit. Certain alternative models replace that infinitely sharp central point with a small, finite region dominated by active quantum gravitational effects. There are also imaginative proposals involving a cosmic bounce, where the collapsing matter is reborn, leading directly into another, expanding region of space. Some even suggest deep connections with white holes, those hypothetical, glowing cosmic objects from which matter can wildly emerge, but never enter. While these possibilities are immensely interesting and romantic, none has yet been confirmed as the uniquely correct description of a real black hole's mysterious interior. Yet, this profound uncertainty should never be mistaken for complete and utter ignorance. General relativity still provides remarkably reliable and beautiful predictions everywhere outside that deepest, darkest region. With growing precision, astronomers can measure the graceful motion of distant stars orbiting black holes, study the swirling, hot gas near them, detect the ripples of gravitational waves from violent mergers, and capture breathtaking images of glowing material dancing close to their horizons. In all of these extreme cosmic environments, the theory has triumphed, passing every direct test with flying colors within the ever-increasing precision of our modern measurements. Yet, the profound scientific dilemma begins precisely at the point where the fabric of spacetime curves so exquisitely and extremely that the mysterious realm of quantum gravity is fully expected to take over. This threshold creates an unsettling, strange division in our understanding. For much of its dramatic journey, the collapse of a dying star is understood remarkably well. Elegant nuclear physics explains the fueling fire, while relentless gravity explains the crushing compression. Particle physics, too, gracefully helps us describe the intricate details of the ultimate core collapse. Sophisticated computer models can faithfully track the explosive shock waves and elusive, ghostly neutrinos, while general relativity beautifully describes the inevitable formation of the event horizon. Then, deep inside this shrouded dark heart, our scientific explanation inevitably reaches an insurmountable boundary. This boundary does not arise because passionate physicists have run out of intellectual enthusiasm or curiosity. Rather, it arises because the two strongest, most enduring theoretical frameworks available to humanity describe the natural world in fundamentally different languages. General relativity elegantly treats the vast continuum of spacetime as a smooth, continuous fabric. In stark contrast, quantum physics meticulously describes physical systems through discrete quantum states and energetic interactions. Both frameworks perform extremely well in their respective domains, yet harmoniously combining them under the violent, extreme conditions deep inside a black hole remains one of modern science's most difficult endeavors. Dying stars therefore become grand, natural cosmic experiments that relentlessly push several of our finest theories to their absolute physical limits. A majestic, massive star spends its long life patiently building heavier and heavier elements in its core, yet its sudden, cataclysmic death ultimately compresses this ancient matter far beyond normal atomic density. If the remaining stellar remnant is sufficiently heavy, this cosmic event creates a strange region where smooth, continuous spacetime may eventually cease to be an adequate description of reality. Yet, not every massive star follows precisely this same tragic route. Some stars gently shed much of their outer material through powerful, sweeping stellar winds long before they die. Others intimately exchange matter with a close companion star, while some rotate rapidly, spinning wildly through the cosmos. Their unique chemical composition also deeply affects their overall evolution. A star born in the early universe with fewer heavy elements may successfully retain more of its total mass, ultimately producing a significantly heavier remnant. In certain rare cases, such a star may quietly collapse with only a weak, barely visible explosion, where much of its massive material falls directly into the newly forming black hole. Astronomers sometimes poeticize this quiet demise as a failed supernova. The dying star may brighten briefly in a fleeting whisper of light, or simply disappear altogether from our view, leaving nothing but a silent black hole where a grand, luminous object once proudly stood. There may also exist stars so immensely massive that they encounter another, far more violent form of cosmic instability. At extremely high internal temperatures, highly energetic light can spontaneously produce pairs of physical particles and their corresponding antimatter partners. This sudden transformation drastically reduces the outward thermal pressure supporting the heavy core. The core rapidly contracts, nuclear fusion accelerates dramatically, and the resulting titanic explosion can become enormously, devastatingly powerful. For certain specific mass ranges, the star can be completely, violently destroyed in this manner, leaving behind no compact remnant whatsoever. For even larger stellar cores, however, the immense energy released may still utterly fail to reverse the overwhelming gravity of the collapse, silently allowing a heavy, massive black hole to form. The exact physical outcomes depend delicately on the star's initial mass, chemical composition, rotation speed, and historical mass loss. These grand events show us that pushing the fabric of spacetime to its ultimate breaking point is not controlled by a single, simple number. Total mass certainly matters, but so too does its dense concentration. A vast, diffuse cosmic cloud can contain more than enough raw material to birth many individual stars without ever forming a single event horizon around the entire cloud. Conversely, that exact same amount of matter, compressed tightly into a smaller, denser region, may readily collapse into a black hole. The geometric shape and dynamic motion of the collapsing material matter deeply, too. Rapid rotation can significantly delay the collapse, while outward pressure can support the celestial object. Radiant radiation can drive material far away. Powerful magnetic fields can dynamically transfer energy, and a nearby companion star can continuously add or remove mass. The intricate path toward an event horizon is determined by the full, complex physical condition of the system, not merely by placing a star on a simple cosmic scale. Yet, there remains a beautiful general rule underlying all of this complex detail. When enough mass and energy become closely confined within a sufficiently small region, an event horizon can inevitably form. Once it forms, the dramatic central evolution of what lies within becomes forever hidden from the outside world. This is not a violent tear that suddenly opens into an empty, absolute nothingness. Rather, it is a profound change in how physical events can communicate with other events. The outside universe continues to spin normally. Nearby planets can peacefully orbit the black hole, hot gas can circle it in glowing disks, and light can pass by at a safe, respectful distance and easily escape. A black hole harboring the exact same mass as a normal star produces precisely the same distant gravitational effect as that star, provided, of course, that its rapid rotation and other intricate physical details are treated with appropriate mathematical care. If our own life-giving sun were somehow miraculously replaced by a silent black hole of the exact same mass, our Earth would quietly continue along almost precisely the same orbital path. This fragile planet would not be violently pulled inward simply because its central guardian had transformed into an unseen abyss. The true, devastating crisis would instead be the sudden, absolute disappearance of warm sunlight, a catastrophic loss that would quickly make our continued orbital stability feel like a very small and cold consolation. These cosmic entities only become genuinely dangerous when wandering objects venture too closely to their boundaries, not because they actively drag the entire universe toward them like insatiable drains. Indeed, their gravity behaves according to the very same elegant principles that govern any other mass in the cosmos. What truly makes them so extreme is the staggering amount of mass concentrated deep within the event horizon, and the sheer, severe intensity with which spacetime bends and curves nearby. The dying, collapsing star has therefore not spawned a monstrous anomaly that defies the laws of physics. Rather, it has birthed an exotic object beautifully predicted by those very laws, one that forces us to carefully distinguish between an incredibly strong curvature of space and an actual, profound failure of our scientific descriptions. The mysterious horizon itself can be remarkably smooth, and the geometry of the surrounding spacetime can still be meticulously calculated. The apparent breaking point of reality lies much deeper within, at the dark threshold where all classical paths abruptly end. Before we can truly decide whether that hidden, shadowed region represents a genuine fracture in the fabric of reality or merely a temporary gap in our current, evolving knowledge, we must pause to examine these black holes much more closely. Their quiet horizons, turbulent interiors, cataclysmic mergers, and unfathomable singularities offer the closest thing physics has to a literal edge, a boundary where spacetime may finally cease to behave as a familiar, continuous geometry. A black hole is most often described in the popular imagination as a desolate place where gravity becomes so immensely strong that absolutely nothing can escape its grasp. While that simple description remains highly useful, it can unfortunately make a black hole sound like a monstrously powerful vacuum cleaner, endlessly roaming through the void of space and greedily devouring anything that happens to drift nearby. In truth, real black holes are far less eager, far more patient than that. They do not actively hunt down innocent stars, aggressively inhale entire galaxies, or needlessly pull distant, orbiting objects out of their stable paths without cause. Viewed from a safe distance, their gravitational influence behaves almost indistinguishably from the gravity of any ordinary cosmic body possessing the exact same mass. The true, dramatic difference only manifests when a traveler ventures perilously close to the black hole's edge. There, the fabric of spacetime is warped so profoundly that the available paths forward begin to twist and change in ways that possess no ordinary equivalent in our daily lives. In those strange depths, light itself can temporarily orbit in glowing, ghostly rings. Clocks can disagree by astonishingly vast amounts of time. Falling matter can be violently compressed and heated until it shines far more brilliantly than entire galaxies of stars. Yet, once crossing beyond the fateful event horizon, every conceivable route into the future leads inexorably, inevitably further inward. This absolute boundary makes the event horizon the most natural place for our journey to begin. It is the defining feature that forever separates a true black hole from any other dense, compact cosmic object. A dense neutron star, for instance, still possesses a tangible physical surface. Matter plunging toward it will violently strike that solid ground, heating it intensely and releasing a fierce burst of radiation. A black hole, by stark contrast, possesses no known material surface at its horizon. Any falling matter simply slips silently through the invisible boundary and continues its journey inward. Consequently, a distant, patient observer will never receive a final signal marking the exact, fleeting moment when the traveler crosses over. The fragile light signals sent back from the falling object take longer and longer to escape the tightening grip of gravity as the object draws nearer to the horizon. Each subsequent signal arrives noticeably weaker, shifted to a deeper, ghostly red, and more agonizingly delayed than the one that came before it.